feedback, which will help us, of course, in planning the next strings meeting. Okay, so now we're ready to start the session. So Stefan Sieber will be the first chair.
Okay, thank you very much. I'm honored to be the chair for this morning session. And our first talk will be a review talk on celestial amplitudes by Sabrina Pasterski from Princeton University. So please start, Sabrina.
Awesome. Well, good morning, everybody, and thank you so much for having me. I am very happy to be
talking
about
which will help us, of course, in planning the next strings meeting. Okay, so now we're ready to start the session. So Stefan Sieber will be the first chair.
Okay, thank you very much. I'm honored to be the chair for.
Are you hearing the same loop as me? Yep. Okay, good. Okay. Well, now that we've got to have some fun there, basically, I'm happy to be starting to talk about this program, which we have a lot of people here who have also worked on it. Let's start with what celestial holography is and what celestial amplitudes are. So the title of the review talk is Celestial Amplitudes, but first it sits within a bigger program that I guess you could call celestial holography, and that's purporting a duality between gravitational scattering in asymptotically flat spacetimes and a CFT that's living on the celestial sphere. So if you look up at the night sky, there's this, for d equals 4, a 2D celestial sphere, where we're trying to find a dictionary between S matrix elements and correlators there. So celestial amplitudes are the central object of that. So basically they're S matrix elements in a basis for the scattering states, such that they're guaranteed to transform as conformal correlators in codimension 2. So in this case, for this talk, I'm going to be looking at 4D and then a 2D celestial sphere. Okay, so the plan for today is the following. So we're going to break it into two parts, where the first part is going to be a bit of a review, taking a step back to the original motivation for why would we be looking at the celestial CFT. And in the second part, we're going to go through different aspects of celestial amplitudes to kind of see how the structure of the dictionary and paths forward in that. So of course, everything that I presented today, it's a review talk, is thanks to a lot of people. So I've tried to list many of them as possible here, but of course it's a growing list, and many interesting contributions I won't be able to talk about in detail today, but fortunately we have a discussion session this afternoon, so that time is in Brazilian time, where Andy and Tomasz will be leading that, and so there's plenty of opportunities to go into things that I wasn't able to cover in this talk. Great, okay, so part one of the talk, asymptotic symmetries. First step is to match even just the global symmetry. So when we want to say that there's a dictionary between the celestial CFT and S matrix elements, the symmetries on both sides should be the same. And the first statement is that this is supposed to be a codimension 2 CFT. And so where does that conformal symmetry come from? Well, that's just going to be Lorentz transformations of Minkowski space. So those Lorentz transformations are going to turn into my global conformal transformations of the celestial sphere. And so Lorentz invariance in the bulk is going to translate then into this conformal covariance depending on the external states that we choose to scatter. So also, even though I'm starting with asymptotic symmetries, I want to keep in mind that the end goal here is to connect to amplitudes. So whenever I say something about what's happening in the asymptotic limits of the space-time, I want to connect that to the picture of what I'm doing for my external particle states. So normally I would have a momentum space, a set of on-shell momenta. So if it's massive, it's parameterized by a point on a hyperboloid. And if it's massless, there's a null cone of momentum. And so for S matrix elements, we typically specify the set of on-shell momenta for my in and my out particles. Now in the space-time picture, I would want to take a Cauchy slice and specify the data on that slice. Now, because we were interested in quantum gravity, we want to be able to have the metric fluctuate in the bulk. And so we really want to pin down the free data at the asymptotic boundaries. So we're going to be looking at the conformal boundary of asymptotically flat spacetimes. Okay, so to go about doing that, the first thing is just to look at the Penrose diagram for Minkowski space. Interesting things happen when you add horizons, etc. But for the purpose of this talk, all I'm going to need is asymptotically flat spacetimes, and basically the causal structure is going to look the same here. So the important point for me is the this conformal boundary. So what happens if you look at Penrose diagram for Minkowski space? So we've basically rescaled distances down so we can just look at the causal structure. And the interesting thing about asymptotically flat spacetimes is that they will have boundary components which are null. So we have time like past and future infinity here. space like infinity here. And then we have these S2 cross R null hypersurfaces, which capture incoming and outgoing radiation. So basically a massless particle will enter and exit at antipodal points if it were freely propagating through of scry minus and scry plus. And so that's going to be important for us because when we have this picture of massless scattering, on the one hand, we know that we have this like cone of on-shell momenta. And on the other, in the space-time picture, we're going to have the data where we push our Cauchy slice up to this boundary. Good. Okay. So now, in the interest of, again, connecting something that's we're saying in for asymptotically flat spacetimes to what's happening in the amplitude, we just want to look at the free mode expansion of the field operators. And the nice thing about that is that when you take the large R limit holding U fixed, so again, U is this retarded time here. If I go out to large R, essentially I have a very rapidly oscillating phase in the dot product between the direction that I'm pointing at on the night sky and the direction of the momentum of the particle. And so because of that, basically the angular dependence in this integral localizes to a delta function. So I end up seeing that the large R limit of my metric perturbation will essentially capture the in and the out modes. So in the case that if you have a vacuum on the one side, you'll kill half this term. But basically here, what I'm saying is you see that only one integral is left over. So the S2 part goes away. And essentially now this U dependence turns into an omega dependence if you Fourier transform. So that's the connection here, which is going to be good because essentially we're going to want to relate soft theorems in the standard amplitudes picture to what are going to be asymptotic symmetries in this picture. Good. Okay. And just a quick aside, if we want to do the same thing for massive particles, you can also. And in that case, it's basically that if you have a particle with a definite momentum at the end, essentially if you hyperbolically like foliate Minkowski space, then the point on that asymptotic hyperboloid that it hits would correspond to the momentum direction. And of course, in the one case, that's like the curvature there is corresponding to a large x squared, versus in the other case, this hyperboloid size is set by the mass of the particle in a momentum space picture. So one could do a similar type of saddle point approximation, and I point to references completely unloaded to see that worked out. Okay, so I said that the goal of this part of the talk was to talk about asymptotic symmetry. So let's go about doing that. So when we're interested in gravitational scattering in these asymptotically flat spacetimes, you're looking at solutions to Einstein's equations with vanishing cosmological constant and some assumptions about the matter stress tensor. So this was done by Bondi, Vandenberg, Metzner, and Sachs back in the 60s. And the key point for takeaway here is that essentially you're looking at the metric and perturbations of the metric near future null infinity now instead of at some other boundary. So in this case, you have the flat metric in the first line, and then the corrections to that are all parameterized by subleading powers in 1 over R. And so again, this is how you would identify here the radiation is in these angle-dependent terms that are just subleading to the round sphere metric, which has a different form, so you can extract it from the ZZ component. And the point of doing this expansion, so first of all, if you really want to study the phase space and the symmetries of this class of solutions, you're going to first have to pick a convenient gauge so that you can make sense of what each of the terms in those in the metric are. And then you want to also specify physical fall-offs. So this Bondi gauge metrics already, that process has already been done. And the fun thing about it is that there's this balance that you have between what fall-offs you want to allow for, say, both the large R dependence and then the U behavior of the metric along future null infinity, or the same thing for past null infinity. And you don't want to allow like unphysical solutions, but you also don't want to kill physical solutions. So that's a bit of a balance there. And then depending on what you do on that side, the residual symmetries are going to change. So, and why I point out that it's a little bit of a balance in the sense that there actually been some, we'll see examples where the asymptotic symmetry group proposal has slightly changed based on trade-offs that one can make there. So the statement of what a residual or asymptotic symmetry is that I have these diffeomorphisms. They're going to change my metric, but they're going to keep the fall-offs. So this expansion in 1 over R relative to the flat metric, even if the coefficients of the expansion changes, the powers in R are the same. And so those sets of diffeomorphisms will preserve that class of solutions. And this asymptotic symmetry group are the ones that basically act on the data that survives in the large R limit. And so my allowed symmetries are the ones that preserve those fall-offs. My trivial ones are the ones that fall off fast enough that they never change the data on my slices. And so the asymptotic symmetry group can be a lot larger than the isometries of any given metric, so like Minkowski space, essentially because it's not supposed to preserve a single metric, it's supposed to preserve a class. And also once you think about the fact that you have generic matter configurations will break any isometries that you'd have, it's good to, I guess, like the natural thing would be to try to identify these asymptotic symmetries as opposed to like sticking to a given space-time and asking what are the isometries, because you would expect that in the large you would be able to see some remnant of Poincare invariance even if the solution itself that you're looking at is not Poincare invariant. So what we find is that, of course, BMS isn't just larger than Poincare, it's infinitely larger. And so the next slide will go into which, in what sense it's infinitely larger, but essentially this is the power or like the stepping off point for this program into celestial holography, is noticing that there is this enhancement of symmetries that we want to make manifest. Okay, so the two sets of symmetries that we'll be interested in for the gravitational case are super translations and super rotations. So in the one case, you can think of, if you look at different points in the night sky, you have the sphere, and then you also have a like time at which radiation hits that sphere or like crosses null infinity. And what a super translation is going to do is let you basically shift the U coordinate independently at different points in the night sky. So this is much bigger than a translation, which would just be essentially like the L equals 1 modes or 0 mode, like of just translating everything with special functions of Z and Z bar that terminate at quadratic order. So super rotations, on the other hand, are going to let you go from just global rotations to local conformal transformations of this celestial sphere. And so this is already kind of the tantalizing hint that, oh, maybe we can define some sort of stress tensor using the fact that basically these transformations are these CKVs like we would see in a 2D CFT. So this is a special aspect of being in 4D versus in 2D. Is like, right, this is the same thing that you see in 2D CFTs where you go from the global conformal group to now these local conformal transformations. Hopefully later in the talk, I'll discuss a little bit more about how you can still apply these same structures in other dimensions. But I did want to point out that right now, this enhancement is special to that. But the nice thing here also is that somehow hindsight is 2020 in the sense that originally, if you wanted to say that I want everything to be globally defined in the celestial sphere, then you'd still knock this back down to Lorentz transformations. And then in the context of celestial CFT, now, because we're basically more okay with having punctured spheres and whatnot, these transformations will basically induce at localized points changes to the round metric. And so that's where these are some point thrown out, debated or whatever. So that's good to keep in mind. Okay, so the next stage of this is to basically understand the extent to which these symmetries are actually realized in the S matrix. And the quick route of seeing that is essentially actually this really nice observation by Strominger, which is that word identities for those asymptotic symmetries are equivalent to just soft theorems in the S matrix side. And so the point of this talk is to use this as motivation for celestial amplitude. So I'm just going to outline like the two features that you would need to basically motivate this. The first thing is that the canonical charges in gravity are going to be codimension 2. So we think of our Cauchy slices living at future null infinity, say, and the same for past null infinity for these two definitions of the charges acting on the in and the out states. And then you have this data that is like, say, the bonding mass or the angular momentum aspect at spatial infinity. And now I can write that, of course, as a total U derivative if I add a corresponding term at the other U boundary. And that trick basically turns it into clearly like a zero energy, like it's a U integral, so it's picking out something zero of zero energy frequency part of whatever is the object that then is left over on the null infinity. And then it turns out you can use constraint equations or whatnot to find out what that is. But intuitively also, because these symmetries are mostly spontaneously broken, except for the ones that the Poincare preserves the vacuum, there's going to be a part of the metric that will shift under doing this diffeomorphism. So to get that shift, there's a term in the chart that's going to be linear in the metric. And so there's some term here where you literally are just plugging in the mode expansion that I pointed out earlier and picking at the zero frequency limit of that. So that will be the quote unquote soft charge that is basically inhomogeneously shifting the metric field when you do some asymptotic symmetry transformation. Okay, so that's all I need from this like wonderful like old story about asymptotic symmetries. The key point here is that not only do you have this equivalence between this asymptotic symmetry group word identities and the soft theorems, but you also are naturally recasting those guys as a 2D conformal field theory word identity. So basically this equivalence was like a lot of papers starting in like 2013, 2014 there, and it's very cool because also from that time, it was noticed that basically the structure of the soft theorems was such that it kind of looked like it could be interpreted in a 2D CFT language. So this celestial holography program and celestial amplitudes program basically is taking that and pushing it just to see how far you can go with the full amplitude. So just to point out what that first example, I guess, is, it's kind of hinting that you really want to go to this 2D celestial CFT interpretation, is that there's some zero energy modes. So here, like I have the U integral of a metric mode that was appearing in my expansion. And so this particular zero mode of the metric is a candidate stress tensor in the sense that within amplitudes, the soft theorem turns into what I can make look like, or Anna and Prahar and Dan can make look like a correlator and a word identity for the stress tensor. And so the point is to unpack the fact that it looks like this. So right now it's like, oh, this is a nice equation I would have from my 2D CFT. But the point is that this insertion of this mode here is coming on the amplitude side from a soft theorem. And then I want to be able to interpret my in and my out states in terms of operators. So already with this picture of what the on-shell momenta are, for massless particles, there's an actual point on the celestial sphere, which they would then go to. But I need to somehow convert their energies into to a basis where they're diagonalized. So essentially, if I want these waves to just be numbers, then I would want to go to Rindler energy eigenstates. And so that's going to kick us off into celestial amplitudes. Great. Okay. So we're done with part one. On to part two. We have now this understanding that the infrared physics via these soft theorems are hiding this infinite symmetry enhancement. Then we can try to take advantage of that by basically turning each of those soft theorems into some currents in this 2D picture. And so in order to then fully go to that 2D picture, we need to have these operators that are have definite H and H bar, and that requires a change of basis for the scattering states. So we just want to now look at the wave packets that we're scattering to talk about amplitudes in the spaces. So I'm going to define a conformal primary wave function to be a function of a point x in my space-time. And then a reference point for the case of 4D and 2D, this is a point on the complex plane. And I demand that it transforms as follows. So essentially, if I have a spin for this field, that's the representation of the Lorentz group here acting. And then I get some conformal weights based on the delta and J when I do the corresponding Mobius transformation in the celestial sphere at the same time as I do the Lorentz transformation. So the easiest way to see what this is to write X in terms of Pauli matrices. And then you have lambda as a function of A, B, C, and D. So these are SL2C. So basically now what I'm going to look at in this context is just the case where the spin matches the magnitude of the helicity. And then also that ones that solve the appropriate source-free equations of motion. Now, if I give you such a solution, and I have my mode expansion of my operator like I'd written up before, and I have a Cauchy slice and I have an inner product, I can just construct an operator that will effectively look like it lives in 2D. And so, right, so what's happening is the X part is being integrated over this inner product. The conformal dimensions of this guy are guaranteed by the wave function that I happen to be scattering. And the W and W bar dependence here to make it look like it's a local operator in 2D is again coming from the fact that these wave functions have this like bulk to boundary propagator type dependence on a point on this plane and a point in the bulk. And so the wave functions roughly will look like the dimensions coming from factors of 1 over negative q dot x. So you can imagine this hyperplane in Minkowski space. That's the normal for that is setting the reference direction where this operator is going to sit on this celestial sphere, which we've kind of projected down to the plane. Now, one other caveat is that these amplitudes will carry additional labels for whether the particles in and out. So from the point of view of the fact that the metric near in the large element fixed U looks like it's like an integral along future null infinity. There's a similar thing where the operator that you think of inserting in a correlation function, the bulk would be at past null infinity. So keep in mind that's a little bit different in the sense that we're saying that there's one celestial sphere instead of two celestial spheres, but adding an extra label to each of the operators in it. And we can at some point talk about going to 2-2 and basically how that analytic continuation there, maybe you can say something. Okay, so for massless particles, which is just the easiest case to do because basically there's only one integral to do, one can quickly see that the wave functions that one write down that transform as follows, as previously said, which this X Lorentz transformation and W Mobius transformation giving a nice prefactor at fun. Those guys are actually going to be up to proportionality constant, just gauge equivalent to doing a Mellin transform of the plane wave. So we are normally scattering just these plane wave packets with some polarization tensors. And just by integrating over the energies with certain weight, I can trade out the energy for conformal dimension. And so also point out that everything I'm saying here can also apply to the case of massive particles. And there, the technical burden, of course, is just that like the transform that you're doing to take you from amplitudes to celestial amplitudes is a little bit more work because there's an extra integral. But again, you're basically using just the SL2C covariance. And so in the context of ADS-CFT, we're more familiar with thinking of the embedding space as something that's formal. And in this context, we're basically taking that embedding space point to be anywhere in that flat space. And so now that's on the position space side of things. And in the momentum space side of things, we actually naturally have a hyperboloid. So here we're basically using a bulk to boundary propagator for the point where the momentum is for the normal S matrix element to boost it up to a reference point that is set by me. So the operator is sitting then at W and it's smeared over the actual momentum space amplitude versus in the massless case, the point in which a particle heads out is naturally fixing the point in the night sky. And then I have to smear over just the energies there. So there's one integral for every particle instead of 3. Great, okay, so the fancy thing here is our object of study. So celestial amplitude will be, for the massless case, this guy. I'm taking my amplitude and I am Mellin transforming it over every energy. So this is my guy here. And so this guy is guaranteed to transform like a correlator of quasi-primaries because the external particle states are now in boost eigenstates. states. So that transform can be thought of as acting on the amplitude itself or on the basis states for my S matrix element. And so we have these transformations for the states after Mellin transforming, and they give us this covariance of the amplitudes. So I have this object that the one, technically it is the image of, in the sense that if you interpret they're saying that like I have my map between S matrix elements and correlators in a 2D CFT, this is the map. But of course, the dictionary, the interesting part of that dictionary is understanding exactly what features of the amplitudes are translating over. So that's what we're going to be getting into. The first step to notice, though, is that I basically invert this transform just fine if the delta are in the principal series. And so this principal series set of dimensions is going to be the ones that capture finite energy radiation. Now, when we look at translations, because everything right now has basically been making Lorentz transformations look really nice, but translations will shift the conformal dimension. And so what one wants to think of is one can still formally write the data off of the principal series in terms of smearing on the principal series. This is something that we were looking into with Done and Poom. But it's natural to kind of think of this paradigm as the data on the principal series is capturing the scattering data for like everything that's not zero energy. But then you want to look at how that amplitude behaves as a function of delta in this complex plane. So we're going to be looking at delta that are off of the principal series and what follows. Okay, so one other thing to point out. So basically I'm trying to point out the things that make it like, okay, so Lorentz invariance gives you this correlator. Great. Now, like this, what about it is weird? Like, can we just go open the yellow book and then do something with it, or do we have to be careful? So the other thing to point out is that essentially this amplitude that you're integrating over, of course, has a momentum conservation constraint in it. So again, in the last slide, I was pointing out that the translation generators shift the dimensions. Well, here they also do this funny business of giving you this delta function in some momentum. So what does that look like? if I just literally want to take some tree level amplitude and write down the celestial amplitude, it's quite easy to do technically because I'm integrating over only the energies. I have a bunch of delta functions there. So I have a delta function from the sum of momenta. And then when I do this integral, I have a scale integral, and I also have the simplex integral. So somehow I basically have like 5 delta functions that are sitting there that can localize up to 5 Mellin transforms. So in terms of spinor helicity variables, right, I'm picking the direction of the particles to stay fixed and finding the modulus of that null vector such that the null polygon closes. So the remaining delta functions that are left over when I am in the case of scattering less than 5 particles will mean that the correlation functions are singular. And so that's not super great from the point of view of trying to like just directly connect to your garden variety 2D CFTs. And so one either gets discouraged or uses that as an interesting, well, in one sense it's a playground to try to like make sure that everything you're taking for granted isn't like technically forced on you by formal covariance. And the other thing is to still to see what happens. So the aim again of this map, doing this map in the first place, was that we wanted to be able to use CFT techniques to learn about amplitudes. So you want to use the powers of these symmetries that you find in the IR to constrain scattering, to constrain gravitational scattering in the bulk. So we're already seeing 2 problems or like issues, which are, first of all, this dual CFT is exotic in the sense that its spectrum is complex. The singular behavior at low point amplitudes is strange. It still is conformally covariant, but it's basically like delta function pieces instead of the ordinary power laws for the 2-point functions of two operators. Meanwhile, the quantity that we want to look at in 4D is also unusual because we're probing energy that's scattered at all scales. So we see that there's this scale integral that's left over that is really looking at the amplitude at all energies. And so if one wants to take it in mind that normally you would have some sort of effective theory that is only valid up to some cutoff scale, then this is going to be a problem because technically this object is defined for having these external states at that make it to all boosted versions of their energies. And so one could take that also as a concern, or one could take that as a feature. And so in what follows, I'm going to talk about different limits of the S matrix elements and how they're encoded in this 2D CFT, and kind of advocate that the bugs or what looks like it could be weird and scary are actually interesting, and see the fun things that people have been up to. Okay, so we're doing fine on time. It should be good. I'll use, it'll be fine. Okay, good. So now to understand how to effectively use this framework, we have to build up our dictionary, and I'm going to focus on 3 aspects of celestial amplitudes. And my bias is always towards this infrared stuff, but some very, very cool things have happened recently in the collinear ultraviolet cases that I will get to. So the point here is that each of these, I guess, items listed in line are all kind of connected. And so that's fun because someone who's coming from being interested in the soft theorem side of the story and these like putative currents in the celestial CFT can connect it to interesting constraints on these S matrix elements. And then one can keep going from there. Okay, so the first thing to point out is, again, you're integrating over energy scales. When I look at the contribution to that Mellin integral from the low frequency part, then basically what like Chung, De La Fontaine, Sundrum pointed out is that I would expect to pull in that weight now. So what's interesting is that on the one hand, soft theorems, like it would be surprising that you change the spaces where you're integrating over all energy scales and you still get soft factorization theorems, but you do. And in this case, instead of a pull, we're basically resolving the omega goes to 0 limit of a single particle going soft. So at different powers of omega, there's a leading soft theorem here and a subleading soft theorem here. Those different soft theorems actually get kind of spread out in this Mellin transform variable, where now those are poles at delta equals 1 in one case, and then delta equals 0 for the subleading stuff, graviton theorem. So you already see that kind of nice kind of separation of different soft theorems in this picture. Now, for all of the soft theorems that like there is no I guess question of like whether they get correct, so like one loop exact corrections to the stress tensor, et cetera, you basically have a nice asymptotic symmetry interpretation because these conformal primary functions that we're using to set up these states just reduce to becoming pure gauge. And so for each spin, you can list off which ones they are. And so the leading soft theorem in E&M is this large U1, like so gauge symmetries where the choice of gauge parameter varies on the celestial sphere and makes it out to the infinity. And then for the gravitational case, you have super translations and super rotations or diff-S2 for those two soft theorems I was pointing out. So now we're taking an amplitude where we're taking one of the external legs soft, and you can, I guess, investigate the amplitude and see that there's a pole and this factorization at these values of delta. Or one can note the state that I'm preparing basically is going pure gauge. And so that's how I am essentially seeing the asymptotic symmetry interpretation in this new set of wave functions, of basically a gauge fixing of these guys. And one thing I want to also point out is that those special values of the dimension can come from the representation theory. So what we have is basically just looking at the global conformal multiplets. You want to have a primary state, which is going to be annihilated by L1 and L1 bar. So these are just Lorentz generators. And then you find form descendants of it by acting with L-1 and same with L-1 bar. So I can have a primary descendant for special values of those dimensions. And those dimensions are going to be exactly ones that correspond to these poles in the amplitude. So on the one hand, there's this infinite tower of conformally soft theorems that were studied, I think, noticed by Guevara and others. And then also recently have appeared in this paper with Guevara, Himwich, Pate, and Strominger. So Andy has this fun W infinity paper recently. Maybe he can talk about that in the discussion session. And then for the point of view of the soft theorems that I kind of motivated this program to begin with, those guys are descending to operators that generate these asymptotic symmetries. So the soft charges I mentioned are in the same multiplet. And this was noticed by Banerjee et al. And the symplectic partner of those operators are basically interpretable as dressings. So essentially the soft theorems and the structures of the conformal multiplets and the notion of IR divergences and dressings are all connected, which I guess it makes sense in hindsight, but it's nice to see that like different ventures of like people who are looking at trying to find differential equations to constrain amplitudes in this basis and people looking at IR divergences and dressings kind of all landing on the same topic. Okay, so one thing to point out here with the dressing is that of course the fact that I have this soft theorem is, I guess, also connected to the fact that actually if I didn't have any and I said like I'm just going to scatter some in particles, some out particles, no radiation whatsoever, I would get zero, because basically there's also these virtual exchanges that with when you lower the IR cutoff, they diverge eventually when we sum over it so that you have vanishing amplitudes. So one thing nice about the original first part of the talk in that program is the statement that you can reinterpret that vanishing of those amplitudes as being a symptom of the fact that you aren't preserving, or like you're not conserving these asymptotic charges, symmetry charges. And so that interpretation is nice from the point of view of people going into like saying, well, what happens when you have horizons? Do you have extra constraints there? But for the case here, it motivates also looking at dressed operators. And so Pate, Enrique Leroux, Connie Hamid, and Andy pointed out that when you go to this conformal basis, you can actually pick a form of the dressing such that it also has a definite weight. And then the nice thing about this this operator is that you can actually interpret now essentially the smearing that's appearing in this definition in terms of so you just look at the frequency integral that's appearing here to identify that if you don't have in the Fitted equivalent dressing any kind of cutoff in the frequency, that this picks out a delta equals 1 mode of these A's and A daggers. And then the guy looks like a vertex operator where basically the SL2C ascendant of the guy, if you go up the diamond, is sitting in this dressing. And so the fun thing about that then is it leads you to thinking about conformally soft sectors of celestial CFT. Those correlators of vertex operators there are basically governed by the spontaneous symmetry breaking dynamics. So you identify the spectrum by trying to see like where the soft things are going to be, and then you see that essentially you have these effective theories for these to model like the breaking of diff-S2 to rehearsal, or in this case the large U1 symmetry being modeled by a free boson. So from the point of view of Truman trying to construct a nice example 2D CFT, these are like the easiest ones to start from. These are just like the parts that capture the spontaneous symmetry breaking dynamics of asymptotic symmetries in the bulk. And the other interesting thing about it, and one of the, I guess, obstacles to, again, interpreting some of the celestial CFT story was that the levels that you would get were naively zero from the point of view of taking two, say, photons soft, but there's an additional symplectic partner mode, which is this pure gauge guy appearing in the dressing, and a very nice observation by Pate and Strominger is that you can read off from the cosmological dimension levels in these theories, and this has been extended to gravity too. So here, the slide we're talking about, there's some nice toy models for these asymptotic symmetry breaking dynamics, and non-zero levels can come out of these resummed exchanges. So the next thing I want to go to from the soft story is to the collinear limits. So there again, I'm highlighting another papers by the Taylor group and Andy, Yuan, Pate, and Anna. So there I can, so far I've been looking at special values of the delta. Instead of that, I can turn to special limits of the positions on the celestial sphere. And so collinear limits should be governed by celestial OPE. And so if I take two gluons collinear, one can work out that, like looking at the operators for the interactions in the bulk, that the leading singular form is this. And so the kind of fun thing about this particular paper is that they're showing that they can show that there's recursion relations that are symmetry constraints that govern this C that then let you solve for it. So that's kind of fun. So from the point of view of if I just had an amplitude and a Mellin transform, I can read it off from that. But the fact that I can also use symmetries to derive it shows some of the power of this kind of exotic celestial CFT, where now like the dimensions are in some sense like parameters, more so than like operators with that dimension are in the theory or not. So translation invariance gives you some relation. Similarly, a normalization comes from Salk-Lewin theorem. And then just to harken back to the work with these like these conformal multiplets, you get extra symmetries coming from the fact that basically there's a kernel when you try to ascend from the soft operator up to the radiative guys. And so there are extra global symmetries corresponding to the subleading Salk-Lewin theorem that gives you one more recursion relation, so you can solve for what matches the collinear limit. So this is a really nice calculation. I would recommend it, those interested, like it's a nice paper, because it's really highlighting the power of using symmetries to learn something about celestial CFTs versus everything being forced by kinematics. So, or in this case, at least the kinematics are non-trivial. So, okay, now, so this other thing to point out is that with kind of this paradigm in mind, you can notice that by looking at collinear limits, even though your 3-point amplitudes were very singular, you can extract the CIJKs. And so we have the spectrum, we have this data for the CFT, and you can try to apply other CFT machinery to it. And so there have been interesting papers by authors below looking at both doing conformal block decompositions and different signatures for these amplitudes and trying to interpret what's happening in the exchanges, radial quantization, et cetera. So there's a lot that goes on when you kind of are assuming that you really can apply CFT machinery to these celestial CFTs. And then also pushing these symmetries that you're getting from the soft theorems to have these differential equations and null state conditions for your S matrix elements. So those are two interesting directions to push in there. And then I just want to close off. So I think I'll be fine on the time. Let's close off with some looking at 2-to-2 scattering. So in the past, I guess I was focusing more on the fact that everything's singular and the dimensions are weird, but now let's look at how nice things can actually get. So this is going to be based off of Arkani, Hamid, Pate, Rickler, and Strominger. And so just starting from the fact that you have a function of Mandelson invariance times this momentum conserving delta function. This is my 4-point amplitude and momentum space. And when I do this transformation, part of this transformation is just guaranteeing the conformal covariance, because again, I'm in boost eigenstates, so we expect this. This extra delta function was that feature I was mentioning about how these constraints make things a little bit singular. But the nice thing about it then is that the part that kind of remains, I can probe the S&T dependence of this, the Mandelson dependence of this amplitude via this factor here. So what I have now is I basically have a stripped amplitude that probes scattering at all energy scales, where now this was S and this is T. So fixed angle scattering is keeping Z fixed. And so just the last 2 slides pointing out that the convergence of the integral is tied to the ultraviolet behavior. So something that's very UV sensitive. So depending on how M will behave as a function of, I guess, this Mandelson S, you will or won't have different pole structures in this beta plane, which is the Mellin transform for the Mandelson variable. So you have an imprint of the UV completion in the analytic structure in this beta plane. And similarly, if you look at an effective expansion around the 0 frequency, you can see that there's, first of all, if there's logarithmic runnings, you get poles, higher order poles instead of just simple pole, you have double poles, et cetera, coming from these logs. And you can also try to translate positivity constraints from that from amplitudes to then positivity constraints on the residues. So basically, all I want to say in this slide is that there's some very interesting recent work last week from Chang, Huang, and Li, continuing that effort. And so there, you're at a stage where you can translate over the statements from amplitudes that you know to statements about celestial CFTs. And some of the features are pretty nice, like the fact that these logs turn into like multiple poles, the fact that the soft theorems are separated out, and then the fact that the statements about EV behavior somehow seem like natural to impose in the spaces too are kind of nice. So now this goes just my conclusion. So I have lots of time for questions. There's this 2 more slides. We have a framework that makes symmetry enhancements manifest. It reorganizes soft and collinear limits, and it's sensitive to the very deep UV. So that's nice. And we've given examples of how to translate features of amplitudes into objects within the celestial CFT, whether it's conformal soft theorems and also operator product expansions. So these different currents, et cetera. And also what kinds of properties we can demand of celestial CFTs. So in this case, the statement that you have no poles in some region of this complex beta plane, et cetera, for 2 to 2. So these are what we've tried to motivate and review today. And the next step forward are basically to try to expand this dictionary. And so like we have mapped from the S matrix elements to these objects in celestial CFT, but you really don't want to just have the correlation functions. You want to basically probe bulk physics with it. And so the way to do that would be to connect to adjacent subfields and to also look for an intrinsic construction of the sky. So you can kind of see we're motivated by aspects of gravity and of like IR limits of scattering to look for this framework. And now the goal for the next the years is to look at how we can use tools or like understanding from different subfields to kind of tie in and feedback hopefully too. So that's the structure. And then I'll just close with a bunch of people who've been working on different aspects and kind of trying to show where they're focused on with where their names are located. But thank you guys for hearing me out. And thank you to everybody whose names are on these slides. So thanks.
Okay. Thank you very much, Sabrina, for this great talk. So let's thank Sabrina for this wonderful talk and also these beautiful figures. We have now time for questions. So first question goes to Shusheng Zhao.
Hi, Sabrina. Thank you for the excellent talk. It was really nice. I have a question kind of along the future direction you mentioned. I was just wondering that there has been a lot of developments on computing correlation functions of the celestial CFT. Do we have any idea to compute, for example, the torus partition function of the celestial CFT?
Okay, so right, like the extent to it, I think I'm going to defer to Andy a little bit for that, because I know that, for instance, we have the notion of this torus from 2-2 signature,
right?
But then it's Lorenzi. Okay, so the modular parameter seems to be fixed in that context. I think, though, the fact that you can make the conformal block decompositions work consistently, like say you take Taylor's paper and then you take Andy's paper, so the 2 different conformal block decompositions and different signatures, and like, so in some sense we want to define the data for the scattering in either case, and I think that power probably implies that you can then change the manifold that you're on, so you can go from the celestial sphere or the celestial torus that happens to be given to you by 2-2 to some other guy. But I don't like, in some sense, I would say that the people who are studying these, like the operators that you need to add to talk about dressings, et cetera, are trying to basically see what exactly the states are. So I don't have an answer to that, but I think that a lot of people could talk about what they think about it, maybe in discussion system for the 2-2 people. And then my take would be that I want to understand any dressing, like extra states that have to appear from, that I'm kind of maybe missing, just looking at the radiative guys.
Okay, thank you.
Yeah.
Okay, so next question goes to node of Institute for Advanced Study. So it's Yuan Malasino.
Yeah, I have a question about these poles and the omega variable that you discussed.
Yes.
You said that they're present in field theory, but not in gravity. Can one see what happens to them as we turn on the Newton constant?
Yeah, so I guess, so this is, again, based on Nima and Andy's paper, so hopefully I'm not going to end up saying something too fast there. So they're looking at gravitational, like, so gravity-photon interactions. And so I guess the M that's there is capturing the orders of the G Newton. I guess, I mean, I have to think of maybe I will defer if there's a quick answer that Andy would have, but if my intuition would be that, okay, so somehow the way that these poles go away is supposed to be related to how the bulk point singularity is resolved in the ADS context. So I guess the funny thing about it is sometimes when you have this, like it's coming from this, getting this exponential damping, giving a gamma function where you can see where the poles are. So I don't know if I have at the moment, because I haven't thought about the UV side of it as much, intuition for how that transition happens. But I guess in some sense, like the only funny thing about it is somehow like this rough, like the change from this behavior to that behavior is what's killing the poles. And I know that you could capture order by order, like what the gravitational coupling is doing via like an expression like this, but I don't know if I have a good intuition for how it really like goes like on and off. Maybe if anyone wants to add to that, I'm happy to, because yeah.
Okay.
Okay, so Johan, you have one further comment or?
No, that's fine.
Okay, so then maybe let's change continent. Let's so Shiraj Minwala.
Hi, Sabrina. A quick question, and maybe you said this, but I sort of missed it. S matrices obey this unitarity equation, SS dagger is equal to 1. Is that automatic from your celestial point of view, or is it a condition that imposes conditions on correlators from the celestial point of view?
I would say that it probably has to impose conditions on, yeah, it has to impose conditions, right? So, yes. So what I think, like, so Hotat and Shuhong's paper started looking into that, and then I believe also the recent paper on that came out basically last week also does, I believe, look at constraints of unitarity there. So basically, we know that it's the same object, so it's the same S matrix, it's just in this different basis. So even though the one side of people like trying to define the celestial CFT intrinsically, like you want to see, I guess, like radial quantization, how you define the state operator correspondence there, et cetera, like, and see if there's a notion of unitarity that you can make sense of. It doesn't look like a unitary 2D CFT. So we know there is unitarity. It's encoded somehow in features of this guy. And so it's definitely an extra constraint on top of it. So it's like extra constraints on top of like the data in the CV. CFT. But I don't think I would right now be able to list off like a nice kind of example, but I know a couple of papers I would point to that might be of interest, which would be Hotat's and Shuhong's paper, and then the Chang, Huang and Li paper should say something to that effect.
So thank you. Could I ask a follow-up, please?
Yes.
Okay.
You talked about how these in the context of I think photon scattering, you talked about how amplitudes split up into a soft part and a hard part.
Yes.
Does the hard part obey a unitarity type equation by itself? Does it obey some sort of Kutkowski's rules that are modified by the fact that it was dressed by the soft part?
If I say anything too strong, then somebody who knows it from the amplitude side of things could come in and tell me I'm wrong. But my impression would be that I think it should be consistent to scatter dressed particles. But and in that situation, then one would imagine that like any statements about like unitarity among the dressed particles would then follow, like you're saying. I think that maybe there's some issue of like IR cutoff coming into that definition, because even in this definition of these vertex operators, there's the IR cutoff in the phi's, somehow like the 2-point functions have an IR cutoff dependence. So I again welcome, like every time I'm answering questions on behalf of a group of people, I'm happy if the people or authors on those papers want to say something that I'm not saying as well as they would want to. But in this situation, I think that one should be able to consistently consider just stress scattering. And then I would imagine, like, I guess the question would be, like, there's like some shifts in the conformal dimensions and a little, like, it might not be, I'm not sure how easy it is to look at the conformal block decompositions of these dress guys in particular as compared, because like the way that they're written out is still defined in terms of typically like you normal order, and you have this dressing for each particle. So like I think maybe once you have more of the celestial CFT techniques down, you can do something more fruitful with that, because I think still you'd be kind of computing things like with like cloud to cloud like exchanges and stuff like that. So
thank you.
Yeah.
Thank you.
Okay, Simon Caron Hood is waiting for quite some time already, I think. So Please go ahead.
Yeah, thanks for the talk. So one of my questions was already asked by Shira. So yeah, let me just reiterate that it would be very nice to work out what unitarity means for this hard amplitude. But my question is about crossing symmetry, which has always been a very fruitful tool in CFT. Yeah. So do I understand correctly that this distribution nature of the four-part particle amplitude is making it a bit
it's weird. So it's definitely weird. So okay. So
can you comment on? Yeah.
I'll comment. I'll make a lot of comments, and then also mention caveats where like. So the first comment is that for 2 to 2 somehow there's something kind of nice, which is that you're on this. So you're on the circle here. And the kinematics of in and out actually happen to be such that, like, basically on the circle, there's an ordering where in and out have to alternate around in order for momentum to still be conserved. And so what happens then, basically, if I do just a SL2C transformation to put one point at, like, 0, 1, and infinity, wherever that fourth point is, there's, like, basically 3. It can be here. It can be, like, it can be basically between the other 3. So say this is the fourth one. It can be here, here, here. Those different kinematical crossings are then like step functions. So basically, instead of a circle, it's actually an interval, like between 2 of these points where you have support. So okay, the weird thing, what happens is that so basically there's a sense which just for 2 to 2 at least, it doesn't go to higher point. The amplitude defined in those different ranges are the different crossings. So somehow if you add overall crossings, you see this to avoid these theta functions in the recent paper by Taylor et al. You can get around that. Now, the funny thing about it, what comes into a problem with is you also want to think about crossing in the 2D CFT. And so when you have this kind of restriction, naturally then the channels that you're allowed to do, like an operator product expansion around, somehow are related to the crossing in 40. So that's a problem people have run into, is essentially like sometimes integrals to convert the conformal block decomposition are easier to do in a channel that isn't actually the one that's supported from, like, the point of view of the kinematics. So I would say that I think that the paper with Hotat and Shuhung pointed out an issue with the behavior, like the phases when Z, but I think that could have been an artifact of, like, you want to put the negative sign for, like, the Mellin transform into the definition of the cross guy. So I would say that crossing isn't fully understood from this point of view, but I do want to say that, like, a very, like, okay, so the picture that you have right now is that you have basically not a light ray operator, but an operator sitting at null infinity integrated with U to some power for future null infinity and V to some power for past null infinity. To pick out positive or negative frequency modes, I have an I epsilon prescription on the U or the V to select A or A dagger. Now, if I go to 2-2, that guy should somehow, like there should basically a pi rotation in the time coordinate between those two. So what I think is natural is that somehow you have this like O plus and O minus, if you can continue to 2-2 and back, should somehow be like the same guy moved around. So I think that, like, the next interesting thing is people who are more comfortable, like, looking at contours and complexified coordinates are going to notice that how crossing would manifest itself if you analytically continue this celestial sphere. I think I've said all these interesting issues people run into with their crossing, but haven't just given you an answer. And I think that the answer then is that basically it's active area.
I think we can delay this to the afternoon session. So we have by Tom and Andy, we have plenty of time for discussions, because I was told by the super chairman that we should move on. So let's thank Sabrina again for this wonderful talk. And I'm so sorry that I have to cut off, but we have still a lot of time later in the afternoon session for questions. So let's move on to Pavel Putrov's talk. So
can you see my window?
Yeah. Okay. You can start. So we are happy to have Pavel Putrov here from ICTP Trieste. He will talk about spin cobordism, surgeries, and fermionic modular bootstrap. Please go ahead.
Thank you for the introduction, and I would like to thank the organizers for inviting me to give a talk at this great conference. So my talk will be based on a recent work done together with my student Andrea Grigoletto. And So in the beginning, let me be quite general and schematic, but later on I will be more concrete. So suppose we consider a quantum field series with a fixed global symmetry group G, and then we can consider the following three abelian groups. So the first abelian group is simply a group of all representations of this G, and the second abelian group will be a group which classifies anomalies of G. So it has a natural abelian group structure with respect to stacking of non-interacting series. Equivalently, one can understand this group as a group of invertible topological quantum field series in one high dimensions, which has the symmetry group G. And the second, for the third group, let me consider some particular space-time X, and one can consider all possible anomalous phases that can appear under action of large diffeomorphisms or gauge transformations of a series with for series on X, so that they're just consistent with the group structure on these groups of large diffeomorphisms and gauge transformations. So then one can consider a sequence of homomorphism between these three abelian groups. So physically, these maps can be understood as follows. So the first map is given by taking a series of free fermions in a given representations and considering the value of the corresponding anomaly of the series. And the second map can be understood as is given by the representation of corresponding invertible TKFT in one high dimension on Hilbert spaces associated to X with possibly some non-trivial backgrounds, background gauge fields for our global symmetry group G. And so this is considered as a representation of this topological quantum theory with respect to a group of, again, large diffeomorphisms and gauge transformations. So the goal is to understand more or less explicitly how to evaluate these maps. Of course, this problem is interesting when we consider non-perturbative anomalies, because in perturbative case, this is relatively well known how to do this. And so there are some basic motivations behind this. So the motivation for understanding the first map is, of course, to answer the questions like anomaly cancellation. Suppose when arise when suppose we want to gauge this G, or anomaly matching between two possibly different series, if we can would like to check if they can be equivalent in the infrared. And the second map is important for understanding, for example, what kind of constraints anomaly puts on possible values of partition functions or spectrum on a series on some given space-time, as, for example, can be done using modular bootstrap techniques. So these maps have a very important property, which can be formulated as follows. Suppose we consider a homomorphism between two different symmetry groups. So a basic example of this is if we can consider the subgroup of another symmetry group. And then for any such homomorphism, there will be a corresponding pullbacks maps between these three groups, which I just described. And there's a nice property that if we put them together with these maps, which I described before, this whole diagram will be commutative. And this is actually a very constraining condition, which can be used to do some calculations. But let me mention that mathematically, this condition can be understood as follows. So these groups which appear here, they can be understood as values of certain functors from the group, from the category of all groups to the category of abelian groups. And so these are contravariant functors. That's why we have pullbacks corresponding to homomorphism. And this property can be understood as the fact that we have a natural transformation between these functors. But let me mention again, so this is not just some abstract nonsense. This actually can be used to do some calculations. In particular, the version of this constraint was actually used before, but mostly in the case when G prime was continuous. So, for example, such type of relations were used to relate non-perturbative anomalies and perturbative ones. So let me proceed with a more concrete setup. So let me consider the case of 2 dimensions and consider series with a symmetry, which is a product of fermion parity times some symmetry group, which I assume to be finite and unitary. And let me consider them on a 2-dimensional space-time, which is a torus. Then explicitly this group of representations can be suited as so one way to understand it as just a pre-abelian group generated by all irreducible real representations, and can be understood just as a usual ring of real representations, considered just as an abelian group under direct sum of representations. And so the group which classifies anomalies. So let me mention that here I'm considering the case that all series are assumed absent of perturbative anomalies. So in this case, the anomalies are known to be classified by the following one-target dual to a spin Bardism group in 3 dimensions. So this type of Bardism groups already appeared in a Ren-Valusainer talk, for example. And so let me remind you, so what it is. So this is a group of equivalence classes of 3-dimensional manifolds equipped with G bundles, so that the pair of manifolds are declared to be equivalent if they form a boundary of a 4-dimensional manifold, so that the corresponding spin structures and G bundles are induced from this bulk for manifold. So the elements of this group which classified anomalies can be understood as invariants, as a Bardism invariant. So physically they correspond to values to the partition values of the partition function of the bulk TQFT, which corresponds to the anomaly by inflow on these 3 manifolds. And then the first map can be realized physically as follows. So the elements of this in the first group are formal differences of representations. So one can take for example, ρ2 minus ρ1. So one can take a series of left moving fermions in representation ρ1 and a series of right moving fermions in representation ρ2, and also add a bunch of fermions in trivial representation, so that the total chiral central charge is 0, because we want the perturbative anomaly to be 0. And finally, the third group, the group which describes possible anomalous phases, has mathematical interpretation, which is written here. So it's a certain cohomology group, where the group is a product of G and so-called metaplacer group, which is a central extension of the usual model group by Z2. And the coefficients in these group cohomologies are product of U1s, so that each U1 is assigned to a certain choice of background, which can be the choice of spin structure and a choice of background G bundle. And so again, the second map is given by just consider a representation of the Hilbert space of the 3-dimensional bulk TQFT with respect to the action of this group of large propagation transformations and large diffeomorphisms extended to the diffeomorphisms of spin manifolds. And for short, I will denote this the group classifying anomalies as A of G and group classifying possible phases by phi of G. And so I will first consider this first map. And so to touch base, let me consider a very well-known example when the group is Z2. Then the anomaly group is well known to be Z8. And the representation ring is now generated by trivial representation, which is real one-dimensional, and sign representation, which is non-trivial one-dimensional representations. So that the trivial representation is mapped to 0, and the sign representation is mapped to the generator Z8. So what happens in general? So in general, we have a certain map from this real representation ring to the group classifying anomalies, which I will call for short as Chern character map because it's analog of the corresponding Chern character map in the perturbative case. And so in general, it's very hard to fix this explicitly. But, well, certain components of this map can be described rather explicitly, and which was done in this paper. But instead, we want to propose to kind of fix, we will propose that the values of this map can always be fixed kind of using the following three main properties of this map. So in a sense, this map can be axiomatically defined using the linearity property, which is just a statement that this is a group homomorphism between abelian groups. And the property is a neutrality property, so that if you consider homomorphism between from G to G prime, so note that physically this means that, so why do we have pullbacks between the corresponding anomaly groups? Is that because if you have a series with symmetry G prime and we have such homomorphism, we can automatically consider it as a series with symmetry group G, where the G acts by composing elements of G with this homomorphism. So let me mention here, I'm not assuming that groups act faithfully. So in particular, in principle, groups can act trivially. And then we want to require that the following commutativity, so we can first take a pullback of this representation of G prime to representation of G, but we can do this in a different order. We first want to calculate the corresponding anomaly and then take a pullback in the corresponding anomaly group. And the third defining property is a normalization. So we want to fix the values of this map for whenever G is abelian. And these values are essentially listed in our paper. So in part, this is just a collection of known results, but in part, it's new. And so let me give a simple example how this can work to determine the values of the map from the representations to the anomalies, which again physically correspond to taking the anomaly of fermions. So let me consider a simple non-abelian group. It's a symmetric group of S3, the group of permutation of three elements. And one consider the first subgroup, embedding of the Z2 subgroup as a subgroup of interposition of just two elements. And then consider also Z3 as a subgroup of cyclic permutation. And also consider a map from S3 to Z2, which is given by taking a parity of representation. If we consider the corresponding anomaly groups, so for Z2, this is again Z8, and for Z3 is the classifying group is Z3, and one can show that for this S3 group, the classifying group is Z8 times Z3. We have the corresponding maps in the opposite directions. And so by knowing how this character map acts, how the character map acts in the case of all abelian groups, we can determine it here. So in particular, in this case, there are three irreducible representations. So there is one-dimensional trivial representations, one-dimensional representation which acts by sign of parity, and there is a non-trivial two-dimensional real representation which can be stood as a representation given by isometries of a equilateral triangle in 2 dimensions. And one can explicitly determine the images of these representations in the anomaly group by using the properties which I described before. So now let me proceed to the group describing anomalous phases. So let us consider the set of all. So now we have a torus as a space-time, and let me consider the set of all possible spin structures on a torus and background and isomorphism classes of the G bundles, which is equivalent. So these are just equivalents to assigning a pair of holonomies to each one cycle on the torus. In this case, so if I consider, for example, the case of G equals Z2, there are 16 possible choices of backgrounds. So here 1 and 0 or 0 denotes the holonomies of the global symmetry group, and A and P denotes either periodic or anti-periodic spin structure conditions. And then, so the data of anomalous phases can be used as an assignment of one-dimensional complex vector spaces to each element of this set. And for each element of the group G times this extended version of SL to Z, which is also often referred as a metaplexic group. So for each element of the group, we want to assign a linear map between a pair of corresponding vector spaces. And all possible such assignment up to change of basis, such as they are consistent with the group law, they can be classified by the following first homology group. So equivalently, this can be used as a representation of a groupoid, where the objects of the groupoids are again the choices of the background. And then one can show that the map from the group classifying anomalies to this group of all possible phases which is given by considering a representation of representation given by the corresponding bulk relative T can be fixed just by considering the partition function of this relative T on certain closed manifolds, which in particular can be always taken to be mappintory, but this is not always necessary. And so these correspondences can be realized roughly by taking, so in each connected component of this groupoid, we can fix some basis object, so basis choice of background, and then for each other object in the groupoid, we fix a path to this base object. And then if you consider, for example, so that then we identify the corresponding vector spaces to the vector space of the base object. And then for any error between two different objects, we just compose it with this with some chosen fixed path to the base object. So we get a certain loop. And for this loop, we have a corresponding mapping torus. And the value of the invertible decryption of this mapping torus gives us determines this linear map. So, so in principle, this gives a description of this map from the group of anomalies to the group of possible phases. But of course, we want to make it more explicit. We want to learn how to calculate it. So let me know that since the set of all possible background G gauge field on a torus is essentially the set of all possible commuting pairs on a torus. One can use this to essentially boil down everything to the case of abelian groups. So one can always consider a certain different abelian subgroups or G prime of G, and moreover, these subgroups are always has at most two independent generators. So it follows that it's enough to calculate the values of partition function of the corresponding convertible to T, or equivalently the values of the corresponding Bordism invariance on mapping tori in the case of when G is abelian with at most two independent generators. But in fact, we actually will show how to calculate these Bordism invariance on any closed P3 manifold in an easy way using their surgery representation. So let me remind briefly what is the surgery realization of three manifolds. So any three manifold can be realized by surgery on what is called a framed link. So let me consider a V component link in S3, and the framings geometrically can be suited to the choice of normal vector field to each component, non-vanishing normal vector field to each component, and more combinatorially, the framings can be fixed by assigning an integer number to each link component, so that it corresponds to what is called self-linking number, which is a linking number between the link component and its push off towards the framing vectors. Then three manifold corresponding to this data can be obtained as follows. So we remove a tubular neighborhood for each link component, and we glue back in solid tori, so that the contractible cycle in solid tori is mapped to a one cycle traced by this normal vector field given by the framing. So it's often useful to introduce what is called linking matrix. So it's a V by V linking matrix. And then things like background Zn gauge field, which is as a first element, the elements in the first cohomology group of our three manifold with Zn coefficient can be combinatorially described as false. So they can be described as a rank V mod n vectors, which satisfy this condition. And similarly, the spin structures can be combinatorially described as rank V mod 2 vectors, which satisfy these conditions. In particular, for each spin structure described by such rank V mod 2 vector, one can assign what is called characteristic sublink. It's a union of components of our link L over indices for which the corresponding S vector describing spin structure is 1 modular 2. Okay, and so using such combinatorial description, one can show that in the case of a abelian group with at most two generators, all possible Bardism invariants can be expressed using just the two basic invariants, which are listed here. So one, which denote gamma s, takes as values Zn ground gauge field on our three manifold, and spits out an element of Z to n, and is given by the following expression in terms of this combinatorial description of the spin structure and the gauge field. And the other invariant which we will use is takes as an input Z2 background gauge field, and output is a mod 8 valued invariant, and is given by the following formula in terms of the surgery, where here it's this is what is called Arf invariant of a link, and so these links which appear here are characteristic sublinks corresponding to particular choice of spin structure. And so the values of these Arf invariants are well known for basic links, and well, it's relatively easy to calculate in general. But also here I gave some combinatorial description, which is very easy to use for calculation. But in principle, these invariants can be given some geometric interpretation in terms of surfaces representing Poincare duals to these cohomology elements. So let me give a simple example how I can use this to calculate the action, for example, the action of t square element in SL2Z on the vector space corresponding to this background. So we have a torus with periodic spin structure and holonomy 1 along one direction. So in the case of GZ2, the anomaly is again classified by Z8, and choosing some new mod 8, the corresponding Bardism invariant is nu times invariant beta, which I introduced before. And using this surgery representation, it's easy to calculate it to get the following value. And so in this case, the surgery can be realized by the following link with three components, which is known as Borromean rings. And the linking matrix is very simple. So let me mention, in principle, one can use this directly, the geometrical interpretation of the invariants. So the geometric interpretation is the following. So one can take a Poincare dual surface representing this element of the first cohomology with the two coefficients. So physically, this surface can be understood as support of the Z2 charge operator in our theory. And then the spin structure in the 3-manifold induces p- structure on the surface, for which we can calculate mod 8 valued Brown invariant. And so physically, this relation can be understood as decorating this charge operator with 1 + 1 dimensional SPT known as K spin chain. So in this particular example, when we again consider the mapping torus of T2, which starts from this torus with periodic spin structure and holonomies 1, 0, the corresponding surface is a connected sum of 3 copies of RP2, and again, by calculating its R-bound invariant, we arrive at the same expression, and this can be done for all other generators for other elements of SL2Z. So as an example, we can as an application we can use the known modular transformations to do modular bootstrap, and this we do essentially by generalizing the work done in bosonic case by these people using this SDPP semi-definite program solver. So here I just list some results. So these bounds on the lightest scalars in the Neveu-Schwarz sector untwisted with projection to the trivial fermion parity and the trivial Z2 global charge. And so the horizontal axis corresponds to the central charge, and the vertical axis is a conformal dimension of the lightest scalar, and different curves correspond to different values of the anomaly. In particular, these kinks can be understood, the points below the kinks can be realized by free fermions, where the Z2 global symmetry acts either as left-moving or right-moving fermion parity. So finally, let me mention some possible future directions. Of course, there are some kind of obvious ways to try to generalize it. First of all, it would be interesting to do this bootstrap for, in the case of fermionic series with some non-abelian global symmetries. And it would be interesting if one can do something in high dimensions or for generalized symmetries mentioned in the Shao talk. And another interesting thing is that, so suppose we consider now fermionic series, which apart from this G global symmetry, now also has 0-1 supersymmetry. And these are supposed to be classified by G equivariant version of the theory of topological model forms, which was mentioned in the Yuji Tajikawa's talks. So here, the anomaly group plays a role of some additional grading. And in particular, the pre-part of this theory is described by certain Jacobi-like modular forms for which the model transformations are determined by this map to the anomalous, to the group of anomalous phases. Okay, so that's it. That's all I wanted to say. Thank you.
Okay, thank you very much for your interesting talk. So we have time for questions. I see Gregory Moore.
Yes, could you go back to the Bordism invariance defined by Kirby et al.?
This?
Yeah, I had trouble following this. So in the first one for gamma sub s, n is not invertible modulo to n.
Yeah, so here what I'm saying, one can take any representative. So A is this. So one can take any lift of A to Z to the V.
And then it doesn't matter.
And it doesn't matter. It shows that it doesn't matter.
Okay,
using this property, one can show that it doesn't matter.
Okay, so so similarly, you're choosing integral lifts.
Oh well, here it's actually important. In the second, it's actually important that here to do this formula, it's important that S is chosen to be only 0 and 1. It's a particular lift to Z. So A is yeah. So here is.
So A, I see. So A is any integral left, and S is 0 or 1, and then you say these are well defined. And similarly, in the same spirit, you know, if the ARF invariant is mod 2 valued, then 4 times the ARF invariant is 0. So I wasn't quite sure what you meant. Like,
well, this is good because this is mod 2 defined. So this is already mod A defined, well defined. Right?
So you're so you're embedding.
But
You're embedding Z2 and Z8. Okay, I had a more conceptual question. So I didn't follow how the topological and anomaly cancellations that you used in most of your talk are input into the fermionic bootstrap. That's probably just because I don't know enough about the fermionic bootstrap, but it seemed like a giant leap in slide 13.
Well, we determine the anomaly determine essentially all these maps, how these linear maps corresponding S and T act.
Sure, that was clear.
So yeah, and then this map, they put the constraints. So
okay,
I didn't write this, but
you're just constraining the partition functions under modular transformations using this.
So this for each of these objects in the groupoid, we have a corresponding partition function which depends on tau and these twists.
Now I see what you mean.
And then this gives us some non-trivial relation between the partition function with different twists and different t related by t going to -1 over t or t plus 1.
Okay, that correct. You have one more.
No, I'm done.
Okay, so we have a last question for Kumram Wafa.
Thanks for a nice talk, Pavel. Perhaps it's something related to what you already said, but I'm not completely sure. So if you take the G symmetry and twisted theory by that, the phases that you studied presumably will give you some information about the Verlinde algebra you get for such a twisted orbifold. Have you studied the relation between this? I mean, it's going to be a vector valued object, so at that point.
Well, no, we haven't studied it, but well, in part, yeah, this essentially the bosonic version. Well, the bosonic version of this is, if one gets a bosonic version of this, this is quite closely related to these orbifolds which were considered before, yes.
So is there a general map between finding, I mean, for example, the orbifold for a rational conformal field theory with G symmetry has been tried to be classified in some older works. The question is, do you have a map between this and that story? I just want to know what is the...
Well, not really, but yeah, it will be good to think. I think about it. Yeah, not ready to answer.
Thanks.
Okay, so then I don't see any more questions, and so let's thank Pavel again, and we will see us again in 22 minutes at 11:20 Brazilian time. Thank you for your audience.
Thank you, Stefan. So let's just try to quickly do the share screens, and we want to check a video too. So Alba, can you try to share screen first?
Oh, yes. Does it work?
Looks good.
Good.
Thanks. Tomasz, you want to try yours?
Okay. Yes, do you see it?
Yeah, maybe you can make it full screen.
Like that?
Control L, maybe.
Yeah, it was better before. I don't know if there's if you go on view, if it does full screen.
And where is
yeah, go to the view tag at the top left.
Up left?
Or the view.
Click
on the view.
You mean I should go in Acrobat or in Zoom?
You just stay Acrobat. You just go to video view, or you go to the top left.
Okay, you want me to go to Acrobat now?
No, I think you're on Acrobat now. At least the share screen looks like it's Acrobat. So if you can just click on view.
Let me stop sharing. Okay, and now you want me to do, I'm full screen on Acrobat now.
Okay, so try to share screen your Acrobat then.
Okay, so I go back to that and share screen here. That's what you get.
Okay, so
because I'm using vertical. I'm using just pages like that. I'm not using not landscape.
okay, so maybe the first way you showed it was better.
Okay. Yeah. So let me go back to that. Yes.
This is perfect.
Yeah, we're missing the very bottom of your screen. But if you can scroll, it's okay.
Okay, so I'll make it longer. I can try to.
You might try go to view in the option in the panel option, and then there's view, and then there should be a enter full screen option.
Yeah, go up to the top.
That's what I did. So now do you see full page starting, let's say at 1 and then...
Nathan and Stefan, some people prefer not to use full view, so I think this should be okay.
It's okay.
So it should you see on the top, you see the celestial holograph and
Yeah, now
it's now perfect. It's fine.
Okay,
now
I
it's
want.
fine.
Okay, cool. Okay, all right.
Very good.
Thank you.
Sorry about it. So Hirosi, do you want to try to check your video?
Sure. Can I try my slide first?
Yes.
I cannot do that.
Sorry, you're not co-host. 1 second. Okay.
Okay, so let's see. This one. Can you see it?
Yes.
And if I change page, can you see it?
Yes.
Yeah.
And if I move the pointer, can you see it?
Yes.
Yes.
And I prefer not to use the full screen mode, so
Okay.
I'd like to stay like this.
Okay, that's fine.
Yeah, you can't see the pointer in full screen, right?
Beg your pardon?
If you go to full screen, I don't think you can see the pointer.
Yeah, that's one of the program. Another program is that I have other files on the desktop. So
I think on the Mac you can do it like that.
yeah, but I'm not a Mac user, so
that's a problem.
Well, it's not a problem; it's a feature. Now let's try the video also.
When you click share, when you choose the video, on the left there will be 2 tick boxes, right? 2 shoes.
Yeah, that was what I was about to ask. What is a tick box? I don't know what.
So when you click share screen and you select the video, before you choose select the video, you have many options to share screen, right?
Oh, okay. So let me go back.
Then there are 2 things that you can tick there, and that will, I think, improve typically the quality of the video.
So let me try. Oh yes, I see that.
There are 2 options, one for sound and one
should
for
I click
optimize.
on both of them?
I think so, yeah.
Okay, so let me, so I did that. And then, I closed the video, I'm sorry. So I should open it again. Just a minute, just a second. No, not this one. No, I'm sorry. Okay, so let's see. Okay, so it should work.
So thank you, Hiroshi.
Let me, just a moment. Let me try again. Can you see the video?
Yes.
It's not moving.
I know, I have not started it.
Okay, go ahead.
Okay, so let me start it.
So thank you, Hiroshi, for granting me 5 minutes to talk about.
Can you hear the, can you see and hear the audio?
Yeah, it's perfect.
Good.
Okay, thanks, Hiroshi. Andy, do you want to try to share your screen now?
Yeah. How's that?
Looks good. Good. So we're seeing the side panel, but it looks fine.
Yeah, I like the side panel there in case I have to go back and forth during the talk.
That's fine.
Yeah.
Okay, very good. Okay, so we're just waiting for Roger. Let's hope he gets online soon.
Good. Nathan, did you send an email to John, Michael, and Edward for them to stay on after at the next session?
To stay
test
on?
their slides?
Okay. Yeah, so everybody should have gotten that email. So they should be online before whatever it's 13:35.
I don't think I got the email or didn't notice it, but I'm here.
Okay, if you want, you can try to share screen. But we're going to do it again in the next interval. So
yeah, Nathan, maybe you can send an email to these three panelists.
Okay,
to make sure.
I will. Okay.
Thank you.
It may be worth sending it to Roger as well, just in case.
Yeah, I've sent a few right now. I don't know if you have. I asked Lionel to try to join us too.
I'm not sure he's really an email person.
Yeah. So let's see if I asked Lionel to try to join us.
Yeah, that might help.
When is the next session supposed to start?
At 11:20.
Okay, so we do have time. I could share the screen right now if that's convenient.
Yes, if you want to try, sure.
But you have to enable it.
I'm sorry, I have to enable you. One second. Okay.
That worked, didn't it?
Yeah, that works well. Yeah, we can see.
Yeah, that's perfect.
Okay. I guess I'll stop the share now.
Okay, thank you.
Dying to know the answer to that question.
Sorry, that wasn't the intended.
I have to watch the talk.
So are we waiting here for Roger next?
Yeah, we're waiting for Roger. He should be checking his share screen. I don't see him yet.
I think if Michael or John would be online, if they would like to test the share screen, maybe it will be useful, I think. Yeah.
Sorry, hi,
Thanks for
Pedro.
sharing.
I just spoke to Roger, and
Okay.
he, of course, thought it was in 50 minutes, not 10 minutes. And I just sent him the link, and so anyway, that's where we are. Sorry, maybe I should have called him before just to alert him as to the precise time.
Okay, thanks, Lionel.
I'm just wondering whether, well, I don't know. I mean, he seemed to think that, well, anyway. Just so you know where he is anyway. So I don't know if you've got somebody who you might want to wheel in ahead of him just in case.
I don't think we can change the order. I mean,
no, okay, that's fine. I mean, he seemed to be confident he'd be good in 10 minutes. So I stopped talking to him just so that he could get on with that.
Okay, well, if you stay online here, that will be helpful.
The what was I going to say? Yeah, so if you've got somebody there who uses a Mac and PowerPoint, then
a Mac, I don't.
Yeah, I mean, sometimes he just struggles to see where the button is.
Right. Okay. Well, we'll see how it goes.
Yeah, he might. He's done it so many times before. He should be able to do it. But you know, I'm just. This is just a familiar thing. Great. Good luck, and I'll keep online here.
Okay. Thank you. Yeah. Okay, he's online. Roger?
Yeah.
Hi, Roger.
Can you hear me?
Can we try to share screen?
Yes. If I can find it. Okay. Is that working?
Not yet.
I clicked on the blue thing. Does that, perhaps I've got to click on something else, haven't I?
Okay, on my screen, it's green, the share screen.
Yes, I clicked on that. I did click on that. Then I've got the thing which says which picture do I use or something.
Right, so you have to say, yeah, find the picture and then do share.
That's the one in the top left. Is it the one which is looks, you know, share? Oh, share. I see. Okay. Basic. No, where does it say share? At the top?
On the bottom. On mine, it's on the bottom. On the bottom right hand, it says share.
Oh, share. Oh, I see. That's probably it. Yeah, that's it. Okay. Is that right?
Yeah, we're seeing your screen, but we're not seeing the slides yet. So
No, I haven't got, shall I bring the slides in?
Yeah.
Also, I have to put it the right size, and otherwise you see it all funny. So where is my PowerPoint? Good question. Where is it?
Yeah,
There.
that's
Yeah. Yes, that should be it.
Okay.
I think that's it. Yes, that's the first one.
That looks good. So you're able to switch the screens, right? Switch the slides.
Now, what am I doing for that? There's a little thing at the bottom. Do you want that one? This is the one that always gets me because I can't see anything.
So this is good enough. If you can see, like, if it's okay, I would suggest.
Okay.
It's okay,
but you can just get the little square on the left.
I know, it's the one, and I have to find the right one. Which of the little squares is it? It's the one that looks like a TV set.
No.
Is that one?
Yes.
You can just go to the
everything. Oh, here we are. Yes.
Oh, perfect.
Okay. And
how long do I talk for?
So you talk for 25 minutes, and then there are 5 minutes for questions.
Okay.
So can you just can you make sure that the slides can go back and forth? Yeah, very good. Okay, perfect.
Actually, that was fourth. I'm not sure about back. Yes, there we go.
Okay.
Yeah.
So David Skinner will be your chairman. So we'll just be starting in 2 minutes. So you can just
Okay.
leave. Very good.
Hi, Roger.
Hi. Hello. Yes. I haven't seen you for a while. I can't actually see you now either. Never mind. I've forgotten what my title is. Maybe do you announce my title?
Well, yeah. Why current string theory cannot resolve gravitational singularity issue.
Okay, that's good enough. Thank you. Yeah.
Would you like me to give you a warning as you're coming up to your 25 minutes?
Might be a good idea. Yes, I've got a clock, but I'm not quite sure if I.
Perhaps I'll just give you a gentle reminder when there's 5 minutes to go.
Yes, that's all right. Yes, actually, I have a clock which is all right. So as long as I know when I'm starting. Yes, perhaps you're better because it's 25 minutes. It's 25 minutes from now, or from when?
Yep, that's right. 11:20.
Yeah. Yeah.
11:20
for you.
Oh, wait a minute, man.
Yeah, 3:20, and we stop 3:45 UK time.
Oh, 3:45 UK time.
Yeah.
What?
Well, no. We start more or less now and stop
at 22, 25 minutes to 4. Something. No,
quarter.
I've got 25 minutes. Is that right?
Yep. Yep.
Okay. So all right. Then that means it's at 25 to. Oh no. Hello. I'm just in the middle of giving a talk. Just in a minute. I'll talk to you afterwards. Can you call in about an hour? Okay. Good to hear from you. Let's talk. Bye-bye.
Okay.
Hello? Okay.
Okay, so are you happy to start, Roger?
Yes.
Okay. So welcome to the next session, everyone. And we're delighted to have Roger Penrose, who's going to talk about why current string theory cannot resolve the gravitational singularity issue.
Thank you very much. No, I'm happy to give this talk. I should explain that it's not restricted to string theory. That is to say, I don't think any theory which one could call a quantum gravity theory can resolve. In the normal terms, we use that, the idea of a quantization of something can resolve the singularity problem. So it's not specific to string theory. I want to make that point. The first picture here is one taken from my paper, and which was published in whatever it was, 65, which seems to have got me a Nobel Prize, which shows, the article was to show that in a general case where you have gravitational collapse with a certain criterion for when collapse has sort of passed the point of no return, which is the existence of trapped surface. And if the density of energy never becomes negative, you're looking at classical physics, and you're looking at the evolution from a non-compact Cauchy surface, you have to have singularities. So that was the argument there. The argument was, as you can see, to show that you get singularities in the future. This is a collapsing material, and it gets to a point where there's no escape without having negative energies or something like that. And that was the theorem this was in 64. I think I gave a talk in London, and it was repeated in Cambridge, where Stephen Hawking was there, and I talked to him about the techniques I was using. He developed these techniques specifically to talk about cosmology, and particularly the Big Bang. And the idea again was, you see, what I showed was that singularities were generic. You don't have to assume symmetry or anything like that in the local gravitational collapse. And what Hawking developed these ideas to show that for a cosmology, generalizing the technique somewhat, introducing ingenious ideas like the Cauchy horizon, which I think was one of the most important ones, that if you have a collapsing universe, again, with the sort of criteria that you don't get negative, looking at classical physics, negative energies. Now, that I remember being rather puzzled by this, because particularly after I had a very brief discussion with Jim Peebles, because I knew there are all sorts of different kinds of singularities you can have, and the cosmologists never studied them. They only looked at this one, which is basically the Friedman-Robertson-Walker with cosmological constant model. The acceleration at the top, you see that's where we now see this acceleration taking place, which can be explained by a positive cosmological constant. At the back, I've indicated that I'm not really trying to prejudice the issue as to whether the universe is spatially closed or not. It might go on and on and on, or it might not. The arguments apply to both cases, whether it's closed or whether it's not. Now, the issue always puzzled me is that we don't see all these complicated solutions that can occur. Certainly nothing like the Oppenheimer-Snyder collapse of a black hole, anything like that. And in fact, in a generic collapse, this is sort of turning my picture upside down, but not introducing perturbations so that you could have local regions which collapse faster than others or more dense than others, so they produce the singularity sooner in a certain sense, and you will get one incredible mess at the end. Perhaps like the sort of model that Belinsky, Lifshitz, and Kalatnikov considered, following the mistake that was discovered in the original paper by Lifshitz and Kalatnikov, which I think Belinsky found. Also the model due to Charlie Misner for type 9, Bianchi type 9s. You also get this very, very complicated kind of situation, which is nothing like what we have in the observed Big Bang. Now, what we see in the observed Big Bang is not like the time reverse. You see this, if you imagine time going backwards, should say you could put the inflaton field if you like. I'm not going to talk about inflation. It doesn't help at all. It doesn't make much difference at all to this picture. And it doesn't say why a generic situation like this couldn't happen. And you can do sort of rough calculations considering that these are lots and lots of black holes or white holes, it doesn't matter. The entropy considered as we look at the
sort of phase space of all possibilities and take the logarithm and that gives you a value for the entropy. And all I'm using is the Bekenstein-Hawking formula, which applies to the entropy in black holes, but it would work just as well in the opposite direction. And so this is an extremely unlikely situation. That is to say, sorry, that's not unlikely, that's the likely situation. What's unlikely is something like this, what we actually have, where you have a very, very uniform initial state. As Jim Peebles pointed out to me, that's what the universe is like, not like all the other possibilities which you could have. So we have this real puzzle. Why do we have this very, very special case? And if you put the Bekenstein-Hawking entropy into it, you see, and look at the numbers of black holes we see and all sorts of things, something like an unlikeliness of 1 in 10 to the power 104. Yes, 124, I think, if you put the dark matter in, things like that. So you get an enormously, incredibly special situation, and you have to see why it's like that. Just having a theory which gets rid of the singularities. See, I used to think for a long time that maybe quantum gravity was a very, very strange theory, in that its quantum mechanics was very strange, as well as being not just the standard quantum mechanics, but something which was very, very time asymmetrical. I couldn't make much sense of it, but the general sort of feeling was there that some scheme that combines general relativity with quantum mechanics has to involve this extraordinary asymmetry. Otherwise, we have a very unlikely situation. And I should explain, if put inflation, it doesn't really make any difference to this. It only deals with situations which are very, very close to Robertson-Walker. If they're very far from it, it doesn't do anything. So let's think of the issue now from the point of view of the second law of thermodynamics, because that's really a key issue. What we're looking at, well, this picture is just a sort of cartoon. The top 3 pictures, you imagine a gas in a box, where initially it's constrained to a smaller box in the corner. You open the box and the gas spreads out. So as time progresses, entropy increases left to right. Now, suppose we have in the bottom 3 pictures a box of a galactic scale containing many, many stars. And I'm supposing these are sort of randomly distributed. As time progresses, then they will start to clump and you will get eventually black holes. Entropy is still increasing from left to right. Time is increasing from left to right, but it's completely different with regard to the uniformity of the picture. What we actually see in our universe is a combination of top right and bottom left. We see uniformity. We don't see something which is, we see something which is, actually, let's go to the next picture because it's even more striking that it's not just a gas. This is the picture, I think, from the Kobe satellite, where they looked at the basically different frequencies. At the bottom, you see frequencies increasing, top is the intensity. And this curve is a Planck curve. And the actual observations, I should explain that these error bars on that curve are magnified by a factor of 500. So if you reduce them by a factor of 500, they would hug the curve to within the thickness of the incline, even the last one. So you see that it's a really very powerful indication, not simply that the distribution is pretty uniform, but that we are looking at a state of thermal equilibrium with regard to matter and radiation. So that's what it's telling us. Of course, the universe is expanding, and you have to take that into consideration. It doesn't really make any difference to this fact that you have a very, very special situation only in gravity. That's the point. The main point is it's only in gravity. You don't see this in our universe, that is. We don't see this in the matter. So what is it that makes the state so special? And I'm arguing that it can't be any ordinary kind of quantum gravity, string theory or what have you, because it doesn't have in it this fundamental time asymmetry in what we see. You could imagine a bouncing universe, but it wouldn't do this because the bounce would, in general, yes, it would be very much like the thing I had in the earlier picture here, where it would collapse in a great mess. And then if it's to bounce, it'd come out in a big mess. I mean, how do you lose all those degrees of freedom which are flowing right through the universe in all sorts of complicated ways? I mean, there's not much physics, it's just general ideas here. Now let me talk about the kind of curvature. This is a key point in my point of view. I was arguing, this is just a cartoon to show how the two different kinds of curvature, the Bauer curvature and the Ricci curvature, affect light rays. So if you have an observer up at the top of the picture looking back, then the Weyl curvature introduces distortion, and the Ricci curvature introduces a contraction or a positive lens, if you like. So things would be magnified as you look back, but here you get astigmatism. I should say that this is the trace-free Ricci tensor. The lambda term doesn't actually affect the light rays anyway. It doesn't do either. But you can see there's something very special about the absence of the Weyl curve, which is what we're apparently seeing in the Big Bang. And I used to postulate, well, whatever the theory is, it should say that the Weyl curvature is 0 at the Big Bang. So it's just a hand-waving postulate. Now, the key, yes, this is the point I want to make here. That's the Weyl curvature in particular singularity, which is the Big Bang, goes to 0, or as you approach it, whereas in generic singularities, it goes to infinity. Why do we have this extraordinary difference in the way that the Weyl curvature behaves? And if it's just as an explanation from some sort of quantum gravity theory, I don't see it. It's got to be something of a very different character. I mean, it's well motivated that you should look at quantum gravity to consider what to do with singularities. I can understand that completely. But if it is just a question of quantum gravity, we have a big puzzle. Now, let me continue and look at this from a different point of view, which was a point of view I adopted for many, many years, looking at radiation fields and things like this, is simply to look at the conformal structure. It's very nice because if you have the right kind of geometry, you can represent infinity as a nice boundary. This is hyperbolic plane, the hyperbolic plane in the Beltrami-Poincare, if you like, originally Beltrami, representation of hyperbolic geometry. And you see these Escher fish. This is an Escher, of course. And it's nice, this particular one, because you see the eyes on the fish are circles, and the circles remain exact circles no matter how close to the edge you get. It's illustrating the striking conformal nature of this squashing at the edge. And you can represent infinity. So that's the nice way. So can you use this conformal trick? Well, you have to bear in mind space-time is not a Euclidean, locally Euclidean type of geometry. It's locally Lorentzian. So we have to think about the light cones. In fact, what is the metric? The metric in general relativity, it's best to think of it as a time, really, because time is what you directly measure. Here I'm imagining two particles whizzing by through the same point, and here we have the null cone at that point, and we have to add the bowl-shaped and hill-shaped surfaces to represent the passage of time with regard to these different particles. And basically all we're doing is combining the two most famous formulae of 20th century physics, E equals mc squared and E equals h nu, Einstein and Max Planck. You combine the two, energy, Einstein tells you energy and frequency, energy and mass are equivalent. Planck tells you energy and frequency equivalent, so mass and frequency equivalent. So if you have a massive particle, it is ultimately a clock. For ordinary particles, it will be enormously high. You have to scale it down to get atomic or nuclear clocks, but it's basically the same idea. So it's the mass which gives you the scale. If you don't have mass, if you just have photons, it doesn't even see the hills. There is no passage of time with regard to a photon. There's no passage of time if you take classical Maxwell equations. Classical Maxwell equations are conformally invariant, so they just are interested in the light cones, or the null cones, I should say. They don't care about the hills-shaped surfaces. So the geometry, it's the causal geometry of space-time, if you like. The light cone, the null cone geometry of space-time, which is more primitive than the metric in the normal Einstein sense. And this is the way I like to look at things, particularly because infinity can be represented. And this enables us to talk about squashing infinity down. Now that we have a cosmological constant, we know that it becomes space-like. There's important work due to Helmut-Friedrich, which shows that in generic situations, as long as you have massless fields and things like that running around, generic situations, you can always do this. And you have a nice squashing down to infinity. And the Weyl curvature does go to 0 at the future boundary. Now, that's nothing unconventional about this. You could also imagine stretching out the Big Bang. And this was rather a good way, a very good way that at that time student, I think, Paul Todd, who rather than talking about the Weyl curvature directly, you just take the same sort of picture, but now the opposite way. You can stretch out the Big Bang to say that it makes a nice, smooth, conformal boundary. So you could The idea is that you could, in principle, extend conformally. You're saying there isn't really anything beyond infinity, or there wasn't really anything before the Big Bang, but nevertheless, it's mathematically very handy to pretend there was, and it makes the equations all work, and you can talk about both ends. Okay, that's not outrageous. What is outrageous is this idea that I introduced about 15 years ago, that you really take it seriously, and you say there was something after the remote, there will be something after the remote future, there was something before the Big Bang, and one was the conformal continuation of the other. So I'm saying that our Big Bang could, yes, indeed, be stretched out to be nice and smooth, but it has to match the remote future of a conformally squashed previous eon, as I'm calling it, cosmic eon. This actually makes the Weyl curvature 0 rather than finite, as Paul in his original discussion had. It has to be 0 because of Feldman Friedrich and all this, and calculations that I did quite early. You can see that the Weyl curvature has to go to 0. And that means that because the Weyl curvature is a conformal quantity, it has to be 0 in the next eon. So you do get a Weyl curvature hypothesis from this. You might say it's pretty outrageous. What about this cold, rarefied remote future being identified with this extremely hot, dense Big Bang? Well, you see the conformal things do just what you want, because the mass and the energy, the mass and the energy go the opposite directions. If I've got it, maybe talking through my head here. What I'm trying to say is that when you squash something down, it increases the temperature. If you stretch something out, it reduces the temperature, just because the way that energy, momentum, and mass and time are conjugate to each other. So you can imagine that this cooled, when you do the stretching, it will cool it down. So maybe the matching isn't so ridiculous. You have to have some hypothesis which tells you, because it isn't just photons in the remote future, we have hydrogen, we have probably stray electrons and positrons running around. You have plasma, and they might just become running around loose. And the hypothesis I introduce is that there is a fade out of mass in the remote future. The Big Bang is easier because you have very, very high temperatures, and you could say that the mass becomes irrelevant when the motion becomes very, very high. There is a physical assumption there, but it's a much weaker one to say that the mass fades out in the remote future. But I want to make both assumptions, and this makes the picture at least plausible. Now, for a long time, I gave talks on this, expecting that nobody could prove me wrong, so I could talk forever on the subject. But then I began to think if possibly you can have experimental tests. Here's the sort of thing. Here's the crossover. The curve in the middle is supposed to represent the three-dimensional crossover from previous eon to post-eon. And if you have light-like signals, electromagnetic signals, they could get through, or gravitational wave signals. So it's a possibility. Oh, so I'm going the wrong way. And this was the initial thing I thought about. Is suppose you imagine supermassive black hole collisions in the previous eon, they would produce signals which we might be able to see. And I have them in the bottom picture. The point I'm making here is that a cluster of galaxies, that would be where these supermassive black holes would mostly take, and they various galaxies in the cluster would run into each other from time to time until eventually there's one super duper one, which basically ultimately swallows the whole cluster. I don't know how much of it, but a good most of the cluster probably gets swallowed by the supermassive black hole. That's where all the mass energy goes. And that's would be eventually end up, you would see that as it would be a point in our sky. And I've indicated a couple of rather faint looking concentric circles representing what the gravitational radiation does. Now, Vahe Gerzajan, who first looked at these things for me, looked at circles which have low variance. That was his way of doing it. And he was looking at triples of circles which had the same center and low variance. To have triples with the same center to get a strong enough signal. And what I found very remarkable of this is from the Planck data, and the points indicate the centers of triples of circles of low variance. You expect to see them low variance. They're not singled out for the temperature, but by the low variance. And the point I want to make here is that you're very, very crowded in a very strange way, which is not what people expect for the universe. The cosmological principle should tell you that things are pretty uniform on a very large scale, as we're seeing here. Not true, according to this picture. And clumping also in color. Why is, well, you see color, of course, it's very confusing because red means low frequency, and therefore one normally thinks it's distant redshifted, but it is, no. Redshift, the blue ones at the top are redshifted because they're blue. The red ones at the bottom are blue shifted because they're red. That's because of the color coding. The redshifted ones at the top are not so distant because of the way it works. You have to look at the way the signal comes to us. The nearer ones are the ones which are more blue shifted. I'm getting it the wrong way around, which are more red shifted. The nearer ones are more red shifted. Sorry?
So just say about 5 minutes left.
I've got 2 minutes.
5.
Oh, I see. Okay, fine. No, I really just wanted to point out that the top ones are relatively close in the sense that they're inside our particle horizon. The ones at the top, the ones at the bottom right are outside our particle horizon. I think they do probably have an effect on the mass distribution according to the model. And in fact, the cold spot is somewhere around here. And I did wonder whether that might be due to a thinning out of material due to the attractive force of this thing in the previous eon. I don't know, that would be nice looked at. There was something interesting about the ones up at the top because you might actually see signals. And in fact, there are very strong clumpings of quasars in the sort of neighborhood here. I don't quite know what to make of that, but I should think things like that should be investigated in the future. It would be very interesting. Okay, that was those things. I'm going the wrong way, sorry. The final thing I wanted to say about the other type of signal which we've looked at, there are other possible signals we could look for. The other ones are the following. You look at the black hole evaporation. So you have a supermassive black hole formed from some galactic cluster, and you have to wait for the really big ones, something like 10 to the 100 years, or Google years, according to Don Page, I think 10 to the 103 years. Anyway, it's an awful long time. And all this radiation, all the content of the mass content of this black hole will go out in this radiation. And maybe there's a little bit comes out from the final pop. But it doesn't actually make much difference to what I want to say, because all this radiation, it comes out so late. Let's look at the last picture here. This is a picture from the paper in the monthly notices of the Royal Astronomical Society by myself, Christoph Meisner, Daniel Ann, and Pavel Mirovsky. And it appeared about a year ago in the monthly notices. And we were looking for things which I refer to as Hawking points. This is just what I was talking about. The bottom of the picture, I should say halfway down, the picture is a conformal diagram. The top part is just showing you the sort of thing you might see. Bottom part, right below the lowest horizontal line, we have the world line of a supermassive black hole. It doesn't start to radiate away until way right up until it's nearly at the crossing point. So the fact that this is all spread out doesn't make much difference. Because it's so late, it's just a point. So all the energy comes squashing through, and you can make an estimate. You can make integrals of things outside around it. So the fact that there's probably effectively a singularity in the cross, everywhere else it will be nice and smooth, according to the theory. But here you have something which would come through on the other side, probably smaller than a Planck scale. So you could say, okay, it's not ordinary classical physics there. It's some kind of quantum gravity going on. Yes, I'm agreeing with that. But it doesn't explain the uniformity that you get out here, which is the big puzzle. That's most of the sky. This, in 380,000 years, spreads out to this part here. This is the decoupling or last scattering. It doesn't make much difference where we are. That's when you start to see something. And the spreading out will be to about 4 degrees across the sky, which is about 8 times the diameter of the full moon. And this would give you a spot, something like a Gaussian, which is warmer in the middle, spreading towards the outside. And this is what we seem to see. We see evidence, according to the Christoph's analysis, the existence of these spots not being a random effect is confidence level of 99.98%. So they seem to be there. To locate the actual spots, Daniel used a different algorithm, and I'm not quite sure about the confidence there, but you can look at the 5 strongest points in the Planck data. You look back in the WMAP data, and you find they're there also in exactly the same places. You also look in the WMAP papers, WMAP data, and you find another point which is almost as strong. Look back in the Planck data, there it is in exactly the same place. So we have 6 points, which I say are pretty good candidates for being Hawking points. They would certainly affect cosmology to some degree. I mean, there'd be a scattering of these points. No, they're not everywhere. And we wouldn't actually see them because most of them occur within our past light cone. We can only see the ones which are just on the edge. That's us looking back. You can only see them when they're just on the edge. So the fact we only see 6 strong ones is probably not too surprising. There would be dozens, well, dozens is a huge underestimate, an enormous number of these things, according to theory, and they would have an influence. Most places which follow the sort of Jim Peebles and company evolution, that's fine, but there would be the odd place where you get something funny happening. So I think this is very interesting for people to look at. The thing is, what I'm trying to say is it doesn't seem to be much to do with quantum gravity. I mean, quantum gravity maybe can deal with the future singularities. Maybe it can deal with the Hawking points. I think that would be really a most interesting place where a good theory of quantum gravity might play a role and maybe produce something observational. Thank you very much.
Thank you very much, Roger, for the talk. Got time for questions.
Good.
Cameron, you have a question.
Yes, thank you very much, Roger, for a beautiful talk. So I want to make sure I understand. Part of the issue that you're raising about singularity makes an assumption that any theory of gravity which uses Einstein's theory will have problems resolving this issue. But suppose we say that we have a theory for which Einstein's theory breaks down as we approach Big Bang time. And not just by adding 1 or 2 terms or whatever, but actually the whole thing breaks down by the emergence of infinitely many light modes with a dual space emerging and all that. Then, as far as I can see, there would be no argument that that kind of theory, if we have such a theory, would not resolve this problem. So given this, I think in the context of string theory, we do see this happening again and again. That is, when we approach singular points, namely if you go back to infinitely dense situation or high temperatures, you always get some kind of a dual description, and the theory that you're dealing with breaks down due to the emergence of many light modes. So potentially that could resolve the issues that you're mentioning, as far as I can see.
Well, I don't quite follow it. I mean, I don't know the details of what you're saying, but what it would have to do is something very different as you approach these singularities in the future from what happens when you approach the singularities in the past.
Yes, exactly. So in other words, it could be that when you're approaching, for example, black hole will be different from the singularity of the Big Bang.
Where does the difference come in the theory? I mean, you say it's not GR, some other model, is that right?
You're right. So for example, if your space is contracting, it's very simple. I will give you a very simple model in string theory where we do know what happens. So if you take the universe to be a box, and if you suppose you shrink the 3-dimensional torus and you shrink the size, you know that after a while where the size of the box is smaller than the string size, the description breaks down. Einstein's theory breaks down. For black hole, you don't have that description, that issue at all. So in other words, there's 2 different situations that we're having.
I haven't understood why it's different in one direction of time from the other direction of time.
No, I'm just saying that the situation where the universe is shrinking is very different from the case where you have a black hole collapse in the context of string
theory. How does that difference appear in the mathematics then?
Yeah, so I'm just explaining it. So if you take a universe given by a 3-dimensional box, so you don't think about the black hole that's coming emerging, let's say, for a 3-dimensional torus. I'm just saying, if you imagine the universe as a 3-dimensional box, we do know a situation where we get a dual description when the universe becomes smaller than a string scale, a certain particular scale. Whereas that's not what happens in the context of black holes. So we do have this asymmetry. And so I think what you're pointing out is the issue that you would naturally, it's natural to have a dual description taking over. And I think I wholeheartedly agree with that picture, that we cannot have a single Einstein's picture covering the whole regime.
Perhaps we could move to another question. I think Samir was the person who got in there next with a question.
Okay, let's have another question.
Hi, thanks for that wonderful talk. I wanted to point out something that we are seeing from string theory, which might have this asymmetry that you were talking about.
Okay.
So in one picture we are finding from string theory, instead of black holes, we get these things called fuzzballs, which are large constructions of strings and brains, which are like the microshades of black holes. And the point is, of course, because the Bekenstein entropy is so large, the picture of the quantum gravity vacuum changes. Instead of just having structure at the Planck scale, what seems to happen is that you have virtual fluctuations of these black hole microstates of all sizes, because the unlikely fluctuation of a large mass object is cancelled by the large entropy of those large mass objects. They exactly cancel. So you have a picture where you have these virtual fluctuations of large things all over, except this is where there is an asymmetry. In an expanding cosmology, the very large virtual fluctuations of the black hole type states haven't had time to form. And you need this to actually reconcile some paradoxes with cosmology, exactly of the kind you were mentioning. So the same thing we need to solve the black hole puzzle, the existence of these virtual black hole states also shows us an asymmetry in cosmology, because extended virtual fluctuations cannot form until the light has had time to cross across that distance. I was just wondering if something like this kind of asymmetry might address what you were asking.
Well, maybe it would if I understood it better, but I can't quite see. You say fuzzballs or whatever it is, I don't have time to perform. Well, why do you assume that the before was of such a special nature? I mean, there's a big assumption which is put into the theory. Is that right? You have to say, you have to wait until some features appear in the model, and then they appear. Whereas when you're looking at the collapse situation, you take a different philosophy. I mean, it's sort of, it sounds to me awfully with these descriptions. And maybe I just don't understand the things you do better, which is probably true because I don't. But I mean, you have to have something where you really treat the time in an asymmetrical way. Because you say, okay, something doesn't have time to form, but then what was it that you decree was before I mean, there has to be a before in order to wait until something happens.
No, I agree. I don't understand the initial conditions very well. So, but maybe we can talk offline so other people could also.
I can understand. Okay, thank you. Thanks for your comment.
Maybe we could take a question from Edward Witten.
Of course.
Just a very small comment. The conventional explanation of the simplicity of the Big Bang is simply that we're only seeing back to a post-inflationary epoch.
But that doesn't work, you see. I mean, well, you see, inflation doesn't work either, because in my scheme, I mean, there's one question about the observations, which is a separate issue, because I can't really see how you can have inflation with CCC. It just doesn't work, because it expands the conformal gap between the Big Bang and what the last scattering, if you like, is enormously stretched, and so you have no chance of propagating effects from one side to the other. Of course, that's not a criticism with regard to models which aren't mine. With my model, I'm saying that you can't have inflation, but I'm not quite sure I understand your point that you're only looking at post-inflation. You see, you have to have some theory which tells you pre-inflation. I mean, that's where the quantum gravity be entering anyways.
The point of inflation is that exactly what there was pre-inflation tends to get lost. All those complexities in practice we don't see because we only see the post-inflationary universe.
Well, there's a huge number of assumptions involved there. You're saying that inflation is taking place in something which you don't see. I'm not sure I understand the logic of it.
For Manu, maybe we could take your question.
Yeah. So I was wondering, what are your thoughts about quantum gravity saying something about singularities, which are singularities in the sense of geodesic incompleteness and where there are no curvature invariants blowing up?
Yes, well, the theory, I mean, I think I even mentioned in that original paper, you know, maybe quantum gravity does something. I can't remember what I said exactly. But sure, the idea was floating around very much at that time that the singularities that arise maybe the way physics answers the question is to say, okay, we have to resort to quantum gravity. And that was a perfectly reasonable point of view, which I myself held for a long time and probably still hold. I think that's true. But what I don't see is how you can talk about the Big Bang in anything like the same way, because it's just different. And if your theory is supposed to get rid of singularities, and if you take one of the big reasons for doing quantum gravity, and I completely accept it, is to resolve the singularity problem. Now, if you take that viewpoint, then it's a very strange issue when you apply that philosophy to the Big Bang. It just doesn't seem to work because the Big Bang singularity is completely unlike a generic singularity. You set things up already in some way, even to allow inflation. You set things up in such a way to allow that sort of model to be considered seriously. You don't say, why is that initial singularity utterly different from those in the future? All I'm saying in the title of the talk, that the quantum gravity issue does not, well, it's strings specifically, but it's really a more general comment, that the quantum gravity issue does not resolve the Big Bang problem. The Big Bang problem is a completely different problem. So if you think of it in the terms of the conformal picture, you get a completely different insight into what the Big Bang is like, what it should be like, what you expect to see, what expectations there are from theory to observation. And it gives you a lot to work with. Whereas if you're just playing around with quantum gravity ideas, which fine, I'm very supportive of doing it. I don't want to give that impression that I'm against it. I'm supportive of it, but I don't quite see how any of these models is going to resolve the Big Bang issue. It's something quite different.
And perhaps just one final question from Gabriel Veneziano.
Yes, hi, Roger.
Oh, hi, yes.
Very nice talk.
Of course, you have ideas like this before me. Go on, yes.
I have one comment to what Qumran said and one to what Ed was saying. To Qumran, I think indeed you don't have to distinguish crunching or Big Bang singularities. What you see clearly in string theory is that when the curvature exceeds a certain value, which is still much smaller than the Planck value,
can I
there are corrections.
When you say curvature, do you mean either Weil or Ricci curvature?
Yes, either Ricci or Weil, the same, you get corrections. Now, honestly, we don't know for sure what happens to a space-like singularity like the Big Bang. But we know that there are corrections which become order 1 much before you reach the Planck scale. Now, the second comment is just to perhaps explain better what Ed Witten was saying. I think there is a confusion about what now most cosmologists call the Big Bang and what you were referring to. Namely, the Big Bang, the physical observable Big Bang is defined, if you want, as the end of inflation when the universe reheats and there is no singularity there.
Okay, well, that's very much consistent with your point of view that you put forward.
And then, of course, this Big Bang has nothing to do with the beginning of time. It's the end of inflation. And then you are perfectly right that still you have to understand how inflation comes about from some initial state. And that could be either your way of thinking, or maybe you just pick up one patch in your very inhomogeneous initial Big Bang, and that small patch becomes itself large, homogeneous, flat, and it eventually becomes our universe.
I understand the point of view, but it seems to me that none of these things really resolve the problem. I mean, I talked about some of these things in one of my books, I can't remember. I think it was Fashion, Faith, and Fantasy, where you imagine, the point you were making at the end about maybe we're lucky to find out, or lucky is the wrong word, but we find ourselves in a particular place where huge amounts of expansion took place, and that is anomalous. And of course, we have to find ourselves where we find ourselves, in a place where consciousness can arise on some planet or something like that. And so that singles it out. But I never quite understand why lots of little ones like this wouldn't be much more likely than one big one. That is to say, okay, we've got our neighborhood, maybe take our galactic cluster, that's good enough. And then why didn't you do something completely different outside that? I mean, this is more like this sort of anthropic argument, if you like.
Yeah.
So I can't quite see why arguments, I think they're okay, they're worth trying, but I think it's not the right track, because you get yourself one problem after another. You have to say why.
Maybe we should all thank Roger very much again for a very nice talk.
Okay.
I think it's time to move on. To
we can keep
Thank
discussing on Slack. Yeah.
Thank you for your questions, everybody. Thank you.
So, Alba, are you there?
Yes, I'm here. So, hi.
Hi. Hi.
Yeah, maybe I can try to share the screen, but probably first, because there's still the previous slide.
No, you can share right over. It will take.
Okay.
Do you want me to close my things down somehow?
Sure.
Unshare. Did I unshare?
Perfect.
Yep.
Work.
Okay, fantastic. So with apologies for the slightly delayed start, we're now very, very happy to have Alba Grassi here, who'll tell us about a geometric approach to black hole spectral theory.
Okay, so hi everyone, and well, first thank you very much to the organizer for organizing this nice conference, and also for the invitation to give this talk. So yeah, today I would like to present a certain. Sorry, I have a problem with my fancy. I would like to present a certain geometric or gauge theoretic approach to the spectral theory of a certain class of quantum mechanical operators, and then show some maybe more concrete application to the study of black holes. And most of what I'm going to talk about can be found in this. Okay, I cannot use the. I don't know. I cannot use it. Okay, maybe now I can. No, you don't. Okay. Anyway, most of what I'm going to talk about can be found in these works, which I did together with several great collaborators. Okay, so let me maybe start with some introduction and also a little bit of motivation. So one first point is the following. In general, we know that finding exact analytic solution for the spectral theory of quantum mechanical operators is extremely hard, right? We have some toy model that we like very much, and the standard example is the harmonic oscillator, where we can write down exact analytic solution for the quantization condition, the eigenfunction, and so on. But in general, this is much harder. So in order to make some progress in this direction, we needed to develop some new non-perturbative tools. And what we noticed during the last decade, more or less, is that basically, if we think of quantum mechanics from a geometrical point of view, similar in some sense to what Bailly and Parisi and Boros were doing in the 70s, then if we follow this geometrical approach, then we can actually make contact with supersymmetric gauge theory and also with topological string, and we can use tools, an idea that we have been developing in this context, to provide exact solution for a new family of operators. So what I would like to do today is the following. So in the first part, I would like to review some of the idea behind this geometric or gauge theoretic approach to spectral theory, and then show maybe more concrete application to black holes, and in particular, I will focus on the particular example of black hole. Now, from the point of view of spectral theory or quantum mechanics, black hole quasi-normal mode are like resonances or discrete. Okay, so we have like a discrete family of eigenvalues which have a non-zero imaginary part. And physically, these quantities are interesting because they encode the response of the black hole to a certain perturbation. And well, recently, this quantity also received a lot of attention because they also appear in the signal when we consider the merging of two black holes. In particular, they are the responsible for this downed oscillation that we see in this final or this ring down phase of the system. And one interesting aspect of this quantity is that if once we are able to measure them, then according to the no-head theorem, we can use that, for example, to determine the mass and the angular momentum of the final. And if we have enough precision to actually measure several of these oscillation frequencies, we can also use that to test this null hypothesis. Okay, so this was to introduce and motivate a little bit the various topics that are going to appear in this talk. Now I would like to go a little bit more into the detail, and in particular present some of the aspects behind this geometric or gauge theoretic approach to quantum mechanics. So a very important role in this approach is played by what are called the quantum periods. Okay, so these are, for example, the main building block which determine the exact quantization condition for the operators. Okay, so if we want to get exact analytic solution for the spectral theory of quantum mechanical operators, as a first step, we have to find exact analytic expression for this quantum theory. So what I would like to do now is to introduce this quantity a little bit more in details. And well, in order to do that, it's useful maybe to take one step back and start from the classical. Okay. So once we have a quantum mechanical operator of this form here, if we look at the classical counterpart, we can systematically associate to this operator a classical curve, which look like this, where now x and p are just complex values. And today we will actually focus on a particular subset of operators, which are those such that the classical curve coincide with a four-dimensional SU2 cyber-Witten. And there are actually several interesting extension and generalization of this framework, which make contact with higher rank gauge theory or also higher dimensional theory. But what I'm going to say today apply to this particular subset. And because of this connection with cyber and Witten, sometimes we refer to this operator as the quantum cyber-Witten. Now, one of the simplest but already non-trivial example, which is sometimes useful for pedagogical purposes, is the example of the modifier. So in this case, the relevant operator is given by this. Okay, so we have a Schrödinger type of equation with a hyperbolic cosine potential, and lambda here is like the strength of our potential. Now, when we look at the classical curve, basically we end up with the cyber-Witten curve of the four-dimensional n equals to SU2 superunits. Okay, and from the point of view of the gauge theory, then lambda here is played the role of, it's like the dynamical scale of the exponential of the gauge coupling, and this instead is the current branch value. And then once we have this classical setup here, we also associate to this curve the classical periods, which are defined in this way. Okay, so this is the what is usually called the cyber-Witten differential, and we integrate this differential over the corresponding sides. Now, once we have the classical periods, we can already get some intuition in the spectrum of this operator by using the semi-classical Borg-Sommer quantization. So in this setup, basically we are quantizing the classical phase space value, and the quantization looks like this, where n here is the quantum number and makes contact with the different energy. Okay. And in our framework, this classical volume is basically computed by the classical B period, which for this geometry we can compute explicitly in the particular example of the modifier material. For instance, this is given by this explicit expression here, where kappa and chi here are like elliptic integral of first and second kind. I think it says that the organizer has stopped the sharing. Maybe I can start again.
Nice.
Wasn't me.
Okay, can you see it again?
Yeah.
And okay, so this is basically the classical volume, and then this gives us already some kind of intuition on the spectrum. But it's known that in general, this semi-classical Borg-Sommer quantization has to be supplied by additional quantum correction, which are both perturbative and non-perturbative in each part. Now, the perturbative correction can be computed in a systematic way by using the all-order W. Okay. So in this method, basically what we do is that we make a perturbative ansatz of this form here. So this is a perturbative series in each bar. We plug it into the equation and we solve order by order each bar. And this is something that we can do in a relatively systematic way. And then we define the WKB period basically by integrating this perturbative quantum differential over the corresponding cycles. And when we take n equals 0, this gives us back the classical period. But on the top of that, we have a full tower of perturbative correction in each bar, which are essentially these corrections. Now, as it happens very often in physics, when we do perturbation theory, we end up with divergence series. Okay? And this is also the case here. So this is an asymptotic series with 0 radius of convergence. And if we want to get exact analytic answer, we need to find a way to sum this perturbative expansion. Now, before going into the resumation problem, let me just stress that this connection that we were observing at the level of the classical curve with this supersymmetric theory actually also persists at the WKB level, and a concrete realization of this connection can be seen, for example, from the fact that we can read the BPS spectrum of the underlying theory and also the corresponding central charge simply by looking at the singularity in the Borel plane of this WKB. So this is just to stress that the connection between these quantum mechanical operators and the supersymmetric theory is really something which is quite deep and that show up at various levels. Now, the point where this connection is really very strong is when it comes to finding an exact resumation of the WKB. Okay, so this is what we usually refer to for quantum periods. And by using four-dimensional gauge theory tools, which we can actually perform this resumation very explicitly. And there are actually several ways in which we can do that, depending on which problem we are interested in or which question we want to answer. There is one or another which may be more suitable. Now, today I will focus on one particular approach, which is the one that relies on the formulation in terms of four-dimensional omega background, and in particular, which goes back to the work of Nekrasov and Shafashvili. So a very important point in this approach is that basically we can map this very hard task of finding the resumation of this H-bar expansion in the WKB period. We can map this very hard question to something much simpler, which is how to compute the four-dimensional Nekrasov-Shafashvili image. And today, this is something that we really know how to do very explicitly. So if we go back to our example of the modified material, for example, the quantum D period can be computed exactly and explicitly in this form here. So we have some log of gamma function, and then we are basically repackaging everything into this function f, which is the Nekrasov-Shafashvili image. And for the example of the modified material, this is the free energy of the four-dimensional n equal to pure SU2 superluminous, which we already. This is the same gauge theory that show up at the classical level. Now, I think probably the main point that I want to make here is that this quantity is not just some kind of abstract object that we don't really know what it is. In this four-dimensional framework, this is really a very concrete object which needs a proper definition and that we know how to compute very explicitly. And for the purpose of this talk, one important property of this quantity is that it's exact in H bar, where H bar, from the point of view of the supersymmetric gauge theory, play the role of the omega background. Okay. So thanks to this supersymmetric gauge theory technology, we can sum this WKB period and get an exact analytic expression for this quantum. And then once we have this, we can write down in a more or less direct way the exact quantization condition for the spectrum, which in the case of the modified material look like this, where this is precisely the Nekrasov-Shafashvili image. Now, in the following, in order to stress that this is really a precise quantity that we can compute within this supersymmetric gauge theory framework, I will use this particular notation. Now, this is the example of the modified material. But actually, there are much larger and maybe also more interesting class of operators which we can study and which have been studied in a similar way. And also here, I just focus exclusively on the quantization condition, but this approach can also be used to compute other objects in spectral theory, like the eigenfunction, the Fermionic. Okay, so what I would like to do now is to apply this type of idea to the study of black holes, and more precisely, here I will focus only on this black hole. And okay, so this is the second. And to start with, we can start with the simplest example, which is the one of the four-dimensional Schwarz black hole. Okay, so in this case, the metric can be written explicitly in this form here. And in this convention, n is like the mass of our book. Okay. So this is a particular solution to the Einstein equation. And one maybe more or less natural question that we can ask is, okay, so we have the Schwarz metric, what happens if we add a small perturbation to this solution? And it was shown already a while ago by Reggie and Wheeler that linear perturbation of the Schwarz metric can be encoded in a relatively simple and also elegant second-order differential equation, which is the Reggie-Wheeler equation. Now, in order to derive this equation, it's convenient in some sense to exploit the symmetry of the problem and decompose the perturbation in something which looks more or less like this. Okay. So this is essentially a decomposition in terms of spherical harmonics, which encode the angular part. Then we also have the radial part and some time dependence. And then when we take these ansatz and we plug this back into the Einstein equation, we obtain, we do also some algebra and so on, we obtain the Reggie-Wheeler equation, which is this equation. Okay. So this is characterized by a potential, which looks like this. L here is related to this decomposition in spherical harmonics. And then we have the frequency here, omega, which comes from the fact that in the process we had some time derivative. And then we have the radial part, which is encoded in this quantity. Okay. So basically, this means that we can rephrase the problem of study linear perturbation of the Schwarz metric to study this Reggie-Wheeler equation. And for the particular setup of quasi-Normal mode, this Reggie-Wheeler equation also has to be supplied by some appropriate boundary condition. And in order to maybe get a feeling of which type of boundary condition we want to impose, sometimes it's useful to introduce the tortoise coordinate in this way here. Okay. So what we are doing here, essentially, we are making sure that the horizon now is at minus infinity. And when we write the potential, we have something which looks like this. And when we have this type of potential in quantum mechanics, usually the type of boundary condition that we impose are either outgoing or ingoing. And if we look at the physics of the problem, then at infinity, we don't want anything to come inside our universe. So we impose outgoing, and at the horizon, we have ingoing. Now, you can show that the Reggie-Wheeler equation with this particular type of boundary condition is satisfied only for a discrete complex set of frequencies, which I am going to denote in this way. And these are precisely what I call the black hole quasi-Normal. So what we notice basically is that if you do a little bit of algebra, you can write the Reggie-Wheeler equation as the quantum Seider-Witten curve for an SU2 gauge theory with 3 fields. And in order to do that, you have to use a particular dictionary between the gauge theoretic framework and the black hole setup, which is summarized in this table. So this basically means that this Reggie-Wheeler equation also belongs to this type of operator, which we can study using this gauge theoretic approach. And for example, if you take this point of view, then you can systematically and in a very straightforward way write down, for example, the exact quantization condition for this black hole quasi-Normal, which in this case it looks like this. Where this is the Nekrasov-Shatashvili free energy for the SU2 theory with 3 flavor. And as I was stressing earlier, this is a well-defined object that we know how to compute explicitly. And in order to make contact with black holes, we have to evaluate this quantity using this particular dictionary. And then indeed you can show, for example, that the quasi-normal mode frequencies which are obtained by imposing this quantization condition indeed agree with several computations that were done before by Berti, Cardoso, and collaborators. Now, this was the example of the Schwarzschild black hole, but the same approach can actually also be generalized to a larger class of black hole, for example, to the Kerr solution. Okay, so in this case, instead of one equation, you have a set of two equations, but you can study both of them within this gauge theoretical framework. And the relevant gauge theory also in this case is the theory with three flavors. But the dictionary now is going to be different with respect to what we saw in the Schwarzschild example. And also an interesting point is, for example, when we want to study the extremal limit in the Kerr framework, from the point of view of the Seider-Witten theory, this has a natural interpretation in terms of the decoupling limit, where we go from the theory with three flavors down to the theory of with two flavors. And this allows us also to analyze this extremal limit in a very smooth way. And then another maybe nice consequence is the fact that by using this approach, you can get a very explicit and also exact form for the spheroidal eigenvalue, which characterize the angular part of the Minkowski equation. And these are essentially given by the Nekrasov-Shepard energy evaluated at some particular using some particular function. Now, these are the two examples that we worked out in detail, and these are four-dimensional examples which are asymptotically flat. But there are also some preliminary results which indicate that this should also be possible to extend this to asymptotically ABS solution. It's just that in this case, the matter content of the gauge theory is going to be different. Instead of a theory with three flavors, we will have four flavors. And also this connection actually, so this is a particular subset of example, because so this connection recently was also extended to a much larger class of gravity background by these people here. And then and another interesting application is that you can actually compute several quantities that appear in this black hole analysis in a very explicit form. Like, for example, the finite frequency gravity factor in this framework is nothing else that up to some factor, the Nekrasov-Shepard energy, again, evaluated by using a particular dictionary. And a last point, which is also interesting, is that basically when you map this the problem to this supersymmetric gauge theory framework, you have some hidden symmetry which show up, and this is actually useful if you want to study, for example, stability in the context of Kerr. Okay, so let me now briefly conclude. So this geometric or gauge theoretic approach to spectral theory gives us some interesting new non-perturbative tools which can actually be applied in various contexts, including, for example, the study of black holes. And it would be maybe interesting to see at which point we can push that and what are the most interesting consequences. And okay, so thank you very much.
So thank you, Alba, for a very, very nice talk. Lots of people jumping in with questions. Andy.
Two related questions. Are you saying there's any relationship between these Seiberg-Witten curves of these gauge theories and the quasi-normal mode equations for the black holes, or they just happen to be the same equation? Is there some duality relating these systems, or you just found the same equation? And the second part of that question is, I mean, these are differential equations that we can only solve numerically, right? So finding them in it, is it helpful to find it in another system?
Okay, so the first part of the question, so we found it that it's the same equation. I don't know if there is a deep physical explanation, like why is it the NF = 3 or the NF = 4 theory which enter rather than another one. I don't know why is that, if there is a physical explanation for that. Yeah, what we found is that basically the equation is the same. So it's more a mathematical. And the second part of the question, yeah, is this. So the second part of the question was, what are the new insights that you can get using this approach, more or less, right? Yeah, so, well, for example, okay, so at the level of, if I insist on comparing with the numerics, which I think is great, for example, one point where the numerics is maybe a little bit hard is when you go to this extreme limit. And instead with this approach, this part you can do it very, very smoothly. But I guess my point is not really to compete with the numerics, which is and people are developing this in great details. But it's rather to give a new, maybe more analytical perspective, which can be useful. For example, to compute the gray body factor at finite frequency, which in this from this point of view, you can really obtain like very explicitly, and then you can show that in the zero frequency limit you recover your result that you obtain. And also this relation with this hidden symmetry that show up and is apparently useful for studying stability question. This is also something that you don't get just by studying numerical distribution.
Okay.
And maybe more wisdom. That's fine.
I had two questions. One was, I understand how to convert a Schrodinger problem to a spectral curve problem. How did you input into the Schrodinger problem the boundary conditions that are specific to quasi-normal modes? Was that part of the dictionary, or is that something natural to a spectral curve?
No, the spectral curve in the quantum Seibert Witten curve is an operator, so you can choose which boundary condition you want to impose, right? And for example, depending on which boundary condition you impose, you have a quantization of a certain cycle. For example, if you take the Kerr solution, okay, you know that you have two equations. You have the angular Czukowski and the radial Czukowski. And two have two different types of boundary conditions.
Right.
And the two are mapped basically to two different types of quantization.
I see. And my second question was, when you talk about stability, you specifically are talking about mode stability, not
yes.
the linear stability of the solution itself.
I'm talking about mode stability. Yes, that's at least this is what these people that I was mentioning were discussing.
Sandeep? Oh, I think you're muted.
Thanks for a very interesting talk. I don't really understand this connection between Schrodinger problems and the spectral curve. My questions are similar to Andy, but please allow me to ask them anyway. When is it that a Schrodinger problem can be mapped to an interesting curve you get out of super symmetric Yang-Mills theories? I mean, is there some general understanding of that, or is it just that it happened to work out for these black hole problems? I mean, it's quite miraculous to me. Go ahead, please, if you could. Is there any sort of understanding? Sorry to make you repeat this, but just in case. Or is it just, yeah.
There are actually a much larger class of problems which can be studied in this way. So this is not just specific to this black hole example. There are like many problems in the higher order equation, even difference equation when you look in terms of relativistic integrable system and so on. So this gauge theoretic approach is quite general, and it's not just for this particular example.
I see.
And usually, if I have an operator and I want to see if I can study that by using this approach, I just see if I can connect that with one of these gauge theory, and then you can.
I see. So you just compare it with the list of all the gauge theory curves, and you see if they fit. Okay. And then, sorry, but again, did this allow you to get a analytic approximation in some way to, for example, the Kerr quasi-normal modes? Does it, in a practical way, help you? You know, you might have said that. Yeah, go ahead.
What do you mean by practical?
Well, I mean, I mean, you may not do as well as the numerics in all detail or something, but as an approximation, does it help you just get a handle on the exact quasi-normal modes? Or what does it buy you just in a very pedestrian way?
Yeah, that is what I was already answering to Andy, for example.
Yeah.
For example, if you just want to stick to the numerics and compare with the numerics, you have the extreme and limit that where you can and yeah, it's essentially this. I would give the same answer.
Okay. Thank you.
Okay, so there are some more questions that people want to ask, but I think we need to move on to the discussion session, please. So let's thank Alba again. And hopefully other people can ask questions this afternoon.
Thank you very much. So there's not much to say since we are all pretty much experts by now in these informal discussions. However, I do want to thank Malena and Tiago. Malena designed the website that many are saying is the most beautiful strings website ever, and I agree. And Tiago is making sure that all the PDFs are posted timely, updated, all the videos are always online. And that's super convenient, in particular for this discussion. So Sabrina's video and PDF are already online, say. And so I would like to propose a big thank you to Malena and Tiago. And then, without further ado, Andy and Tomasz, you know the rules, 20 minutes, followed by 30 minutes, and this 30 is 30 plus minus something, plus something, of a relaxed discussion. So please, I don't know who goes first, if Andy or Tomasz, take it away.
Okay, well, since you were thanking everybody else but yourself, let me thank you and Nathan for this fun and different workshop. So I'm not gonna review celestial holography. I'm just gonna look to the future, and I'm gonna present what I think of as a greedy wish list of things that we might get in the next 5 years. None of these are cats in the bag, but they're problems that we hope to address in the next 5 years in this program of celestial holography. Now, just 30 seconds for those of you, especially in California, who was 5:30 in the morning, who missed Sabrina's excellent review talk. The basic idea of celestial holography is that you rewrite the S matrix for 4-dimensional scattering in quantum gravity as a correlation function of a celestial conformal field theory on the sphere, and this celestial sphere sits up here at null infinity. And this would be a theory without gravity. This would be a theory with gravity. And there's a holographic dictionary, which Sabrina reviewed an awful lot of during her review this morning. But I'm not going to review any of that. I'm going to just talk about what we might hope for in the next 5 years. What are the problems that we could hope to solve? And so one of them is to find all the non-trivial symmetries, the ones that have measurable physical consequences, of the laws of physics that we've known, GR for 100 years, and the standard model for 50 years, in the approximation where there's no cosmological constant. If there's a cosmological constant, we have to worry about de Sitter, whatever. Okay, so we're just imagining we're working in the approximation where space is flat. Now, these symmetries include the antipodal subgroup of BMS acting on the future and BMS acting on the fact. This is past. This is a particular set of super translations plus Lorentz transformations. But it's become clear in the last 5 years that this is only the beginning, that this is already an infinite number of symmetries. but it's become clear that there's an infinite tower of symmetries that generalize this. And these symmetries have physical measurable consequences. They're non-trivial symmetries that act on the S matrix in a non-trivial way. And we don't know what they are. And I would say that, we theorists are behind on our homework. This isn't new laws of physics. We don't need experimentalists can't help us with this problem. They've already given us all the information we could possibly want. We have the laws of physics, and we don't understand what their consequences are, in some cases, very direct experimental consequences. Now, and it turns out to be a really surprising that we haven't solved this problem in 50 years. It's also surprising what an incredibly subtle problem it is. And there are many equivalent formalisms to address this problem: Hamiltonian approach, asymptotic symmetries, symmetries of the S matrix, soft theorems, and so on. But something that seems to be emerging is that the celestial formalism, writing everything covariantly on the celestial sphere, is very powerful. Indeed, in the last 2 weeks, we found that the positive helicity symmetries associated with positive helicity soft gravitons all organize themselves into a W infinity algebra. That would have been very hard to see in a Hamiltonian formulation. And solving this problem is step 0 for flat holography. The first thing that happened in ADS-CFT was the identification of the bulk symmetries of quantum string theory in ADS with various boundary field theories. And so the first step in developing a holographic correspondence is understanding what the symmetries are. Now, this is the real world. We're not assuming string theory either. I'm stressing both of these are bottom-up things. And so there are a plethora of experimental predictions which we should make and then persuade or interest our experimental friends in verifying, that are associated with the infinite tower of conservation laws associated with these symmetries. The first of these is already underway, the detection of gravitational memory. So typical of the experimental consequences of these symmetries is that they're conservation laws that relate some collection of numbers from ingoing data to outgoing data and to some other collection associated with the outgoing data. And part of that data will be the memory, the gravitational memory, the displacement. Measurement of this is already underway at LIGO. Estimates of time are on the order of 5 years before they get this data for us. That's far from the end of the story because there are many more symmetries. So the subleading soft graviton theorem, which is related to conformal symmetry or super rotation symmetry of the celestial sphere, also has some asymmetry associated with it, so-called spin memory. And the LIGO team has talked somewhat about measuring that. It's harder. There's some proposal. I don't know how probable it is, but certainly at upcoming LISA, one might hope to measure this. Color memory. Now, color is confined, of course, so you can't see it out at infinity, but if you're fast enough, you can see it before confinement sets in. And there's a proposal to measure this at the already funded $1 billion electron ion collider. Now, interestingly, electromagnetic memory, which is in the same category of phenomena. There have been various proposals. I don't think any of these proposals were meant as existence proof of how you could measure it. Nobody has really put out a good proposal for a detector that somebody would actually build. But it's analogous. I should mention the magnetic Aharonov-Bohm effect has been measured, but in their original paper, there was also electric Aharonov-Bohm effect, which I think can be regarded as a subset of electromagnetic memory calculations. And there has been some work. It turns out to be very hard to measure because you have to keep phase correlations. And there's been some work, not very much, and they have not yet measured even the electric Aharonov-Bohm effect, but it's plausible. And there's more generally electromagnetic memory effects. And I say that it's also, I've found it to echo Nima. It's very stimulating to talk to experimentalists about how to measure things. It sharpens our thinking about what the nature of physical reality is and what the kind of theoretical structures we should look for. Now, both of those most of the work in celestial holography has been bottom up. That is, we've started with the laws of nature that we know and tried to deduce just from consistency and symmetry requirements what kind of holographic duality could exist in the real world. But it would be really interesting to have some top-down examples it's a duality that exists only in quantum gravity, so the natural place to look for it is string theory. There's the BFSS matrix model that is a dual representation of string theory in 10 or 11 dimensions that perhaps could be connected to some kind of celestial holography. There's also the n=2 string in 4 dimensions, which is a very simple yet rich theory that might have an interesting dual. Also, I'm very impressed by beautiful talks by Gopakumar and Gabriel, in which they kind of start with the world sheet, the string world sheet, and construct the boundary conformal field theory. And of course, they were working in they had a complicated interacting string world sheet. And here, there is a way, there are examples, and things like this were also done 20 years ago by Givyan Kutuzov-Seiberg, who did Nova-Schwarz ADS3 cross S3. And to get pieces or all of the boundary conformal field theory out of the world sheet. And indeed, there should be some way some sense in which the string world sheet in some approximation is the celestial sphere. That came out of work of Stieberger and Taylor. Finally, we'd like to characterize characterize constraints from the infinitely many soft conservation laws on information flow in and out of black holes. So we know that energy conservation forces quantum correlations between the microstate of the black hole and the outgoing Hawking quanta. They must be in a total state of the same energy. And now we have infinitely many conservation laws, which enforce infinitely many correlations between the black hole, microstate of the black hole, and the microstate of the outgoing Hawking radiation. This is the soft hair program. And in order to push this, see how far this goes, we need to be granted wish 1 first. We need to have a complete understanding of exactly what all these symmetries are and how they act. And finally, there's a very interesting analytic structure of the scattering amplitudes in the celestial conformal field theory. As Sabrina was mentioning, as a function of the conformal weights, we just have a series of poles at the negative integers on the complex conformal weight plane. It's writing things on the celestial sphere also bakes in the fact that there's a good UV behavior, so we don't have the freedom to be working in the swampland where things don't have good UV completions. And so we can, maybe a good place to put together all the many constraints that many people in many different fields have been talking about on the 4-point graviton scattering amplitude, and see what the most general form may be. And maybe this will lead us from the bottom back up to the top. Maybe, as many people have conjectured, some version of the string scattering 4-point function is the unique form. And so, okay, Tom is going to go next, but we'll take questions of any kind, and thank you for listening. I hope I didn't go too much over.
We are at 13, it's good. Thank you very much, Andy.
All right.
And let's pass it over to Tomasz then for his half. Yeah, it's good. Please unmute. You do have to unmute yourself.
Okay, very good. Thanks, Pedro. And thanks, Andy. Well, quite a wish list. So here's how we got there, at least to some tiny part of it. So I will start with general remarks, then I will try to outline some roadmap to celestial CFT, and finally summarize on one page. But first of all, let me thank organizers for this wonderful conference and for giving the opportunity to say a few words about celestial holography. The first thing that I want to stress, actually, a special role on 4 dimensions in celestial holography. The whole story started from soft theorems, which describe infinite behavior of scattering amplitudes and the relation of those soft theorems to order identities of asymptotic symmetries. Now, the infinite singularities appear in any number of dimensions, but their physical interpretation is very different in higher dimension than it is in 4 dimensions. In higher dimensions, simply there's too little space to produce Bremsstrahlung. So there are, in other words, charged particles do not come surrounded by clouds of infinite number of photons. And similarly, in loop diagrams, when, for example, you look at the photon propagator, you see that loops are convergent as the photon momentum goes to 0 in higher dimensions, while they have logarithmic divergences in 4 dimensions. Actually, these divergences are responsible for the running of the coupling constants. So there's indeed a very special interplay of infrared and ultraviolet in 4 dimensions. Another thing is that only on 4 dimension, you have celestial sphere at null infinity. You have natural complex structure on which you can develop conformal field theory. And Lorentz symmetry is mapped into isometries of celestial sphere. In general, then superrotations become diffeomorphisms of celestial sphere. So only in 4 dimensions, you have these relation between fundamental symmetries on both sides. Okay, next thing is supersymmetry. Okay, so that's very simple story. When you know that supersymmetry algebra closes on momentum, in terms of celestial coordinates, momentum is not holomorphic. So there is no obvious separation between left and right. So even supersymmetric theory, you do not expect to have left and supersymmetries for left and right movers. So in celestial holography, supersymmetry does not play as fundamental role as it does in superstring theory. Okay, so now what about strings? As I mentioned before, there is no obvious decoupling between Z and Z bar between left and right movers, but celestial amplitudes with gravitons are ultraviolet divergence. And actually the degree of this divergence grows with the number of external gravitons. So the only way to have gravitational celestial amplitudes is in a theory in which you have exponential suppression at high energies. And here, of course, comes string theory, in which this with soft ultraviolet behavior, which is actually for 4-point functions, is controlled by Grossman saddle point. There's a similar limit for celestial amplitudes in which some conformal dimensions go to infinity, And in this case, this Grossman saddle point links the vertex position to the kinematic variable of the celestial sphere. So in some way, string worldsheet gets pinned to celestial sphere. And I suspect this relation is actually valid not only limit, but there is some deeper relation between strings and celestial holography. So to summarize this part, we start off on the right foot in 4 dimensions without supersymmetry and some very interesting relation to strings. All right, so here is what can we do in order to identify this celestial conformal field theory. The goal is to describe 4-dimensional physics as 2-dimensional conformal field theory. Okay, so the first thing to start, obviously, is perturbative Young-Mills, which we know very well, amazing progress over the last few years. And reconstructing this underlying conformal field theory is essentially a type of a detective work. So that explains my figure here, which is my best attempt to imitate Andy's artwork. I even do not dare to imitate Sabrina, who is beyond my abilities. So as any detective work, it consists of office work, which is identifying connections, motifs, symmetries, and this beautiful work that Sabrina mentioned on celestial diamonds of Sabrina and Apum and Trevisane go exactly in this direction, as well as this recent mysterious work of Andy about the relation to W infinity algebra. All this will help us in identify this conformal field theory. What I want to focus here of another aspect of detective work, which is called field work, like would be normally identifying trying DNA samples like cups and so on. Here, we want to look at the amplitudes and to understand what's inside and understand the content and to understand celestial amplitudes as conformal colorators and see the content by exposing conformal blocks. Now, to do that, what you do, you start with celestial amplitudes, as Sabrina explained, and interpret them conformal field as celestial conformal field correlators or primary fields. Now, the basic building blocks of conformal field theory are 3-point functions. Now, here you hit the first obstacle, because on shell, 3 gluon amplitudes vanish due to kinematic constraints. So, well, one can try to change it by modifying space, the metric signature to comma 2, that replaces celestial sphere by celestial torus, that changes essentially the nature of the scattering problem. So I won't go here into that, but I want to just move to 4-point functions. And as you know very well, they depend just on the cross ratio of the 4 points. Now, they are related to kinematic variables. They are related to 2 scattering angles. One of is just regular scattering angle, and the other one is the angle that measures the planarity of events. And of course, 4-dimensional scattering, due to moment conservation, not 4-dimensional, 4-particle scattering events are planar. So what one finds that this 4-point correlation function vanishes everywhere except on the real axis. Actually, as you see here, it's a distribution valued, so it is not a typical conformal field correlator. So seeing that, you can do 2 things. You can just take it as it is and try to perform conformal block decomposition, or what we did in our recent paper with my collaborators, including my student Benzu, who will be graduating next year. We extended this 4-point correlator to the whole plane by performing something which is called shadow transformation. And then you can proceed like in textbooks, perform conformal block decomposition. And as a result, you find an infinite number of conformal blocks with various spins and various gauge group representations. So you find really an infinite number of Verma modules. So this is not a minimal conformal field theory. It's hopefully it's not maximal. Hopefully it's something relatively simple. And actually, in order to really figure out what it is, one has to want to think more about several open problems. For example, one need a more refined relation between the amplitudes and conformal field theory correlators. One has to understand the role of four-dimensional kinematics in 2 dimensions. One has to understand the spectrum and conformal blocks. All these are other technical problems. So just I want to wrap up with, again, some more general remarks. So as you see now, celestial holography describes 4-dimensional physics in the framework of 2-dimensional conformal field theory on celestial sphere. It builds upon some very interesting and quite recent developments in general relativity, amplitude program, and conformal field theory. From general relativity, it takes symmetries of asymptotically flat spacetime where we live. From amplitudes, here we take gluon amplitudes as you measure them at the Large Hadron Collider, and it puts everything in the framework of conformal field theory that we all know and love from string theory. So it is a win-win situation, and I'm sure that Andy will get his wish list sooner than he thinks. Thank you.
Thank you very much. You are perfectly on time. Thank you very much, Tomasz and Andy, for a beautiful setup. So I remind everyone, please raise your hand, wave if your comment is related to what's being discussed right now. And if your internet allows, please turn on your camera. It's always much more fun to see each other. So Tomasz, maybe you could stop sharing so we can have this gallery mode and we can see everyone's face. Perfect. Okay, so let me start with Shuheng, that I think in these particular discussions has been very quiet so far.
Hello, hi Andy and Tomasz. Thanks for the very inspiring presentation. So I want to follow up on a question raised by Simone earlier at Sabrina's talk about crossing symmetry. So celestial holography relates scattering amplitudes to Euclidean CFT correlator. Now, crossing symmetry in amplitudes is very subtle, as beautifully reviewed by Sebastian last week. On the other hand, crossing symmetry in Euclidean CFT is rather straightforward, just follows from microcausality. So I was wondering, like, if this is an interesting question, like, how much can celestial holography teach us about crossing symmetry, and how should I translate crossing symmetry from one side to another?
May I answer that? In order to do that, you have to have the correlators which are defined on a whole complex plane. So I think that the best way to go is to extend them in some way, and this can be done by using the shadow transform. And then you can start talking about relating different channels. There is here additional complication compared to usual CFT, that you have incoming and outgoing states, which are represented by different primary operators. Okay, so, but still, I think this can be done, and that's what actually we are working on.
Maybe I could comment too. Just first thing, we don't know. It's beyond what we've understood so far. The second is there's 4D crossing and there's 2D crossing, and they're related but different. And the third is that there are various singularities in this subject, and the natural way to deal with them seems to be to do what has been done uniformly pretty much in the amplitudes community, which is continue to 2-2 signature. And in 2-2 signature, null infinity has only one component. And so it's not like in 3-1. And so I think crossing must also be trivial in 2-2. Those are comments, not an answer.
Let's go to Mohab.
I'm wondering whether you can apply this program for not the field theory amplitudes, but for the string theory amplitudes. So, I mean, so for example, you mentioned the n = 2 string, Andy, and there the string amplitudes are known. And so one could imagine trying to understand what celestial holography says and whether it describes the bulk string theory as a conformal field theory on the, well, it's not a sphere in this case because of the signature, but on the, let's say, in generalized sense on the celestial sphere.
Tom's written the only papers on this subject, so why don't you take it?
Sorry?
Tom, do you want to take?
Okay, all right. Okay. So what we started from really 4-point scattering amplitude as we have from open string theory. And then you construct celestial amplitude and you see a nice thing that indeed you have control, you obtain something which makes sense because you have exponential suppression at high energies. So you obtain celestial amplitude, okay, which graviton amplitude, anti-graviton amplitudes. And then, of course, you can think what is in this case, what is the underlying conformal field theory. Okay, so that's what you want to do.
Yes, but can you identify what the conformal field theory is, for example, for this?
No, we go even without strings and kind of Young-Mills, we still don't know what it is, but I think we are very close to identifying it.
Sorry. I think Gabriele's comment might have a comment which is related. Yeah.
Yeah, I think I have a comment which is related. Hi, Tom, and hi, Andy. Nice seeing you again. The point is, it's about unitarity, and also it's about the 4 graviton amplitude, stringy gravitons or point-like gravitons, doesn't matter. I want to remind you that the high energy behavior at fixed angle is not given by the Gross-Mende saddle point, which is a complex saddle point and leads to an exponential vanishing of the amplitude, is given by the iconal in agreement with the fact that there is gravitational deflection, in perfect agreement. This goes back to the work of Toft, Amati, Cefaloni, and myself, Muzinich, and Soldate. So I don't think you can use for the high energy limit the Gross-Mende formula. The second remark is about unitarity. Again, unitarity is evident at large impact parameter or large angular momenta in the iconal approximation. And so my suggestion is, why don't you look at the amplitudes at fixed angular momentum and energy instead of fixed t and s? Because this is in angular momentum that unitarity is diagonalized. So can you generalize your connection to celestial amplitudes to amplitude defined at fixed angular momentum?
So does someone want to take up on this?
Comment and the question.
Yeah, Gabriele, let me ask you this. You see, I can take 4-point amplitudes as a function of SNT, yes? Yeah. And then I consider the limit in which the ratio is fixed, yes, it's usual fixed angle. And I take the limit when SCNT goes to infinity.
Yeah.
And then I'm using Stirling formula essentially for gamma functions, and I find asymptotic behavior.
But that's not a unitary amplitude and not the leading term, because you have to sum to infinite genus to get the right result. We had a discussion in my discussion session with David Gross.
Absolutely. Just to say something very simple that Tom noticed, that the S over T, or T over S, I guess, becomes the conformal cross ratio on the celestial sphere. And so that's a nice simple relationship. And all that's been done at this point, yes, of course, it's true that at very high energies, the string scattering amplitude is not the gross Mende. But you know what has been done so far, there's only 2 papers on this, and I think it should be a very rich subject. There's only 2 papers on this, the relationship between, or maybe really only 1 paper, the relationship, you know, the celestial version of the string amplitudes, and all that was done, I'm not on any of them, all that was done was to, you know, take the Mellon transform of the amplitudes and look at the analytic form and verify that it had the pole. Well, later it was verified that the poles were in the right places on the negative real axis. And it was enough that they fall off exponentially. They don't have to fall off to make them well defined. They are well defined in, the Mellon transforms are well defined at string tree level, even though it's not the black hole pair production fall off. But I think there should be some nice connection between, you know, the operator product expansion and the celestial conformal field theory, and the operator product expansion of vertex operators on the string world sheet, maybe using the kind of tools that Hirosi and Wan used when they looked at strings in SL2R at the vertex operators, took the vertex operator to the boundary. So there's a world of stuff to do here, and there's just 1 paper.
Yeah, no, just to finish, I will be brief. I mean, what I wanted to say is that there is a lot of results, as you know, in the 2-body problem in GR, even in the ultra-relativistic or massless limit. We know the answer up to 2 loops. So we know how things go at large angular momenta or large impact parameters.
Yeah.
And it's perturbative, it's not vanishing exponentially, the amplitude is there, healthy. So I think one thing you could certainly do first is to translate all those results in your language and see if they teach us something. On the other hand, if you want to go to the black hole formation regime, then you better work at small impact parameters, smaller than the energy in G Newton units of the collision.
Yeah.
And that's why I was suggesting that you look also at that dictionary.
Yeah.
From angular momentum to your variables.
Atul?
I wanted to ask Andy if, this is probably a slightly technical question, but in your W infinity paper, could you explain the role of the light transforms in the W infinity story?
Well, a little bit black magic. So which I hope we'll understand in the coming whatever, but there was a Monica and Alfredo and Mina and I worked out the algebra of all the, not just the leading soft graviton theorem, but once you get to the sub-leading, you find that they commute them and you have more and more currents and you have an infinite tower of currents. This infinite tower of currents had been found by other methods, Hamada and a couple other papers. There's more and more soft theorems that involve higher and higher angular momentum. And we constructed the algebra, and it was pretty complicated. And then I noticed that, but we wrote it down in closed form, had a lot of gamma functions in it. And I just noticed that if you redefine the generators in a way that is not covariant under the right-moving SL2R, the whole tower dramatically simplifies, and it's just W1 plus infinity. And that redefinition is essentially a light transform on one side, but it's not a very familiar light transform because the representations that appear are integers. The original representations that appear are integers with negative weights. That's one of the features of celestial conformal field theory, is that they don't have the usual positive real weights. And so they're actually finite dimensional representations. So it's the same formula, but looks a little different because of the integer weights. I just wrote it out in modes. I didn't write it as a light transform, but I think it is the light transform. And when you do that transformation, then everything simplifies dramatically. And also the gluons are in irreducible representations of the W algebra too. So it's clearly a big technical simplification. And there are also hints of W algebras in the n=2 string. And so we thought maybe this could make for some connection between the, with n=2 string theory.
Yes, this is in some sense a symmetry algebra of self-dual gravity, or self-dual Yang-Mills probably as well. So in some sense, is the conjecture here that we are just seeing since we are only doing the positive helicity OPEs here, are we somehow just seeing the infinite dimensional symmetry algebra of the self-dual sector?
Well,
between amplitudes.
The shamelessly wild conjecture with very little evidence would be that, yeah, these currents are all that you have in the self-dual gravity, and that the dual of the holographic dual of self-dual gravity is some two-dimensional W theory, and its quantization would be given by, as Hirosi and Kumran showed, its quantization would be given by the n=2 string, but a lot could go wrong.
Thanks. Kevin?
Yeah, just to follow up with what Pavel said, it seems these algebras, like the W infinity algebra, appears in a very simple way from Penrose's nonlinear graviton construction, which is of course closely related to the n=2 string.
Right, that's the same thing. That's the same appearance of W infinity. And so the question is whether that W infinity is the same as the W infinity that appears in the...
So I just wanted to clarify one point. So if you were to build the algebra from a nonlinear graviton, what you would find is some very big chiral algebra. But if you looked at the Lie algebra of conformal primaries, that's W infinity. So that the actual chiral algebra is even bigger. Is this what you found too?
Are you alluding to the fact that the chiral algebra is the wedge is the Ketz-Moody algebra of the wedge algebra of W infinity?
Yes, I think so. It's like it looks like loops in W infinity.
Right. So there's that, but then in the quantum theory, you have the enveloping algebra of that algebra.
Exactly. Yeah.
I've just learned about all this stuff in the last week. There's a beautiful, my students are reading it and helping me with it. There's some beautiful papers by Chris Pope from the early 90s. Yeah. And this also happens in ordinary two-dimensional gravity. I guess, Polyakov did the light cone quantization of two-dimensional gravity, and there he has an SL2R current algebra, not a Versauer algebra. But we know that 2D gravity, we usually think of it as a Versauer algebra, but it's all consistent because the enveloping algebra of the SL2R current algebra contains the Versauer algebra.
Like what made me excited about this stuff is these algebras are really close to stuff that Davide and I found when we were studying holography for topological string. And also there's a full paper of Edward from the early 90s where he studied the C=1 string, I think.
That also has W, the same algebra.
Exactly, it's like symmetries with a three-dimensional cone instead of a two-dimensional cone.
Yeah.
Yeah, so this is what made me convinced that thinking about topological strings and twistor space, a holography for it would be a good setting for the story.
Well, certainly topological theories like self-dual graphs, I don't know whether you call that topological or not, but topological like theories are certainly prime hunting grounds for theories where we could actually really construct a celestial dual.
Let me go to Ashok.
Yeah, so I have a somewhat general question that whether it's in string theory or any theory of gravity, once you go to loop amplitudes, the S matrix becomes infrared divergent, right? And the question is, how will this affect the celestial correlators? So take the 4-point S matrix and it gets infrared divergent at one loop. How will it show up in the celestial correlator?
Okay, I guess I'll take that. I think the whole story of infrared divergences has a very nice picture in the celestial framework. Basically, infrared divergences appear because we weren't careful about imposing the conservation laws, and they appear when they set all amplitudes, which are basically all Fock-space amplitudes, set them to 0 when you exponentiate the infrared divergences, and any amplitude which doesn't violate the conservation laws, which is kind of baked into the celestial conformal field theory formulation, can be non-zero. And so but amplitudes which don't violate the conservation laws, have some kind of dressings, and the dressings can be understood as insertions of Goldstone boson fields, as we discussed in detail in Arcani Hamed, Pedro Clario, and myself. So I think the infrared divergence story there's still more to understand about it, but I think it works nicely in this.
Does that mean that one can now go backwards and try to define S matrix appropriately, which is infrared finite? Starting from
yeah, so of course, Fadeev and Kulish told us how to define infrared finite S matrices. The one thing that they missed is that the dressing for an incoming particle doesn't need to be in the incoming state. It can be in the outgoing state. You can move the soft particles from the in state to the out state. So Fadeev Kulish seemed weird because, of course, we don't dress. The LHC doesn't have, a little dressing shop where all the protons have to get dressed before they enter into the beam. So in that context, the dressing goes to the outside, it's the Cherenkov rate, it goes out. But having that dressing come out in the out state through the same sort of algebra, and this is, I guess, was proven by Ooguri, and we worked out the first order, but Ooguri, I forget the second author on that, proved it.
Choi.
Chong? Yeah.
Choi, Sang-Min Choi.
Yeah, so I think that the story of infrared divergences works nicely.
I'll soon go to the veterans. Thank you for your patience, but first one more from Igor.
Oh, hello, thank you. Can I say now?
Yeah.
Speaker? Okay, the W infinity algebras looking very much like the Kac-Mode algebras. To me, the natural method for quantization is the Balatin-Vinkovsky method. So have you studied the BRST cohomology in order to quantize the theory, meaning celestial holography, from BRST cohomology? And the other question is, this algebras also appears if you generalize to the celestial sphere with punctures, or even the celestial torus or Riemann surface with more modular parameters. So these are, as I can articulate my questions without taking much time. I am sorry. Thank you.
I guess I'll take that. So we haven't studied, so far all this discussion is tree level, and the hope would be, you know, that you get the quantization of little w infinity, which seems to have a unique one parameter family of big W quantizations. And it was very hard to see. And one of the nice things about, which has all been worked out for us, one of the nice things is that it was very hard to see how this tower of soft theorems, we know that there's quantum corrections to the subleading soft theorem and the subleading soft graviton theorem, was very hard to see how you could deform this structure and still have a closed algebra before we understood that it was organized into little w infinity. But the problem of how you deform big W infinity was already solved in the early 90s. So the hope would be that that little w infinity gets deformed in big W infinity in the quantum theory. But that's going to,
if I may, what motivated my question is that you may want to abelianize. I am sorry if I am spelling things correctly. My English is very bad. Your algebra is a very powerful method to do quantum field theory for more generic non-abelian field theory. So have you thought how to abelianize the W infinity algebras? And my final question would be the celestial torus that you have proposed. Can there have you thought about generalizing them to more general Riemann surface?
Maybe before passing back to Andy, maybe we could go to Kevin, because I think Kevin was waving with respect to your first point, and then we'll pass back to Andy.
Oh, I am sorry. I have forgotten about the hands.
No, it's okay. Don't worry. Don't worry. It's the relaxed part of the meeting. Don't worry.
Sorry, I just wanted to make a little comment about Andy's suggestion that one should use, because as we were discussing, the chiral algebra, or say the mode algebra, is much bigger than what is normally called W infinity. It's more like loops into W infinity. And quantization of that much larger object is really quite a challenging question. And my impression from studying anomalies for holomorphic field theories is that it doesn't always work. There are obstructions to finding a good quantization related to anomalies in the topological string. So my concern is that this is where one might run into difficult issues.
Maybe let's move to Shi, that we have I still have a few questions in line.
Hi. My question is closely related to what Ashok was asking, but I want to sharpen it a bit further. What is our expectation on, let's say, in a quantum gravity theory for the asymptotic Minkowskian spacetime? Do we actually believe that there's a mathematically well-defined S matrix of gravitons in the sense that it's a unitary operator acting on the Hilbert space? And if so, can we exhibit a countable orthonormal basis of that Hilbert space? So, I mean, I understand that there could be other kind of infrasafe observables. I want to ask specifically about the ordinary notion of S matrix. Can that actually be made sense in this context?
Remember, anyone can take up on such questions. Just wave or something.
If I can follow up, then
let's now give some opportunity for more new people to chime in. I'm trying to.
Of course, I
don't have a good, I don't really know. Maybe somebody else could.
Maybe. My impression was that this may not have been established, but even just the expectation. Do you think it exists or does it not exist? I don't even know what the expectation is.
I think the expectation is that there is a unitary S matrix.
And acting on what Hilbert space? That's the question. That's also part of the question.
Well, the Hilbert space probably will have to have these dressed states.
That's the part I don't understand. Are you saying that it's spanned by a countable ordinal basis of dressed states? And if so, can we actually write it down and argue that it's unitary? Because to me, the most naive problem is that because the infrared issue below a certain energy, below any finite energy, naively will write down an uncountable basis, and the naive calculation will tell you all the S matrix elements are 0. Now the question is there some clever basis in which the S matrix is actually unitary, and we can apply what we normally think is true for the analytic S matrix to the setting?
Yeah. Are you happy with perturbative unitarity, or you want to know in the black hole formation regime?
I would be happy to know the answer at a particular level already.
I think that we see no signs that unitarity breaks down.
No, but there's infradivergence.
Infradivergences, you know, since Weinberg 65, that they can be coped with. Precisely like Andy.
That's not a reason. No.
Let me finish. You don't have to dress the initial state. You only have to dress the final states.
The usual textbook resolution of divergence is not at level of the S matrix element. It's a level of the scattering probability. That is fine. But what I'm asking is whether there's a unitary operator acting in the Hilbert space. That was not the usual textbook resolution. So I don't understand that statement.
Or you do it with finite epsilon, and then you prove that for all epsilon there is unitarity.
I think you have to take into account vacuum degeneracy.
Well, that's all part of the question.
In the sense that you explained, Andy, that vacuum degeneracy, if it is spontaneously broken, you can interpret the graviton as the soft graviton as the Goldstone boson. So if you dress your final state by gravitational radiation, I have seen, I have done many calculations, and people who do the scattering problem in GR. You know, your question also refers to the collision of two black holes. I mean, do you expect it?
Let me clarify. You know, the S matrix elements themselves are not directly physical observables. I mean, I'm not saying that there's any physical contradiction. You know, the actual observable scattering probability, inclusive scattering probability, there's absolutely no problem. What I'm asking is whether the mathematical object of the S matrix as unitary operator on the Hilbert space actually exists, and that's not clear to me.
Well, you have to define your Hilbert space.
That's exactly my question. How do you define that Hilbert space, and whether you can exhibit a countable orthonormal basis?
But just so that we can still move on, but I saw that Simon wrote something in the chat, so maybe you can check there. But now let's maybe move to Eva.
Sorry, my question is a little orthogonal, but you'll see why it's related. So there's another approach to doing non-asymptotically ADS holography, which is TT bar-like deformation. So the TT bar deformation itself gives you dressed energy levels which agree with a finite patch of ADS, and then you can change the deformation in well understood ways to get the dressed energies to agree with the quasi-local energies of patches of other types of spaces. So it seems interesting to ask if one could do that for the flat space case. And if so, how would it relate to this approach?
Wait, you want to do a TT bar deformation of what?
So the way it works is you start with a CFT, which has a ADS dual. You do a TT bar deformation, and that brings in the boundary and gives you a patch of ADS that's finite. You can get down to where it's flat, and then add a deformation that, say, goes back out, but with a different geometry. So the way it works for de Sitter is you add not just TT bar at each step of this deformation, but you add a cosmological constant. And since it's a differential equation for the deformation, the cosmological constant enters into the stressed energy and enters into the stressed energy levels. And then, but in that way, you build up a calculable set of stressed energy levels, which agree with the Brown-York energies of a patch of space-time of different geometry than the original ADS. Okay, so it's a long trajectory from the CFT through this generalized theory space to a theory whose energy levels agree with those of a different bulk geometry. And people have mostly applied this to ADS and then to DS with flat space in the middle. So it's interesting to ask if when you do that for flat space, you go all the way back out, you land on something that would give you a way to identify this dual theory. It's a very different approach. It has its own set of questions and wish lists and so on. But it is an approach to holography beyond asymptotically ADS, which is under development. So I was wondering if it has any relation to yours.
You want to use this for a top-down construction of a dual conformal, of a dual field.
Yeah, exactly. It's a way of tying it to some known dual and deforming the boundary theory as you deform toward the geometry you want. And it involves interpolating in the theory space defined by Zalmovic and others, involving TT bar deformations and their generalizations. So for the sake of discussion, I'm just bringing up this other approach to defining holography in non-asymptotically flat spaces, and I think non-asymptotically ADS spaces. And I think it might be interesting to connect the different approaches.
I have a suggestion. I suggest that we thank Andy and Tomasz for a beautiful discussion. And I encourage everyone to, I think we should go to testing the share screen for the very last session. If you already thought of questions for the very last session, please go fill in the questionnaire. If you did not think of questions yet for the last session, go think of questions for the very last session, and feel free to continue on Slack, obviously discussing more on celestial holography. And thank you very much. And thank you again, everyone.
John, do you want to try to share your screen now?
Emil asks, where do we find the questionnaire? It's on the web page on home, but I'll also put it on the chat.
Pedro, do you want to start as scheduled?
Yeah. Which is, yeah.
So
yeah,
that's 7 minutes.
Yeah, in 7 minutes. Yeah.
Okay.
So Michael, I see you online also. You want to try to share screen, or is John, can you hear? So Michael, why don't you try while we wait for John?
Hello, I'm here.
Hey, does that work?
Okay, good, Michael.
Okay.
So what time are we going to start? I know we're late.
In about 6 minutes, 7 minutes.
Okay.
So John, you can try to share your screen now.
Okay. So what order are we going in?
That's up to you guys.
Michael, do you have an opinion?
Well, I thought we had decided that you go first, and then me, and then Edward.
That's okay with me. So, how does that look? I have to do something to share the screen, or do you do something?
No, you do it. So you can just click share
Where it
screen.
says share screen?
Yeah. You may need to, may give you an option. Okay, there it is.
Now I should be able to go to full screen.
Yeah.
Right.
Okay.
How's that?
Looks good.
Okay.
So I don't know, Ed, are you using the IAS node by chance, or are you someplace else? So I don't see Edward online, but oh, now he's online. Ed, do you want to try to share screen just to make sure it's still working?
But I did it before. It worked before.
Okay. Okay.
Well,
yeah, that's fine.
Okay. And I would go to full screen, which is this. And now we can unshare.
Yeah.
Remember, oh, here, stop share.
Okay, so we'll start in 4 minutes.
Okay. Are Michael and John on? Oh, Michael.
Hi, Edward.
Hi, John.
Michael.
Hi, John.
Hello, Hirosi and Nathan and anyone else who's here too.
It's a big crowd.
Okay, so good morning, good afternoon, good evening. So Pedro and Nathan asked me to chair this last session. And maybe before we begin, Pedro or Nathan, do you have any announcement to make?
No.
No? Okay, so now we can move on. So the format is as before. So we'll have a presentation by discussion leaders. We have 3 of them. And then after that, we have a discussion, question to the leaders and also discussion among us. So I'd like to ask them to give a presentation in the order of Green, Schwarz, Witten. And so could I ask Michael to start? First by sharing the screen.
Hirosi, I think we decided that I would go first.
Oh, okay. If you, if that's the order you would like, yes, please go ahead.
Can you see my screen?
Yes.
So I thank the organizers for allowing me to participate in this amazing meeting. They've done a fantastic job. The title of our session is supposed to be Perspectives on String Theory, Past, Present, and Future. And at this stage of my career, I feel more qualified to discuss the past than the present or the future. I hope that these remarks will be of interest to those who do not experience this period. So I will quickly survey the distant past of string theory and mention some of the key developments that took place. The choices were tough and subjective. So, as you're surely aware, the bosonic string theory developed in the late 1960s out of S-matrix theory, which was being studied as a potential way of understanding a theory of hadrons, and starting with Veneziano's famous formula, and followed by important work by Fubini, Verrazaro, Nambu, and a couple hundred other people. Since I want to emphasize the supersymmetric extension of bosonic theory, the first big blow was Pierre Ramon's formula for a free fermionic string. What he did was to find a string analog of the Dirac equation. It's a beautiful equation I like to call the Dirac-Ramond equation. A couple months later, Neveu and I constructed a second theory of bosons, and we quickly realized that our bosonic theory and Ramon's fermions fit together in a single theory, and demonstrating that was achieved together with Charles Thorne. It's hard to believe that this was over 50 years ago, and so much has happened in these 50 years, but it doesn't seem that long ago to me. A few months later, Gervais and Sekita wrote down a formula which for today maybe seems trivial, but was pretty amazing at the time. And it was simply a freeze action in 2 dimensions of bosons and fermions. And as you know, if you have the equal number of bosons and fermions, that's supersymmetric. But this was the first example in which someone wrote down an action and showed that it was supersymmetric, at least as far as I know. And this example motivated Wes and Zumina to construct 4-dimensional supersymmetric theories a couple of years later. And also the same year, Neveu and Scherk observed that in a suitable low energy limit, either the bosonic string theory or the RNS string theory reduces to Yang-Mills theory at low energy. And of course, that uses open strings with Chan-Payton factors. In 1971, Claude Lovelace argued for the necessity of 26 dimensions for the bosonic string theory. This was a real shock to people because up until this work, everybody assumed that we were talking about 4 dimensions. And considering anything else was regarded as preposterous. However, that attitude quickly changed. The fact that the RNS string requires 10 dimensions was soon understood. And various no-ghost theorems were proved first for the bosonic string by Brouwer, then by using a different method, Goddard and Thorne proved them both for both theories. And I used Brouwer's method to give an alternative proof to the RNS theory. In 1973, Yonea showed that general relativity emerges at low energy in much the same way that Yang-Mills does, but in this case, starting from closed strings. The following year, Shirk and I rediscovered Yonea's result, but we went further and proposed using string theory to construct a theory of all forces. This was a big conceptual breakthrough. It required shrinking our strings by 20 orders of magnitude. And we expressed optimism about the UV finiteness of the theory and the fact that in a theory of gravity, having extra dimensions could actually be beneficial. In '76, Brinkshirk and I obtained N=4 super Yang-Mills, and we did this by first constructing 10-dimensional super Yang-Mills and doing dimensional reduction. Soon thereafter was the famous work of Liazzi, Shirk, and Olive, in which they explained the necessity of projecting the spectrum of the RNS string in such a way as to give a space-time supersymmetry. And they gave evidence for that symmetry by showing that there were an equal number of bosons and fermions at each mass level, but they didn't actually prove it yet. The following year, Kremer, Julia, and Shirk wrote down the amazing formula for the action of 11-dimensional supergravity. This was a real shock to me. It was completely unclear to me where this fit into the greater scheme of things. The following year, I spent a year in Paris working with Shirk, and among other things, we studied how to break supersymmetry in string theory by using twisted boundary conditions and so forth. And then in 1980, Joel Shirk tragically passed away much too early. It was a great loss personally and for theoretical physics. And as you can see from this slide, he was really a major force in this field. In late '79, I began collaborating with Michael Green, and Lars Brink also participated in some of our work. The first thing we did was to prove the space-time supersymmetry of the GSO projected theory. And then we formulated and named type 1, type 2A, type 2B superstring theories, computed various tree and one-loop amplitudes. In 1983, we constructed an alternative worldsheet action that instead of having two-dimensional supersymmetry may be a space-time supersymmetry in 10 dimensions manifest. In 1984, we analyzed anomalies of the type 1 superstring theories, and we discovered that among all of the possible classically allowed gauge groups, only SO32 is anomaly-free. And we showed that E8 times E8 could also work, although we didn't know such a theory. And that was subsequently, of course, introduced by Gross et al., who found it first. So after a 10-year period in which string theory for unification attracted very little interest, the subject suddenly took off. Despite all the enthusiasm, there was also quite a bit of outspoken opposition to the subject. The main complaint, I think, was that it was far removed from experiment, which was certainly true. It's unfortunately still the case. However, as many very bright young people entered the field and amazing discoveries were made, string theory became mainstream. And this conference is a testament to its vitality. Thank you.
Thank you, John.
Over to Michael.
Can you see my screen?
Yes.
Right. So I have had a wonderful 2 weeks. It's been a fantastic conference, and I've been incredibly impressed by most of the talks. The organizers have done a great job in very difficult circumstances. They've set the standard for future conferences, and we will see what happens next year in Vienna. one of the problems with this presentation is that this conference has shown, as always, that string theory has developed into a huge subject that encompasses ever-widening areas of theoretical physics and mathematics. So it's very difficult to present a perspective that does justice to all of its richness. So what I thought I would do is just compare the way in which string theory originated with its present state, because I think there are lessons to be learned. I'll focus on one particular lesson that might be learned from it. So let me begin by saying that I was a postdoc in Princeton in 1970, and I was wondering how that might fit in with this talk. And then, of course, I realized that we're now 51 years later, and 51 is 3 times 17. 17 is a prime number. So I thought I would focus on perspectives as seen through a cicada rather than through my own eyes, since there are so many cicadas that have come out this year, and they were coming out in 1970 when I first went to Princeton. So let me begin by going back to 1970, and this will be the main part of what I have to say. So in 1970, let's imagine a very intelligent cicada emerging in Princeton after 17 years hibernating underground. So the cicada vaguely remembers being born in 1953, when there wasn't all that much happening, although at the time it would have seemed like there was an enormous amount happening. Quantum electrodynamics had been incredibly successful, and new particles were being discovered, in particular the mesons, and properties of the nucleons were being figured out. Isospin and strangeness quantum numbers were being discovered. But by the time this cicada emerged in 1970, a huge number of things had been transformed. In particular, there was a wealth of experimental data, and it's worth emphasizing this because, as others have pointed out, it's this experimental data throughout the 60s that eventually gave rise to the subject that we're talking about now. This is a subject which has been criticized for not having experimental data, but actually its evolution was incredibly based on data that was being discovered in the 70s. This was data on the strong interactions, when all sorts of concepts that we know about very well now were being formulated. So the idea of analyticity of the S matrix, the existence of quarks and their algebraic relations was being discovered. But my story that I'd like to emphasize is that there was a paper written by Regé in 1959 that was the beginning of what became Regé-Pol theory.
Michael, there is a request in the chat that maybe if you could come closer to the microphone.
I'll try. So
that people can hear you more clearly.
Is that any better? Hiroshi, is that better?
So, yes.
Oh, good. Okay. In 1959, Regé wrote a paper motivated, I believe, from his interest in the mathematical structure of potential scattering. He wrote a paper in which he introduced the notion of complex angular momentum. This wasn't based on trying to explain any experimental data, and indeed it didn't explain any experimental data, but it was an incredibly insightful moment where he realized that it was very interesting to define the angular momentum in the complex plane, to move away from the integers. And then, in a subsequent development, mostly involving Stanley Mandelstam and Jeffrey Chu, the Regé analysis was generalized by a series of basically of guesses to describe hopefully to describe the properties of the strong interactions. And that led to what we call the Chu-Fauci plot. So Chu and Fauci realized that if you plot the mass squared against the spin of in this case, the baryons, nucleons, you get straight lines. Of course, the straight lines are slightly obvious because those straight lines simply join a pair of points. There was very little data, and since you can always join a pair of points by a straight line, they had straight lines. But that was the beginning of Regé theory. Here is a modern plot. This is a plot of the row meson and its partners on the leading radial trajectory for the mesons, and it is a spectacularly straight line, that is part of the whole story that developed in the 60s. And then there were crucial observations following the development of dispersion relations. There were people who formulated some rules, and in particular, there were two groups, one in Japan and one in Caltech, who formulated what became known as finite energy sum rules, which showed that you could, in an average sense, you could equate the contribution to the scattering amplitude of Reggie poles to the contribution of resonances. That you could either think of the amplitude as a sum of resonances or as a sum of Reggie poles, and that became known as duality. And that's an absolutely central feature of what happened next. It was an essential feature of the Bootstrap that you don't add the S-channel and T-channel poles, you equate them. You either sum over one or the other. And I put in a note here that in a very early work, Hagedorn, essentially using the same sort of idea, came up with his with the statement that the spectrum of hadrons has to increase exponentially in order for this idea to work. And then this led to the work by Veneziano, the Veneziano model, who incorporated these ideas in this beautifully simple, absurdly simple formula, which is just the Euler beta function, essentially. As we all know, that is the origin of what happened next. And I'm going to jump over the next few generations of cicadas. Oh, sorry, before doing that, let me say, of course, I've concentrated on the strong interactions. Of course, there was work going on, incredibly important work, developing the electroweak theory at the same time, and then asymptotic freedom. But it wasn't work that had led to anywhere by 1970 that people were convinced by. And at the same time, other areas of theoretical physics involving relativity and cosmology were developing ferociously quickly as well, but they were somewhat disconnected from particle physics. So what we had was a group of subjects which were disconnected from each other, each one of which was advancing rapidly, but now we see that they're all part of the same subject. I put in a picture here of two books that were summarized the status of the Bootstrap ideas in the mid-60s. Two books with almost the same title. There's a hyphen missing in one of them. But it's worth just recording the opening lines of one of the books, the one written by my colleagues in Cambridge, which begins with the line, "One of the most remarkable discoveries in elementary particle physics has been that of the existence of the complex plane," which is, on the one hand, an absurd statement. On the other hand, it's an incredibly insightful statement, because that is what Reggie theory was all about. So let me jump quickly, and I've almost finished, to the present generation of cicadas, which has been bothering some of our colleagues in Princeton, from what I gather. This is a great-grandchild cicada of the one that came out in 1970. And he is, or she is, very impressed by the vast array of topics that have been discussed here. And I've sort of done a stream of consciousness list of these things. I'm sure I've missed many out, and each one of them has a finer grained division, which I haven't put in. But this is sort of the string theory universe. This is a set of subjects that we now talk about at string theory conferences. Why we call them string theory conferences, I don't know, because there's very little stringiness in most of these subjects, but somehow behind all of these topics is string theory. String theory has motivated the development of most of these topics. My last transparency is simply a set of questions that you've been asked to ask questions, but luckily I can also ask questions, because it's easier to ask the questions than to answer them. So I listed a set of questions which you've had circulated, I think, already. And some of them are actually questions which have arisen in the last day or so in the context of discussions by other people. So I won't read them out, but you have the list. And let me finally say once again that this has been a fantastic conference, and we are very grateful indeed to ICTP-SAIFR for organizing it in such a immaculate way. Thank you.
Thank you, Michael. So finally, Edward, can you take the turn? You are muted, Edward.
I think I had to stop the share to unmute myself. I'm sorry for the delay. So I wanted to, first of all, start by thanking the organizers for putting together such a special string conference with all the discussions and interesting talks, and also to thank them for inviting me. I, however, will be rather brief because of the fact that time is limited, but also because I'm going to only be discussing one question which I don't have an answer to, which is what is string theory? So it's actually amazing to know how much, as much as we do about string theory, yet feel one has no little idea of what it really is. There are two useful systematic statements that capture a large part of what we know. If you wanted to capture a lot of what we know in just a couple sentences, I would personally make 2 points. One is that a classical solution corresponds to a two-dimensional superconformal field theory that has a few general properties. And the second is that quantum gravity with negative cosmological constant corresponds to a conformal field theory on the boundary of spacetime. So these statements aren't everything, but they synthesize a great deal of what we've learned in the last half century in 2 sentences. I do want to elaborate slightly on the first one, although I had some reservation. I'm doing this because I found some people looking at my slides were confused, but elaborating on it is slightly off topic, so I wasn't quite sure if I wanted to. So the statement that a classical solution is a superconformal field theory, first of all, it has an elaboration in string perturbation theory where you use the same superconformal field theory to describe quantum fluctuations. It's actually one of the most fundamental statements about string theory, but there's a huge gap in our understanding of what it means, I think, because we have very little understanding of time-dependent superconformal field theories. Everything works perfectly in a time-independent situation where we have a unitary conformal field theory times a decoupled time coordinate. But if you don't decouple time from the rest, you really have a problem because negative dimension vertex operators, e to the I k x naught, enter the game. And therefore, marginal and relevant operators can have an arbitrary number of derivatives compensated for by their time dependence. So I'm afraid we have to imagine an effective action that goes on forever with derivatives of all orders. And I'm actually personally skeptical that it really still fits in the world of local quantum field theory. And I don't think we know what kind of world it does fit into. We can't just throw away locality without something to replace it. But we don't have anything sensible to replace it. Out of desperation, I'll just mention that the TT bar deformation, we don't understand what it is, but it doesn't seem to be a local quantum field theory. It would be great if it was the prototype of a new class of somethings, which you would need to make sense of time-dependent solutions. But that's just wishful thinking. Anyway, going back to these 2 statements, they synthesize a lot of what we've learned in the last half century. And it's notable that neither of them fits into the traditional paradigm that we learned in the 20th century, where we're supposed to find a set of fields and a symmetry principle and an action for those fields with that symmetry. The reason we have trouble with the question, what is string theory, may be that the answer, first of all, is quite different from what we're used to. It doesn't fit the usual paradigm. And secondly, I suspect the answer might be more abstract than we're used to. More abstract than something in the traditional paradigm of field symmetries and action. There's another clue, or at least another fact worth mentioning, which is that our understanding of the relation of string theory to quantum mechanics has gone through several changes. Before the era of non-perturbative dualities, it was reasonable to think, or at least I and I think many thought it was reasonable to think, that the truth in some sense might consist of finding the right new field symmetry and action, which would then be quantized in a possibly relatively conventional way, maybe using the BV formalism or something that isn't usually necessary, but in principle, following normal lines of quantization. However, the important role of non-perturbative dualities seems to contradict that idea. The theory seems to be in some sense intrinsically quantum mechanical, or at least have properties that are crucial and only come to light quantum mechanically. We don't know, we haven't made that much progress in understanding in what sense the theory might be intrinsically quantum mechanical, but possibly the current developments involving quantum information theory and gravity are leading us to a new general lesson that maybe will include a new understanding of the sense in which the theory is intrinsically quantum mechanical. Thank you.
Thank you, Edward. And I'd like to thank all the three discussion leaders for their presentations. So now I'd like to open the floor for questions, comment. Let's see, so Clifford raised hand. Let me see, yeah, I guess we can start with Clifford. Could you unmute yourself?
Hi, hopefully you can hear me.
Yes.
Yes, it's a quick question. I found, well, thanks all three speakers. It's very inspiring to reflect on our history. One of the things that struck me in Michael's presentation was his remarks about how much the experimental activity of the time actually did feed into what we now conceive of what string theory is. And I wonder whether Michael or any of the others have some optimism about what's going on now with the explosion of experimental data coming from astrophysics and cosmology and elsewhere, whether or not there could be some, you know, many years from now we reflect and find that indeed they did begin to teach us things about string theory. Is there some optimism there?
Could I just make a quick comment in addition to what I said? The point of what I said was partly that this story began, I mean, there were lots of things happening in the 50s, of course, but the story I told began with the paper by Regge, which was, in some sense, a purely theoretical paper, in which he suggested that using the angular momentum plane was interesting for certain problems in potential scattering, which were a million miles away from what happened later. So there's this interplay between Regge's sort of mathematically inspired paper and the huge amount of data that was coming in that was sort of a whole jumble of facts without any systematic organization. And really there's this rather extraordinary way in which the mathematical feature that Regge was stressing somehow fed into what happened next. And in this very roundabout way, the experimental data motivated what happened, you know, motivated in the end Veneziano's formula, which then became, of course, very theoretical again. So, of course, you know, in a sense, what I'm saying is, with all the developments that are taking place in the symbiosis between mathematics and physics, now we might hope for something to happen that would be very difficult to predict. No one would have predicted it in 1959.
If there is anybody else who wants to make a related statement, you can. Oh, okay, Andy, please.
Yeah, I think, you know, it's a really great thing if a theorist can make a prediction and it's measured and verified, but I don't think much of the stuff discovered at this conference is very close to, you know, being able to do that. But there's a much lower level of interaction that can happen, but this still is important and productive. It's just interacting with experimentalists and trying to understand what they're doing. And from my own personal experience, you know, partly because they're right next door and I'm friends with them, I've had a lot of interaction with the people on the Event Horizon Telescope, and all this stuff about the photon ring, it really has got me to, I think I've got more out of them than they have out of me. it really has inspired me to think about black holes and from new angles. And it's also interesting how much you learn when you try to explain something to an experimentalist. You thought you understood it, and then you try to explain it, So I think there's a much, to make a prediction is too high a standard, but just to sort of interacting and indeed with the torrent of data that is, we had a whole session on particle physics, but, it seems to me that particle physics data is drying up, whereas astronomical data is just exploding, especially around black holes. I don't think we're going to see Hawking radiation. I don't think we're going to see R-squared corrections or quantum, but I do think that just by the process of talking to them will jog us into new ways of thinking about things.
Great. Nathan, can you unmute yourself?
So this was a question for Edward, but of course anybody else can answer too. So before the non-perturbative dualities were discovered, you had some papers where you conjectured that topological strings might provide an unbroken phase for string theory, where the broken phase would have the metric, but the topological string would somehow be a phase with more symmetry. Has that idea changed with the non-perturbative dualities, or is that still an idea that's valid?
Well, I actually view holography as a somewhat similar idea, but better. Holography, roughly I said there were no local degrees of freedom. What holography says is a boundary correction to that statement. There are local degrees of freedom on the boundary. So I consider whatever I said to have been superseded actually by holography.
Thanks.
Okay, anybody who wants to make comment in this thread?
Yes, may I?
Yes, John, please.
Yes, on this question of connection to experiment, as you know, there was a lot of enthusiasm about the possibility of discovering supersymmetry when the LHC turned on. And my attitude at the time was that I really hoped they would find it, not because I felt that it would prove that string theory was correct, nor did I feel that its non-discovery would prove that it was wrong, but it was such an exciting possibility because we would learn so much more about fundamental physics from studying the supersymmetry, that it would give us a big step up in the energy scale towards a better standard model, which would give us a better target to aim for in the reduction down from 10 to 11 dimensions.
Clifford, did you raise your hand again? Or did you want to say anything related to it? Okay, so then we can go on to Kumran.
Yes, thank you very much for interesting talks. So my question actually is perhaps directed to Edward. As you mentioned, Edward, in your talk, one of the beautiful facts that we have discovered is the duality symmetries and the importance that things are related. In fact, in my view, that's probably one of the most important things we have discovered in string theory in the past few decades. But I don't see connections between that and quantum information theory, where you hope at the end of your talk that might shed light on questions like this. I don't see any hint whatsoever up to now that that's in the card, it's in the cards in some form. Are you seeing any hints of that?
Hints of what?
Quantum information theory, what does it have to do with dualities?
Well, I only made a naive comment in my talk. Dualities, to me, were the first indication that the theory in some sense was intrinsically quantum mechanical. I think with the connection of quantum information theory and gravity, that's being explored more deeply now. And it might, I don't know if it will, but it might lead to a deeper understanding of the sense in which the theory is intrinsically quantum mechanical. That was the hope I was expressing at the end.
But not to understand dualities in some sense, because dualities, for example, relate spaces in different dimensions, and quantum information in different dimensions have completely different structures and different meanings. So I'm not sure what that is going to teach. In other words, I feel that a lot of attempts in the current developments of string theory is pushed away from answering these kind of questions that are basic questions in string theory, like what is duality? Much less effort is being devoted to deeply understanding them, in my opinion. And I just wanted to know, since you felt that the final thing is actually going in the right direction, I just wanted to see what was your take on that?
Well, my only take is that we need a different perspective. Our progress in understanding duality, we made a lot of progress with dualities 20, 25 years ago. now we need a new perspective. Whether it will come from quantum information theory and gravity, I can't promise, of course.
I think Daniel is waving his hand.
Well, yeah, so she had this nice sort of classification of different kinds of dualities in his talk a few days ago. And so one of them was ADS-CFT duality, and certainly that one we've learned a lot from quantum information theory, Kumran. I think if you have in mind something like S-duality, then it's less clear.
Yeah, that's one of the dualities, of course, Daniel. My point is that duality is far richer than ADS-CFT.
Yeah. So, but I mean, some like in condensed matter physics, people have learned a lot of interesting things about using ideas from quantum information to study the
No, I'm not saying quantum information is not useful.
many-body
I don't think
systems.
it's central. That was my point.
But
it's not necessarily a central issue.
But I think understanding duality and understanding the dynamics and phases of quantum field theory are related also, right? So, I mean, and certainly
We should
quantum
understand
information
all
theory has been
dualities.
useful
That's
for
for
that.
sure. We should understand all dualities. That's for sure. Dualities should be understood. But to take one of them as pretty central, that's what I found surprising.
Nazi, are you raising your hand?
Yes.
Please.
I'd like to both raise a question both comment and raise a question in the same circle of ideas. It's clear that we need something which is intrinsically quantum mechanical. But it's also clear, at least to me, that time should also be emergent. And it's hard for me to imagine that these two issues are unrelated to each other. Because if time will be, I don't see how we can even think of quantum mechanics being intrinsic or not without having some pre-existing notion of time. And I don't see how perhaps the quantum information discussions will shed any light on it. But, well, I can go on and on. The short comment, I'll put some phrases: emergent time, emergent quantum mechanics, ... And I would like to hear some comments about that.
Mark, are you raising your hand?
Oh, I was just going to comment about the emergent time. I mean, I think even within ADS-CFT, if you look at time, say, behind black hole horizons, then I think that time should be understood as being emergent. It has very little to do with the time in the quantum system. So understanding that, I think, would be a good step.
Okay, Huang, you just turned on, so maybe you want to say something.
Yeah, so I just wanted to say that this connection between quantum information theory and gravity is teaching us better how to relate different objects in space-time to quantum mechanics and understanding the dictionary better. I think that's something new.
Thank you. Nadia, you are still raising your hand. Do you want to add something more? Or? Oh, okay.
Wish I had something more to add.
Okay, and we can ask Igor to turn on his microphone.
Oh, hello. I want to ask to the seniors, what are the fundamental problems of superstring theory itself from a formal point of view that you would still like to see a new look or a solution, as, for example, the equivalence between the R and S superstring and the Green-Schwarz formalism? Do we have a good description of an action which is manifestly supersymmetric and which we can quantize covariantly? Question of this nature, do you should believe deserves some new look? Can twistor theory help, or algebraic geometry?
Well, you're asking the list, so maybe we can ask others to contribute the list if there are any.
Of course, but thank you. Just for a new person coming to the field now.
I appreciate that. So maybe if there are people who wants to point out some particular theoretical directions to Okay, so Mark, you are still raising your hand and you haven't made a point this week, so maybe you can say something.
Oh, I just related to the connection with experiment. I wanted to just maybe encourage people in the field in general to maybe spend time thinking about this basic question of what could the underlying mathematical description of cosmological physics be? So it's been 20 years or, well, 24 years, and we've had this great microscopic understanding of how to do string theory with asymptotically negatively curved spacetimes. And I think we're learning a lot of things, as Juan mentioned, these connections between quantum information and the bulk are teaching us, I think, a lot of the nuts and bolts of how this works, and maybe, and also with the recent great progress in understanding low dimensional models, I think maybe we have a lot of good tools to sort of think about, what could the final answer look like if we had some microscopic model of cosmology, and I think that if apparently it's quite constrained since we haven't found it yet, and maybe if we find it, then if you just had one example that could teach you something about, say, dark energy or some of the really basic puzzles.
Thank you. Daniel, you want to say something?
Yeah, so one of the things that seems to have been lost in, at least for many people, is the sense that, we have this beautiful ADS-CFT, but ADS-CFT thinks that, for each set of ADS boundary conditions, you have a different conformal field theory, and it's kind of lost track of the idea that these are all different vacua of one theory, which is what was hoped and maybe still expected, earlier on. And in fact, many people who work on, like students who work on ADS-CFT today, many of them, I think, don't learn supersymmetry, don't learn string theory, somehow you can get by without knowing those things, even though actually all the examples still involve supersymmetry and string theory. And so one question I had, which is maybe more concrete way of getting at this, what do we know about, say, understanding from a field theory point of view that, say, ADS4 times S7 and ADS7 times S4 have the same 11-dimensional S matrix from the dual QFT point of view, or can we see somehow how those are related by duality to the 10-dimensional S matrix that we get from n equals 4 super Yang-Mills? Is this a totally intractable question, or could there be some nice field theory way of understanding it? I mean, from the field theory point of view, it seems like a total accident, right? That they would have the same short, S matrix at high energies.
Yeah, well, so she's raising hand, but I take my position to make a couple of comments. One is that, so there are actually a couple of very interesting talks during the conference, maybe relevant to this. One is the exhibition of 10-dimensional symmetries in ADS times sphere calculation. And also another is a very interesting work by Lorenz Eberhard, where so he pointed out that actually it's more natural to consider a grand canonical ensemble summing over different ends. And this is in some way considering different types of theories. And also summing over geometry can be incorporated at the perturbative string level. So there are some hints toward the possible direction to address Daniel's questions, but a couple of others are raising hands. So start with Shi.
I just want to add to that there's a systematic way to produce, in principle, a derivative expansion of M theory effective action, or equivalently, the derivative expansion of the graviton S matrix in 11D from the conformal data. And in fact, some time ago, folks at Princeton, we did this for the arc of the forest, but you can, and then it was proceeded further. But the explicit check of that stops at the order where things are controlled by supersymmetry. But that's mostly because our ignorance on the CFT side, if we were able to bootstrap, AVGN theory to more precision, then there's a hope of actually getting, the non-supersymmetry protected terms, the derivative expansion. I'm just saying that there's, in principle, a way to check that the ADS4 times S7 and ADS7 times S4 from the field theory perspective are, come from the same theory in the bulk, even though the because the details has not been recovered beyond the terms provided by supersymmetry yet.
Right. So of course, computing and checking is a good first thing to do, but it would be even nicer if we could somehow argue that they have to be the same based on some general CFT principles or something, including all the higher derivative terms in the action and so on.
Well, I mean, wouldn't we?
Excuse me, please
sorry,
go ahead.
I mean, of course, I agree that from the what we know from the theory side looks like a miracle, but I mean, we already have an argument. That's how the duality was proposed in the first place. So,
well, the argument is based on this idea that they're all vacua of string theory, right? So I was hoping that we could understand that more from the CFT side. I agree. It's what we expect.
Okay, Gabriele was waiting, so maybe he can.
Yes, thank you. Thank you for the three speakers. Since cosmology could be one of the places where string theory can leave its imprint, I was wondering if Ed could elaborate a little bit on his statement about time-dependent solutions, because does that mean that it will be hopeless to study the Big Bang singularities, or even what strings do inside the black hole horizons where time dependence is present? In particular, suppose I have a Kastner solution with a dilaton, which is at least the lowest order in alpha prime, it's a background. Would you expect to have problems quantizing strings in those backgrounds?
Generically, yes. So special cases like the linear dilaton makes sense. Some special things make sense. I'm actually skeptical that we have an adequate framework to understand classical solutions in strongly time-dependent spacetimes. I believe, well, first of all, I suspect that many of the younger people have no opinion on the question at all and may not be familiar with it. Among those who have an opinion, I believe the prevailing view might be that we just have a non-unitary but otherwise normal local conformal field theory. I'm actually skeptical for the reason I said in my short talk, that when you have time dependence, it looks like you have derivatives of all orders, and it looks like the world sheet theory isn't under any reasonable control. And I think that might be a sign of something important, although I've got no idea what it would be a sign of.
Well, that's certainly a very relevant point if one wants to study physics around the Big Bang.
Yes.
You don't only have, you have fast time behavior, even the derivatives are very large.
But of course, we're okay if the time dependence is slow, because then you have sigma model perturbation theory. We're also okay if the fast time-dependent fields are weak, then you have ordinary perturbation theory. But for strong and strongly time-dependent fields, although I don't know anything for sure, I'm skeptical that our framework is adequate.
Okay.
I think Andy is waving. Andy?
Could it be that when you study something in a time-dependent background, you have to say something about what the quantum state is? There isn't a natural quantum state. And so you have to put some extra data in to the string theory to compute scattering.
It's true you have to do that, but even in some cases that are under control, you have to do that. I think that's really a somewhat different point.
Nati, were you waving? My eyes are not very good, so I couldn't see.
I'm waiting, but it's on a slightly different topic. So I can wait if somebody.
Okay, so then in the order, Igor.
Yeah, thank you. I really enjoyed these three perspectives on string theory, and the cicadas this year were intense. I mean, this was really at the intensity frontier of cicadas, because I remember 17 years ago. But I was wondering if the three of you and other people could venture a speculation on what the cicadas 17 years from now will observe in the world of string theory. I mean, we heard about the spectrum of problems we're trying to solve. Is there any sort of guess as to what we will see, what the cicadas will see in 17 years?
Well, I would very much like to know.
You're going to tell us, aren't you, in a few minutes?
So actually, we are running out of time, but there are lots of people still. So maybe we can ask Shiraz for the last question.
This was just a follow-up on Daniel's question. It seems to me that part of the reason that the M2 brane theory and the M5 brane theory see the same space-time geometry when the space becomes big is that 11-dimensional, the completion of 11-dimensional supergravity is unique. And this is the kind of thing I think that we might hope to be able to establish somehow from low energy considerations. Some sort of uniqueness of gravitational scattering amplitudes or something like that in certain contexts. I think an easy target for this is to look for gravitational scattering amplitudes that are classical, namely that have only poles. And that space of known gravitational scattering amplitudes with only poles is very limited. And perhaps we could use low energy general consistency conditions to show that, to classify all low energy scattering amplitudes first with only poles, and then maybe more ambitiously, all gravitational scattering amplitudes in 11 dimensions or something like that, as a partial answer to your question.
Okay. So maybe Nati, do you want to make the last comment before we close this up?
I don't even know whether it's a comment or a question. Edward mentioned this way of thinking about string theory on the worldsheet with some C-hat CFT coupled to something. What is the status of strings in Ramon background, even time independent? So maybe Nathan could tell us something about that. Is this problem completely solved, or is it solved in principle? Because it's not a super conformal field theory with these conditions. It goes outside this description.
I mean, I can say that you have a sigma model where you can find a nilpotent BRST operator, and you can show that the cohomology of the BRST operator describes the physical spectrum. Can you use it to compute scattering amplitudes? Not yet. But
does this formalism exist for the most general case? Like the case without Ramon background, if it's time dependent, there is a very general description. What's the status of this with Ramon background?
So I mean, if we're talking about the pure spinor formalism, it's only defined for 10-dimensional supergravity backgrounds. So it's not, I mean, you can't describe the most general conformal field theory, but the 10-dimensional supergravity backgrounds that you can do. And, with Cormoran and Edward, we described also ADS 3 times S3 Ramon backgrounds. And that, in some sense, is closely related to the RNS. So at least you can show how it's related to RNS when you turn off the Ramon background.
He has some comment.
I think the pure spinor formalism doesn't address the time-dependent background issue, which, as far as I understand, has to do with the fact that if you can Wick rotate the worldsheet field into a theory that's unitary in the matter sector and obey the usual rules of local CFT. But I think at least perturbatively in the background deformation, this can be addressed in closed-string field theory, which is now completely formulated in SR formalism, with the PCO and vertical integration prescription. So that in principle allows you to treat time-dependent background perturbatively as a perturbative solution to the closed-string field equation. It doesn't theoretically enter what are observable to study, but at least there's a formalism that allows you to describe what the background is and the excitation on top of that background. And also, the closed-string field theory, just in SR formalism, allows you to describe perturbatively in R flux of a Ramon background. It does not deform the worldsheet theory because the string field still lives in the same old worldsheet CFT of the original undeformed NS background, but you can treat the R flux perturbatively. It's complementary to the pure spinor formalism. The pure spinor formalism, as far as I understand, is not quite complete a level of perturbation theory due to this 1 over lambda bar problem, but that maybe can be, eventually resolved. Whereas the closed-string field theory based on NSR can treat R flux perturbatively.
Okay, I wish we could continue going, but I think it's about time to close this conference. So before I give my own summary talk, I would like to show introduction for the next year's string conference in Vienna. So let me share the video presentation by Daniel Gruminer.
So thank you, Hiroshi, for granting me 5 minutes to talk about Strings 2022. And in the following 5 minutes, I'm going to address these questions: where, when, who, and what. So let me start with the first one. Where is Strings 2022 going to take place? It will be in Vienna, in the heart of Europe. Here you see a picture. Vienna, for a long time, leads various rankings of cities. More precisely, it will take place at the University of Vienna. So here you see the main building, the historic building from the 14th century. And even more precisely, we will be in this historic building, and this is literally the place where we'll have lunches, coffee breaks, and also the poster session in these arcades here. To be fully precise, the conference will take place in the largest auditorium, the Audi Max, which has 750 regular places and 4 wheelchair places, and this is literally how it looks now. And of course, we all hope that next year it will be accessible again to everyone. When is Strings 2022 going to take place? It will be July 18 to 22, so save the date and perhaps also save some travel money. Here are some known pre-Strings activities. There will be String Month in Warsaw in Poland the week before, and this is the main person to contact, Piotr Sukowski. And 2 weeks before, there will be String Fino in Liverpool in the UK, and the main person to contact will be Rado Tatar. And additionally, there will be local outreach activities in Vienna starting from March till July, organized by Benjamin Koch. And one of these activities I mentioned here, that includes the minting of a silver euro coin featuring a black hole in May 2022 by the Austrian Mint. So if you're aware of some activity, then please inform me. Who is going to organize Strings 2022? Of course, it will be a large number of people, but the main 2 organizers will be Stefan Friedenhagen from the University of Vienna and myself from the TU Wien. And if you have any questions, concerns, or suggestions, don't hesitate to contact us under these email addresses here. Of course, in addition, there will be the local organizing committee, the scientific program committee, and the international advisory committee. And if I may borrow a slogan from football tournaments, after Strings is before Strings. So shortly after Strings 2021 will end, we're going to reestablish the international advisory committee and also the scientific program committee. What is going to happen? Well, here's a reminder of how conferences used to be. It will involve talks with other people in the same room, random discussions with people queuing for coffee, joint intake of food and beverages, also known as coffee breaks, lunches, and conference dinner, and social activities that do not require internet. And on the downside, half of the participants might be jet-lagged. But more seriously, there will be, of course, again, excellent review and research talks, and perhaps we'll keep some of the techniques that we learned in the last year that were perfected in Brazil during the Amazing Strings 2021. But otherwise, the intention is to go back to the good old times pre-2020. And let me finish with 2 quotes that are sort of antipodal. So Brazil is the country of the future and always will be. That goes back to a book by the Viennese author Stefan Zweig, Brazil, Land of the Future. And the second quote is that Austrians look with great confidence into the past. So I hope to see you all in the future, in 1 year, in Vienna. Thank you.
Okay, so thank you, Daniel, for the virtual presentation. So now the organizer actually asked me to move on to my summary talk immediately after this. So I'm sort of chairing myself. So let me share the screen, my presentation. So, and then let me organize my desktop a little bit before I get started so I can see people. Okay, can you hear me? Good. So I'd like to thank the organizer for inviting me to give this summary talk. And before I begin my main task of summarizing the conference, I'd like to explain first why I think the summary talk is still worth giving, even in this time of online conferences. Why do you need a summary talk when you can watch all the talks on YouTube? Well, the traditional role of the summary talk has been to review and discuss progress at the conference, highlighting major development over the last year and looking forward to the future, and I will certainly do this. As I said, all the talks are on YouTube, but this conference has been for 2 weeks with 100 speakers. And if you have not watched all the talks live, the Strings 2021 YouTube playlist may be a bit overwhelming, and some guidance may be useful in figuring out which talks to watch and in which order. And I hope this summary talk will serve as a kind of TV guide for you. And third, and this is one of the most important, is an opportunity to thank the organizers. I should also tell you that the giving a summary talk is good for you. It forces you to pay attention to all the talks, taking notes, carefully and encapsulating each talk in a few sentences. I should admit that I have not followed all the important development in our field over the past years, and it is a great way to catch up with those I missed. So giving a summary talk is good for you. And if you have not done it, I highly recommend this to you. And then there is an issue with Olympic. So this is actually going to be my fourth time to give a summary talk. I've given one in 2004, 2008, and 2012. And you may notice that all these numbers are divisible by 4. This means that these are also Olympic years. So based on this observation, and following the standard practice in our field nowadays, it is natural to propose a conjecture that Olympic happens in the year when I give a summary talk. And, but this year is not divisible by 4, but Olympics scheduled in Tokyo last year has been postponed due to the pandemic. So when Nathan asked me to give the summary talk, I could not resist the chance to test the conjecture once more. And indeed, it seems like Olympic is going to happen in Tokyo this summer, and I hope it will be held safely. For the last 2 weeks, I have been living like in these cartoons, waking up before sun rises in California to watch talks and trying to make sense of them until I go to bed. So one of the wonderful features of the Strings 2021 has been the discussion session, the chat box, and Slack channels. And I recall some of the interesting comments being made there. They are not meant to be a summary of these discussions, rather they are snapshots of our experiences and are meant to be an appetizer for those of you who did not participate in these sessions live to go back and watch their videos. So now I'd like to tell you what I learned. So the first black hole and wormholes. So this is actually my summary slide from String 2004 in Paris. And you notice that there are actually themes that are relevant for this subject. This is a slide of Mathure's talk on fuzzball. This is a talk by Andy Strominger on black hole and topological strings. Liat Mautz gave a talk on wormhole in ADS. And Juan Maldacena talked about the 2D black holes. And you notice that Samir was worried about where are the states of a black hole. And Liat was worried about factorization programs. So those are the issues that are being discussed. And now in the past 15 years, interaction with quantum information has been very important. And those became evident in this Strings conference. For example, just before the Strings 2021, the AMPS paper appeared, and Rafael Busto gave an impromptu talk rebutting the paper, assuring us that we would not be burned to death when we're crossing the black hole event horizon. And the Ryu Takayanagi formula was discovered a few years before, and Tadashi gave a talk about that at the Strings 2011. And the connection to quantum information theory have inspired major development over the past decade. So ensemble average and wormholes. So Steven Schenker reviewed the bulk explanation of long-term behavior of thermal correlation functions and discussed the factorization puzzle. And Christian Jensen discussed how you actually can compute those things. And then there was a discussion session led by Jan de Boer, Steven Schenker, and Douglas Stanford. Again, how is the factorization restored? And the question of whether this is a low-dimensional artifact or whether it extends to higher dimensions. And there was even a question about whether type 2B string theory in 10 dimensions can be ensemble average. So the poll was taken about whether semi-classical gravity is an ensemble average or not. And it's evenly divided. There are even some people who are requesting recount. And JT gravity and SYK model has been a very important toy model to discuss these things. And there are talks on this subject. So for JT gravity, Tomasz Merton discussed the relation between UV gravity and JT gravity. In some sense, JT gravity is a Q deformation of UV gravity. And Clifford Johnson shows that JT gravity is a random matrix model and use it to compute various interesting quantities. And for SYK model, it has actually interesting condensed matter. That's where it's originally come from. And Gregory Tarnopolsky described it in terms of conformal perturbation theory. And Jeff Morgan discussed its efficient operator spreading on network and consequently its quantum advantage in quantum batteries. Quantum information and quantum gravity has been very important subject. And in Zhao talked about the meeting inside of a wormhole, how it is described in terms of quantum circuit. And Jeff Pennington showed quantum extremal surface helps to reconstruct the black hole interior, even for non-evaporating black holes. And Mukund Rangamani discussed the real-time replica wormhole, and Alex May discussed how the bulk causality is reflected on boundary correlations. And then there was a discussion on quantum information, black hole information program led by Ned Engelhardt and Rob Meyer with additional contribution by Chris Arkers and Dominique Neuenfeld. And one of the issues with the things discussed was the island formula. And there was a question about what kind of non-locality to represent. In this context, Eva Silverstein pointed out that string theory has non-local effect because it's an extended object, but are consistent with causality. And Edward Witten actually provided a very insightful comment about the distinction between evaporating black hole and burning coal. And then there were a couple of more polls being taken. And again, quite evenly split. So people are justifiably very confused. The technique to understand black hole microstate from a holographic point of view has advanced in very high sophistication. And Samir Mathur presented the calculation of superconformal index as sum of a complex saddle point. And Leo Pandozayas talked about log n corrections comparing both gravity and gauge theory. But these are sort of holographic boundary computation of black hole microstate. And important question is that how do you see this from bulk gravity perspective? And in this context, there was a very interesting discussion led by Juan Maldacena and Samir Mathur about the nature of place of fuzzball in this discussion. And during the discussion, it became apparent that quite a few of us don't know the definition of fuzzball. We are very good at discussing things that we don't know. And so Juan actually kindly gave the definition of that in Slack channel. Slack channel has been very important, useful. And again, there was a discussion of what's wrong with non-localities that appear in a recent development in rederiving the page card, etc. There has been great development in understanding ADS-CFT from microscopic point of view, in some sense proving duality. So Matthias Gabadier proposed a string dual for free n equal 4 super Young mills in the planar limit in terms of free bosons and free fermions on the worldsheet, and shows that spectral matches under some assumption. And Lawrence Eberhardt demonstrated that tensionless string in ADS3 with NS flux, the sum over target space geometry is carried out by string excitation. So that means that if you additionally sum over geometry, that's redundant. And so in some sense, perturbative string theory is background independent. And this also raises a possibility that perhaps you can solve the wormhole factorization program in this way. Kumran Buffer sent me a message saying that this redundancy of some of the geometry may be related to his cobordism conjecture. So and then there was a discussion led by Rajesh Gopakumar and Shi In on when you say proving duality, what do you mean to prove and how to prove? And then there was a description of some example where we have succeeded in doing that, like duality between topological cross-string and Chan-Simon theory. And more recently, this great development between tensionless string and free series. And there's a discussion about the place for Vasilyev theory in this context. And Ofer Haroni, ever precise about his use of word, says that it's very important to distinguish the notion of duality and correspondence. There are a discussion on non-perturbative approach. So Ashok Sen presented a very impressive calculation of the Stanton contributions without assuming S dualities and reproduced all these series. And in particular made a point that string field theory is very useful in these calculations. So this brings me to the discussion led by Yuji Okawa and Barton Spivak, very well choreographed presentation about achievement, progress, and recent development and open questions in string field theory. And there are lots of interesting discussion, like Nathan Berkovitz asked, what is the space of string field? And Shi pointed out that this is actually the only way to describe Ramon flux background systematically so far. And Ashok Sen again made a point that string field theory is actually a very useful way to systematize worldsheet calculation. There are a lot of discussion, development in techniques in amplitude and understanding them. So even application to LIGO physics, so Alfred Guevara reviewed how quantum field theory scattering amplitude can be used to calculate general relativity observables. And Frank Coronado demonstrated that n equal 4 super Yang-Mills calculation can reveal emergent 10-dimensional structure. So this was maybe something that related to Daniel's question at the discussion session before. And then Anastasia Borovich presented a very impressive development in calculation of planar n equal 4 super Yang-Mills amplitude with deep mathematical structures such as cluster algebra, parabic graphs, and tensor diagrams. And Freddy Cachazo and Lionel Nathan led discussion of worldsheet approach to these field theory calculations, in particular ambitwister string. And Nathan asked, well, in this approach, how do you integrate over the moduli space? And Rajesh asked how you can see the causality in the actual space line rather than in the twistor space. Again, there is a very impressive calculation of string perturbative string amplitude by Olivier, reported by Olivier Slotterer, please excuse me, and described 1 to 3 loop amplitude, no spurious dependence on location picture changing operator, and explicit integral over modular space have been carried out, and demonstrating agreement in NSR formalism and pure spinor formalism, and testing some of the S-duality predictions. Very impressive achievements. And then there are a very interesting discussion on high energy limit of string theory led by David Gross and Gabriele Veneziano. Wonderful overview by these people. And during the discussion, Juan pointed out that the Regge behavior in high energy is related to the Lyapunov behavior. So it's very interesting that there is a relation between high energy in the bulk and chaos in the black hole state. And Shi-In raised a question of to what extent, so these discussions have mostly been part of in the context of perturbative string or semi-classical gravity. So to what extent does the string perturbation theory capture the hard scattering limit? And S-matrix Bootstrap has been very, very powerful. And Leonardo Rastelli reviews the development of what he called a quantitative swampland program. And in particular, now you can actually incorporate the effect of gravity and proof that leads to the proof that large CFT with large gap has a local radius dual with sharp bound. And in this development, causality and crossing symmetry have been very important concept, and those are discussed by Simon and Sebastian. Then there is a discussion led by Penedones and Sasha Zivoedov. and about S matrix Bootstrap. And so actually, Volodya Kazakov, this is a little bit deviating from S matrix approach, but is there any progress in search of non-supersymmetric conformal feature in 4 dimensions? So these are still outstanding questions. And in some sense, this approach is complementary to a constructive approach of constructing landscape of theories. This is rather putting restriction on this. So this is very much like the swampland idea, which leads me to review the discussion on swampland. And this was first presented at String Conference by Cameron Buffer in 2006 in Beijing. Irene Valenzuela gave a nice review of the progress in this area for the last 3 years or so. There is now web of these swampland conditions and connected by these 3 basic conjectures, no global symmetries, weak gravity, and distance conjecture. And she talked about some new development and the phenomenological implications. Cameron Buffer gave another conjecture that the landscape of consistent quantum gravity theory is finite, and using species bound to relate it to various other conjectures, such as the bound on the type of topologies. So of course, these can have implications on cosmology and particle physics. So when I first gave my summary talk at the Strings 2004, the KKLT construction was a very important subject. And in fact, this was presented at Strings 2003 in Kyoto that I was one of the organizers of. And so anthropic principle was very exciting, and it even made it to the, my joke slide at the end of the summary talk. And there was a discussion led by Miriam Tvetik and Gary Hsu on string universality. And then there was an additional contribution by Lin Lin, Miguel Montero, and Pablo Sola. And during the discussion, Thomas Van Riet made a point that our first job in all of this should be to settle the question of modular stabilization and scale separation, because answer to this question can affect the choice we make in the phenomenological applications. And Eva Silvestre made a very important point that any universality claim like this must be consistent with all the ingredients of the theory we know and all the models we have. And Van Ramstonk pointed out the need for microscopic framework to understand the cosmological solution, something we just had discussion at a discussion session 2. Daniel Baumann and Eva Silverstein led the discussion of cosmology in string theory. The cosmology poses a unique challenge to string theory, and in particular because all inflation models are UV sensitive, and we have to pay attention to rich and highly structured landscape of string theory. Juan, in this relation, pointed out that there will be a precision measurement of the R coming up very soon. And so it's very important to understand before this R is bounded by experiment. And Mark van Ramstonk asked whether it's easier to construct a stabilized logita or rolling models. There was a question of whether you can actually construct the logita space from string theory. So Mariana Grana proposed a tadpole conjecture relating inequality between flux and the number of moduli. And then we heard one of the best line at the Strings conference this year, 10 to the 272,000 vacuum are not phenomenologically relevant. And then, however, Fernando Marchesano suggested there is actually counterexample to this conjecture. And Mariana rebutted that at the Slack channel that I would like to encourage you to review. And on the positive side, Gonzalo Torobar described the logita solution in M theory by compactifying on negative curvature space. But Edward Witten asked whether the construction is parametrically controlled. And then there was a discussion led by Shamit Kachiru and Fernando Quevedo. And Arthur Hebeker raised that the singular bulk program is one of the serious challenges to KKLT. And Sandeep Trivedi said that since we do not have parametric control in this construction, we should compute the first correction to check if the claims are reliable. And for this, we need to develop theoretical tools to compute Ramon background. And again, this leads to some of the earlier discussions. There was also a lot of discussion about the novel class of conformal field theory, surprising higher dimensional conformal field theory with large central charge, dead end, and sparse spectrum predicted by KKLT. So this is something that conformal field theory techniques such as Bootstrap can be useful in addressing. In discussing all of this, I would like to put this in context. So landscapers are claiming anthropic principle, swamplanders are claiming universalities, and I should say both are extraordinary claims. So it's important to test these ideas, and fortunately, a lot of technical progress has been taking place. Being scrutinized is a very good thing for you, and we should all support, encourage, and participate in this kind of activities. Changing a gear a little bit, again, in my summary talks at 2004, Mike Douglas actually predicted that no supersymmetry will be predicted, discovered at the Large Hadron Collider a few years before LHC was turned on, based on his statistical approach to study the space of string vacuum. And then there was a discussion about artificial intelligence in string theory this year. So Lara Anderson actually discussed a very interesting pattern on Yukawa coupling and the application of machine learning to calculate the metric in Calabi-Yau space, even in the case when you have a S3 structure and the structure is non-scalar. And then there was a discussion led by Mike Douglas and Fabian Ruelle of what can machine learning do for physics, or conversely, what physics can do for machine learning. For example, can duality turn a difficult problem, hard problem, into simple problem, for example? There was a long discussion of a thread at the Slack channel on this subject. Of course, we should confront experiment and observation, look for a way of doing this. This is something we discussed at the discussion session. Xavier Siemens reviews the progress of pulsar timing array and the potential to detect the effect from cosmic string. And Nima Al-Kani-Hamed and Ram prediction led discussion of particle physics challenges. And in particular, there are various opportunities such as fate of B-L and the relation of dark energy and neutrino masses and actions. And Gabriele Veneziano pointed out that if moduli are stabilized, we have predictions. So again, the modular stabilization is very important for us. Finally, I'd like to discuss the quantum field theory, because that's one of the techniques that we have that's very important to develop. So we have a discussion of effective long string. So offer Aharoni reviews the universality aspect of long effective string. And in fact, in particular, first several universal terms can be controlled. And also large and confining strings should have worksheet description at all energy scale. So that means that, again, he's very careful with his word. And in his definition of the word, they are fundamental strings. John McGreevy discussed the mean string theory as a generalization of Landau paradigm of one-form symmetries. And then there was a discussion led by Sergei Dubovsky and Igor Klebanov on QCD string. And then there was the discussion of asymptotic integrability of long strings that will come up later. And then there is a very important development on generalized symmetry and its application to new phases of matter. And Shufenshao reviews symmetry and their generalizations, in particular higher form symmetry, subsystem symmetry, and non-invertible topological operators. And then Sakura, Schaefer, and Nameki discussed theories arises from string theory that have no obvious Lagrangian description, and discuss higher form symmetry in this context. And then Jamo Gomez and Zofar Komorowski discussed when how to diagnose the existence of gap or gapless state by using these symmetries. And both of them derive necessary and sufficient condition for these conditions. So those are very important development. Horacio Cassini shows that there is symmetries related to certain simple property of quantum field theory, algebra region relation quantum field theory. And Damson discussed the new development in fractional quantum Hall effects. And then there was a discussion led by Nati Zyberg and Xiaogang Wen about generalized symmetry and in particular new phases of matter. And Xiaogang actually talked about swampland in condensed matter physics, and then there was a discussion of how much we can extend the notion of quantum field theory. So Stephen Schenker raised a point about the TT bar deformation. And then Nima Arkami-Hademe pointed out that where in this condensed matter swamplands, there is a completeness is very important. But in the context of gravity, completeness has to do with the existence of black holes. So what's going on? And Daniel Harrow has a response to that question. And integrability has been a very powerful tool in understanding a strongly coupled effect in quantum field theory. And Shota Komatsu reviewed the integrability of N=4 Young mills, and in particular discussed the finite T behavior, such as radius of convergence. And he actually demonstrated that in this context, there is a precise sense where a large N-Feynman diagram is related to string worldsheet in ADS. And Konkao when calculated the integral of correlator in N=4 super Young mills and shows the modular invariances. These are one of the formulas. And then Schwarz and Edward showed that the partial function of large N-Chern-Simons theory on S2 times S1 is the effective result of the Fock space constrained to the Witten singlet. Yuji Tachikawa used the Seagal, Stoltz, and Teichner conjecture to demonstrate the cancellation of Z24 global anomaly in 2D heterotic compactification. Michael Dushenko discussed the interface between different gauge theory with 8 supercharges. And Kevin Costello described a remarkable new quantum field theory in 4 dimensions that comes from 6-dimensional Twitter space by putting holomorphic Chern-Simons theory coupled to Kodaira-Spencer theory. And these theories, these 4-dimensional theories are apparently non-renormalizable, but there are no counter terms. And it has amazing property like integrability, periodic renormalization group flow, and relation to celestial holography. And then there was a discussion led by Volodya Kazakov and Gregory Kolchemsky on integrability and exact result. And then there was a question of how this is extended to larger class of gauge theory, such as non-conformal gauge theory. But in non-conformal theory, there was a discussion of asymptotic integrability, not exact integrability. And then there was a question of reduced SUSY. And very interestingly, just a couple of weeks ago, Eli Pomoni and collaborator posted a paper with exactly such a subject. So she described some of that. That brings us to the last day. And since we just had this talk, and I did not have time to summarize it, so I'll just present the list of talks. And but the talk, some of the important theme was celestial holography. And again, there was a common thread with other part of the conference, such as existence of W infinity symmetry. And so these are the list of speakers and discussion leaders on this subject. And then we just had this discussion on perspective on string theory by Michael Green, John Schwarz, and Ed Witten. But of course, other important talks, there are other important scientific activities. I think one of the wonderful things was that we had a gong show with this list of 11 speakers, and they're all wonderful. And of course, these are our futures, and I'm very happy to see them all. And poster session was also wonderful. There were 50 rooms, if I remember it correctly, and I visited several of these and had a wonderful discussion. There was also a very nice outreach activities, a public lecture by Jim Gates, and then Ask a String Theorist moderated by David Gross. It's opened with a question of what is string theory, something we just discussed also. I'd like to make a couple of comments about demographics. So first of all, this was the largest strings conference ever, both in terms of number of participants and speakers. And I'm happy to see that 80% of speakers were female. And in this context, there was a discussion led by Miranda Chen, Chiara Nappi, Shruti Paranjape, and Silvia Penati on women in string theory. And a very important point was made about the issue of pipelines. There are several bottlenecks in career of female theorists, and we need safe and inclusive and welcoming working environment. And we should be careful about unconscious bias, and outreach, mentor, and child care support are important. Henrietta Edelman pointed out in the Slack channel that there is actually a study in University of Michigan about pandemic inequality. So some of us think that, well, the pandemic has been actually very good for me because, well, we can stay home, we don't have to travel, and we can be productive. But that's not always the case for everyone. And in fact, 1/3 of the people reported in the University of Michigan that challenge due to caregiving, such as family with young children, have caused challenges in this. And this issue needs immediate attention. So in all of this context, I'd like to make one advertisement that at the Kavli IPMU, actually, we are soliciting application to assistant professor in STEM gender research. And just so that research can be done to find out what we can do to address these issues based on evidence-based research. And if you have anybody who may be interested in this type of position, please let them know. Another question is that, are we getting younger? So, well, I can't tell you how old you are, but I can see the year that a speaker got their PhD. And from that, I can at least see that where I am among all these speakers. And so I have data from the past years when I gave summary talks. So at the Strings 2004, I was actually a younger part of the speakers, but my position gradually declined. And now I'm at the top 22 percentile of speakers. And amazingly, this actually fits very well with this linear curve. So what this means is that there is a constant flow of young people coming in, which is a very good thing. There are other things you can deduce from this formula, which is left to the exercise of the audience. So there is actually also chat and Slack. That was a very important feature. And I actually solicited the comment over SNS from participants, and I got a couple of them. One of the distinguished string theorists pointed out that organization of this year's Strings conference has been amazing. I've never seen this level of open, honest, reflective discussion in a conference with more than 300 live participants. Another distinguished theorist sent me a message saying that this type of format makes the conference much more accessible experience for many. And the organizer has done a superb job. And in particular, Pedro has been consistently amazing in moderating discussion. And of course, I would like to also praise Pedro for the organization of leading of the discussion. But there are also many others who worked very hard in the background. I have organized the Strings conference 3 times at Santa Barbara, in Kyoto, and Okinawa most recently. And I know that these are actually non-trivial tasks. And so I'd like to take this opportunity to thank people who made this conference possible. First of all, our host, ICTP-SAIFR, led by Nathan Berkowitz. And these are some of the council members, former and current council members who contributed to this conference. Of course, running conference requires some fund, and these organizations supported the conference. And last and not least, I would like to thank the local organizer for the wonderful experience we have had over the last 2 weeks. And we'd like to thank the next year's conference organizers. And I hope to see you all in person next year in Vienna. And instead of before I close, and instead of asking for questions from the audience about my summary talk, I'd like to request local organizers and staff members to turn on their video so that their contribution can be acknowledged by the participants. So first, let's wait until they turn on their video, and we should all clap and thank them for the experiences that they have given to us for the last 2 weeks. Thank you very much.
Thank you, Hirosi. Before everybody goes away, can you do us a favor and turn on your camera so we can just take a picture of everybody? So we're going to just take pictures of everybody with the camera on. So it'll take a few minutes because we have over 300 people. So just stay on for a few minutes. Tiago, you're taking the pictures, right?
Right.
You should send us a cue when you take what pictures.
Yeah, I don't know which ones he's taking which, so you won't know.
Okay, just wait a few minutes because not too fast.
Okay, just tell us when you're finished.
Okay. It's done.
Okay, so thank you, Hiroshi, for their wonderful review. And please fill out the questionnaires if you haven't done so, and see you next year.
Thank you so much.
Thank you.
Thank you.
Bye-bye.
Thank you. Thank you for everything.
Thank you.
Thank
you.
Bye-bye.
Thank you. Thank you. Wonderful.
Thank you, Nathan and Pedro and everyone.
Thank you.
Fabulous.
Thank you. Bye.
Thank you, Pedro.